just for making an announcement. Okay. For people from overseas, I'll just explain what that is. In Australia, the Aboriginal people are very badly treated, and so it's becoming good practice to acknowledge that they were the traditional owners of this land that we're on. And so you'll find that increasingly in Australian meetings. Before I hand over to Sarah, just one thing. At the end of each morning session, we have a discussion, and each chair is going to organise that discussion sessions differently. I'll be doing this morning's one, and I'll be asking the speakers and the audience just before lunch a question. And the question is, what do you want to get out from this week? What do you want to get out from this week? And so for me, it's probably obvious. So we're building these telescopes. I'm leading a project which is going to discover, we hope, 70 million galaxies. Okay, that's good. It's a factor, it's 2 orders of magnitude bigger than any previous radio survey. And I suspect that the way we handle the data and extract the science from the data is going to have to be completely different from anything we've done before. I think the approaches we'll take will be very, very different. And what I'm hoping to get out from this week is here's really good ideas on how we can tackle that problem. So you've probably all got your own ideas, and I'd love to hear them just before lunch. Okay, without any further ado, I should say Lewis Ball, Chief of CSIRO Astronomy and Space Science, sends his apologies. He wasn't able to make it today. But I'm very pleased to welcome Sarah Pearce, Deputy Director of CSIRO Astronomy and Space Science. Sarah.
Thanks very much, Ray. Welcome everybody to Marsfield, to CSIRO Astronomy and Space Science, where we are, for those who don't know, the host institute for the Australia Telescope Compact Array and for Parkes, the Dish, more colloquially. If you haven't seen the movie of the Dish, I highly recommend it to you. You should try and see it while you're here, so you get the whole cultural experience. We also host ASCAP, the organisation, which does research in areas as diverse as climate change, molecular biology, minerals and water resources. It goes from basic research, we're really at one far end of the spectrum in CSIRO, looking at astronomy, to research that directly addresses national priorities, for example, future manufacturing. But the cross-fertilisation between the basic research and the industry-focused research is enormously productive, as exemplified by the invention of high bandwidth Wi-Fi in this very building by John O'Sullivan. John's team were working on an astronomy problem, but ended up solving a $1 billion industry challenge, and their algorithm is now in the 802.11 standard and in your smartphones and your laptops. And proceeds from that continue to support innovative science in Australia, both in CSIRO and across the innovation system in Australia. We work closely with industry, and I'm pleased to welcome our representatives from Microsoft, Tony Hay and Dan Fray. So I actually know Tony from my previous existence and Tony's previous existence. So I used to manage the particle physics computing grid in the UK, and Tony led the e-science program in the UK at that time.
Most people go, what's happening here? But first of all, I'd just like to introduce Kate Chow as well, who's on the organ. It's time to evacuate and follow the warden's instructions if they hear a little bin for them. So you're off-site in that room. Then also the most important code with it, but you never know, no torrenting or anything else, please. Furthermore, posters, coffee and tea you've already seen is in the breakout area there, and the posters will be in the room over there. Lunch will be served there as well. We also have technical help, so if you really have problems with your computers or anything, you might have seen Nathan Pope before. He can help out, so I'll direct you to him. Furthermore, there's a couple of goodies from our sponsors in the bag, so just to clear up, there's some Amazon vouchers in there. They're for Amazon Web Services, not...
You talk about all sorts of things, and hopefully you try to say something sensible and not something idiotic. So my goal here today is to think at the highest level about why. So big discoveries in astronomy have come really over the last century from a variety of places. For example, we have quasar lensing as shown in this image that was not really expected, but came about in the rate of the universe. And it just happened to be that the universe was doing what we were able to date a lot more out of our science than just what their original initial intent is. So for example, if you look at Hubble, he went out and probably had some help from friends to know to look for the expansion of the universe. He never claimed this, but it was pretty clear he had realized that various people were making predictions and it was something worthwhile to look at, I think, in retrospect. You have someone like Bato realizing that there are multiple populations of stars. This was made possible by being able to image for the first time stellar populations in the Andromeda galaxy, made partially possible by having telescopes that suddenly were in dark skies thanks to the threat of bombing missions from the Japanese. Fritz Zwicky was always willing to think outside of the box, and he did so. Not necessarily with the best equipment, but he was always able to go through and take data and see it in new and exciting ways. Penzias and Wilson were out, of course, trying to do an experiment in galactic astronomy, got confused by a background signal they could not get rid of, and of course they looked towards Princeton to solve what their answer was, which was the cosmic microwave background. Bell and Hewish found something in their data, doing something perfectly sensible, again, a survey, but they saw something they didn't expect. Those are all individuals working on experiments. Hugely effective facility, and it's been made effective partially due to things it knew it was going to do, but because it was such a lot of data, it has enabled 5,600 papers that maybe most of which were not expected. So if you look at some of the major papers, there's obviously the data, and there are literally thousands of interesting papers written on all sorts of topics. But there have been some major ones, and if you look at the major ones, for example, discovering what looks like the end of the epoch of reionization with quasars, that was sort of forecasted, but they didn't know what they were going to see. But it was made possible by giving people access to the data, even within the consortium, because of course the Sloan consortium was not 10 people, but who knew they were going to find as many objects as they did. They sort of opened up fields in this area. Dynamical asteroid families, I think, was not at all in the plan, just made possible by data. Hypervelocity stars, not in the plan, but made possible. Baryon acoustic oscillations is something made possible again, not originally thought through. The interesting thing is most of this was done by members of the SDSS consortium. A couple of them, hypervelocity stars, low surface brightness galaxies, were not papers that come, well, many thousands of papers come outside the consortium that are interesting within the different areas. There is a common theme. Most of these are not the major selling point of the Sloan Digital Sky Survey. Major selling point of the Sloan Digital Sky Survey was large-scale structure. And of course, that field moved on a lot between inception and being done. And of course, they have made major breakthroughs in that area. but Sloan has been so successful because they've done so much more than that. And it really was made possible by getting into their database and write the nature paper the next day. We like to think of it being that way, but it almost never happens. And so it's going to happen in the future, I predict, the same way it's happened in the past, by people thinking, well, maybe this is a question, and being able to get in and answer that question. It may be something that no one else had, but it requires hard work and dedication. So I would argue that the key of discovering the unexpected is allowing widespread exploration, not blindly exploring. And so I give an example where blind exploration is sometimes interesting, and this is the, help me, Forver? Yes, Forver. The object that was not expected, we don't really even understand it that well. It's a blob of gas being ionized, presumably, by something going on inside of this galaxy. Most of our detection algorithms would have just thrown this out as some artifact that we didn't care about. It was identified by a school teacher in Holland, in the Netherlands, through the Galaxy Zoo type programs as being something that didn't really fit the mode of everything. And so there are objects like that. We can go make big discoveries. But most of the discoveries are not going to be made, that's easy. But having unique and interesting, that is something that has information, that is considered interesting by the scientific community, that is a very unique thing that SDSS did right. So, from my perspective, SDSS increased by about 1,000-fold the precise multicolor photometric data sets available to astronomers. It wasn't a factor of 10. It was a huge leap forward. The data itself was rich. It identified the nature of 10 to the 9 objects. Optical data provided things like redshifts. It told you what type of object it was. For stars, it told you their temperature, rough composition, all sorts of things. And so when you saw something, you knew pretty much what it was. And since it was such an increase, that really enabled all sorts of things to happen. And I would argue that this level is going to be essentially impossible to repeat. You'll never, ever be able to increase things with a richness of data sets by 1,000-fold. We can go through and increase things by 1,000-fold, but it's the actual information density in that extra increase is not going to be as high. So does that mean we all give up? No. There are other things. We just need to be a little bit more clever, I think, how we do things. I would argue that essentially every data set worth taking is unique, and so to get a project up, a survey up, people are making arguments of why they want to do it. That's the classical, what I would describe, hero mode, or where you want to go out and you want to do some projects. So the data is clearly unique to do that. And so the key is finding the uniqueness of these data sets and linking these data sets and their unique aspects to the greater astronomical world provides lots of opportunities that were not available in all of those projects I just told you about. You know, Hubble did a great job just linking to Slipher's data set to be able to measure the expansion of the universe. That was a profound thing. The fact that it took 15 years to make that connection, I think, is quite remarkable. But that is something that I think what we're trying to do for this week is the key. Being able to link interesting data sets together to do better science. And so connecting data sets is currently at a time where we are taking information at different wavelengths and even different non-EM sources in the near future of every object in the sky to a given flux level sensitivity through these surveys. The new opportunities come not just from the uniqueness of the data set, but from also putting together these disparate sets of information to answer new questions. And that seems obvious, but it is also, I think, where the power of people's research is going to come from the work that we're trying to do. And so I would argue that accessing data, being able to nimbly manipulate and explore data is the key factor of scientific creativity. And that's because being able to ask questions and try things out quickly is the way you get to try tens or hundreds or even thousands of ideas out. If you have to spend 6 months to go in and just try something out and it doesn't work, it slows you down. And the thing that allowed me, for example, to get on with my work of measuring the accelerating universe was at the time, relative to my peers, I was very good at being able to manipulate and explore big data sets. They're considered very big now, but they were big then, and that was the skill I brought to that problem. And it's the skill that I feel like I don't have as well as I used to because people have gotten so far out in front. But certainly the best students and best researchers that I see in data-intensive science are the ones who can more nimbly go through those data sets because they have the ability just to go and do all sorts of interesting questions. And like it or not, most questions that you ask turn out not to be very good ones. It's just the few good ones that are valuable. And being able to make it really easy to go in and say, well, how would this correlate, this object correlate if I could see it in gamma rays? Oh, yeah, that was an idea, it didn't work. Next, let's just keep going. If that, as I said, if that takes you 15 minutes, well, that means you can do so much more than if it takes you many, many days. And so now we have databases for easy access. 20 years ago, we really didn't. We have tools for easy access. Those tools, I would still say, are much better and much more widely used than they used to be. But it's a place where I think we can do even better. So I would argue that we need toolkits instead of tools. So the tools of my PhD studies were IRAF, which is anyone who's used will know that I always say to hit on that and then get a vector out. Can't quite do that with these tools yet. And that means that you end up having to rerun or rewrite or redo things, and that's ultimately inefficient. So let's think of the new world. I'm just going to do a quick poll here. I want everyone to think of what their main scientific computing language is right now. Okay, and I have a feeling we're going to have a gradient by age, possibly by discipline, but I might be wrong. Okay, so you're going to think what it is, and I'm going to give you a few. So let's try Fortran. Anyone game to put a hand up for Fortran? All right. So, boy, Andrew, you're pretty young to be a Fortran man. Okay, so Fortran. C or C++. Good. That's probably me as well. Okay. Anyone want to claim Perl? Excellent. All right. How about Python? Yes. So my point is the following. It's a new world. Astronomers are currently using Python, and even I am using Python, and I'm terrible at Python. Whenever I write Python, I'm always amazed. It's like, my God, I wrote something in 6 lines that would have used to take me 500 lines in C. And it doesn't run as fast as C, and I always feel good that my C code runs 100 times faster than Python, but it takes me 100 times longer to write. And so, we live in a world right now of Python. Providing a toolkit written in whatever, C, C++, you can link to almost anything if you have the effort to build up libraries. Linking that to Python is a winning strategy right now, in my opinion. And the reason is just because we have all these toolkits. And one of the reasons that Python is so effective is simply because you can build things up with toolkits. So I had one of my young postdocs came in, and we have an integral field spectrometer. And integral field spectroscopy is notoriously challenging to reduce. And we had built up an image reduction pipeline, which quite frankly wasn't very good. People worked on it for a couple of years. And this guy came and said, oh, I can use these Python tools I've got. And within a month, he had something that worked, quite frankly, 10 times better than the previous one. Because he had the right toolkit. And that, again, is the power. And not only was it easy to write, it really does make that data set probably a factor of 3 better, more sensitive. It makes the instrument 3 times more sensitive because it just does the right thing with the data. So once you have a toolkit, you can build tools from this toolkit for use, not standalone tools. I would so much love to have our new, let's say, the people in this room, and I know some of you are here who are working on, for example, source finding within radio regime, which in data cubes turns out to be a slightly different, and I would say there isn't a standard tool within the community right now how to do this. But as we build those up, let's build it in a toolkit that other people can use and then put into the Python environment, rather than have source extractor radio, which then is stuck there in that regime and not easily transported. That allows other people to build tools up, modify the tools, and we all build on each other's work. And so being able to build up and share new tools from a common toolkit is a place which was discipline, requires discipline, but it allows us to more effectively build on each other's work. So I always argue that science works best when it builds on itself. So I like the idea of what I describe as value-added data sets, where, let's say I have the Sloan Digital Sky Survey, and I'm the quasar person, and I run a nice, KDE analysis of the Sloan Digital Sky Survey, and instead of having 1 billion rows, I end up with 70 million rows of quasars with what I think are the probability of them being a quasar, their likely redshift, whether or not you have other stuff. That's an interesting data set. What we need to be able to do is come up with a quick way that once I come up with that data set, I can publish it and link it in to the toolkits that everyone else is using. Then others can build up on that. Right now, those tend to take a couple years. They get stuck somewhere. They get out there, make our best decisions, and build on the work of others. So, my vision, and this is my vision, and what I'm hoping is it won't exactly be your vision. Hopefully it's, aren't repulsed by it. And I shouldn't say that this is a completely, I think this is a pretty standard view, is that if we have a future of interoperable toolkits, those are toolkits that you can build up on each other, built into shareable tools by the community, and that those are acting on interoperable data sets, which can be built into new data sets, these value-added data sets, which are once again interoperable and shared worldwide. So it's a complicated vision. And so you're really making toolkits, making tools, and those tools then become part of the toolkit that allows you to make even bigger tools. In the same way, once you have those tools, you'll work on the primary data source, you create secondary data, and then you can operate on primary data and the secondary data sets to do new things. The problem, of course, is actually doing this. And so now I'm going to sound like a hypocrite. I have my own data set that we're beginning to work on, the SkyMapper Dataset. So the idea is to essentially do a survey that is analogous to the SDSS Digital Sky Survey. It will be probably have 4 or 5 times more data than the SDS because it's multi-epic and does about 40% more sky. And right now we're working on providing tools for the community within the VO framework, so we just dump data to the existing tools. We do not have the resources to build our own toolkits, I'm afraid. We have to essentially use what other people are using. That means we're not going to do anything horrible and invent new standards and things. But it means we're not really able to add too much to the community just due to resource constraints. I really want to allow users to build their own value-added data sets, where they go in, for example, and say, here are all the quasars, here's a photometric redshift catalog. But it's not clear to me how we can easily right now link this up for the broader community. I'm sort of a, yeah, you can go run with our data, but then where does that data set end up and how does it get linked in? That is something I think is still a little nebulous region. It's not done terribly well yet. And we can talk about how we might do that. But that I see as being the best way to get information out to everyone. So So I guess the real question, as I finish up here, is, you know, I think for long term, because we're going to invest all this effort in these tools, and if they become obsolete, we have to have a way of replacing them and moving them on to whatever the new framework of which we do our work is. I think resourcing this is also a problem. We scientists like to do the science. We're okay programmers, but we're not great programmers. We tend to hack things together so we get our paper out, rather than do a good job of, you know, coding and document. And this type of stuff I'm talking about require a very professional, organized approach, which is more of engineering than science. But the reality is we don't have the resources, or we do have the resources, but we choose to spend them on new computers, new telescopes, and new postdocs, rather than paying engineering or computer science consortia to go out and do what we need. So resourcing, what it's commonly referred to as middleware here that enables these things, is a problem within our community. And it is important. It's not very, from my point of view, it's not that interesting as a scientist. I just want it to work. But the reality is it's a big, hard problem for our community to resource that. And that, as I see, as being the key questions of astroinformatics. And I'll stop there. Hopefully we can talk over some of these issues.
Thank you very much, Brian. Let's have some questions.
So, Brian, your idea that data sets need to age gracefully is arguable, I would say, to some extent. I mean, do you think that in 20 years' time, so we've got LSST, SKA, all these, all these big surveys coming along, which will produce more data than before,
Yep.
et cetera. How much value is there in the data that's still around that we're using now, when most people will actually be focusing on these much larger data sets that are coming, and that probably they will be doing science. I mean, will people still be doing science with Sloan when they've got
So there's an interesting question. So I'll answer it. Depends on uniqueness. So let's say you do LSST. That's great. Southern sky only, Sloan northern. LSST saturates at 18th magnitude. There's a lot of stuff brighter than 18th magnitude. SkyMapper has this UV thing that allows you to do stellar stuff that LSST won't have. And there will be the time domain baselines. So there will be some uniqueness, and it may not be, so my guess is it will be useful. I often go back and refer to DSS images, even today, where Sloan is, specifically for the time domain aspects. So the data sets, I actually see making them age gracefully probably not as hard as the toolkits, the actual software that we end up building up. I mean, source extracting and all that stuff, do we want to retweak that and rebuild it into a new platform every 20 years? That's a huge amount of effort for someone. And, if someone has a brilliant new idea, all for it. But if it's just the same old stuff, how we move that, and the difficulty is you build up these toolkits, they're very valuable. On Ensemble, the reason Python is so valuable is not because Python is such a great programming language, it's a good programming language, but it's because everything an astronomer needs is there in one place. You don't have to rebuild stuff. So how we move that to the future, that's what I see as being quite a challenge, because you have so much vested interest in that toolkit. And then we're going to get split where toolkits will come in maybe from computer science in a different language, and we're going to be trying to figure out how to move on, and that moving on gracefully, I think, can be very challenging. Just yell and I'll repeat the question.
I think there is one other issue which should be taken into account, which is accountability. Because with these huge data sets, even if you want to run the most trivial tasks, you need computing power problem.
Yeah.
So these toolkits should also be thought for a scalable environment.
Can you repeat the question?
Okay, so the point being is having scalability for big data within toolkits. And I agree. one of the nice things about having a toolkit what other people can learn on is imagine you have this toolkit and someone writes a nice algorithm that's not very scalable within the Python library. Then one can imagine that some smarter person come in and say, actually, I have a good way of speeding this up. The problem comes when Python itself doesn't scale in the way you want, or that middleware I'm talking about we need doesn't scale appropriately. And that's, again, where you need to have the computer scientists in there being very professional about what we do, and having very clear vision within the astronomy community of what we need in the future. And it's messy, and right now, we're not disciplined enough, I think, to do it properly, is what it really comes down to it. Because, as I said, I personally spend my resources just trying to do my thing, and I don't have a donate $100 to the central fund button whenever I use a VO tool or something.
Let me ask you a follow-up question. So, it's very nice, this idea. You get stuff on your laptop and you run it as a Python script. But in practice, many of the databases we're talking about are petabytes databases or many terabytes, and you're not going to have those on your laptop. You've got to access them on some server somewhere. You're not going to be writing, I don't think you're going to be writing Python scripts.
I think you're going to write a Python script through an API that then uses the server side to go through and do stuff on that side.
Okay, so what you want are things like VO tools and things to do that job for you.
Yep.
Do you see that work happening? Are you optimistic about getting the tools so we can actually do that?
Well, I mean, we're getting them, and I'm actually pretty impressed where we are, given it's hard. It's a hard space to work on. It's hard to resource. But, we do have a set of fairly, basic tools now, which are useful, and we're certainly going to use in SkyMapper, because I don't have anything else to use, and I'm not going to roll my own and give everyone say, oh, here's my own brilliant idea. I just, that's the wrong thing to do. The question is, how are we going to resource, future tools that are more sophisticated? And how are we going to do it? I mean, big surveys will do this. LSST will do this one way or another. But how are they going to do it versus Gaia doing it? There are big programs that have it. And are we going to have something in the end that talks to each other, that's the same format, which would be ideal? Or are we going to have one version here and one version here, which are completely different, which is what I fear. So the difficulty is it will be more expensive for Gaia, it will be more expensive for LSST to do something that's common, has a common framework, because it's just not going to be the most efficient way. And I don't have a winning solution how to do this, except for saying, as a community, we have to think of ways of having a very clear mission of what we need in the core there, and to get a standards. I mean, FITS, I was talking earlier about FITS, the image standard. Okay, it's a terrible standard now, but we all use it still because we all use it, right? And so we should be moving to HDF at some point. That's where I'm saying this ability to gracefully age. We should be moving to some hierarchical data format. We're all scared to because everything of our toolkits are built around FITS. And it was a great standard in 1968, the year after I was born. Not so clear it's great for 2013. But that's the power, despite all those limitations. Because we all use it, it's incredibly powerful. But we haven't been able to age gracefully past it.
George.
So many of the issues and challenges you talked about were in fact motivation behind the whole virtual observatory concept and framework almost 50 years ago. What happened really was that in virtual observatory we built a data grid of astronomy with standards and all that, but not nearly enough in terms of knowledge discovery tools, to which you referred part of these toolkits. And in my mind at least, the whole point of Astroinformatics was precisely that, to engage a broader community, not just data centers, in contributing to this new methodology and tools. I think that's what Astroinformatics really is all about. Virtual observatory we got.
Yeah, we've got most of the core bits, and at a pretty big pain. I think that was it was a hard a slog for you guys, and I do clap for you because I had my doubts, but in the end, we do have something to work with, and we are working with it. I fear of how we're going to get those things to evolve into the future because it's expensive. Not very interesting to your average astronomer, but an essential part of what we do in the future. And you're right, doing those toolkits, well, those are probably going to be done by scientists playing around with data sets. And we're beginning to get them. And so, you know, many of us use, for example, Topcat. The Topcat is, of course, written in Java, and when I look at that and try to say, well, how am I going to change that? I go, forget it. I don't know Java. Java looks like you start writing code and you quadruple the amount of code that it takes to write something compared to what I'm used to. So, you know, that is a tool that is useful, but the problem I see is it's not so easy for all of our students who are working in Python to adapt, to move on further. And that's one of the maybe mistakes we did, is that we didn't quite get everything into this nice little set of toolkits being unified. We didn't have the underlying standard unified.
If I may add one more thing. I mean, let's distinguish between computer scientists and programmers. Computer scientists are not programmers. And in fact, many of us collaborate very well with applied computer scientists and visual language. Programmers, on the other hand, as you pointed out, are expensive.
Yeah.
And this is now a sociological challenge and not a technological one, to learn to appreciate the value of investing in software instruments just as much as we invest money in hardware instruments.
I agree. And your point is well taken.
I feel that it's much more common practice today to share the method of the toolkit. For example, I wrote a paper in SDSS that is fantastic analysis, is very comprehensive, and they share the method as to how to do it step by step. But if I was to reproduce that, it would take months and months of work, if not longer. Do you think that that's something that's going to need to change in the future?
Well, it's gotten much worse than it used to be. So absolutely, I agree. Personally believe that it should become standard practice within our community to share code, no matter how ugly and bad it is. And I have always shared every piece of code that I have done. Sometimes rather scaringly when Max Tegmark calls you up and says, could you please send me your supernova analysis code? Like, okay. And comes back and says, I've modified it the following ways to make it run faster. Thank you, Max. But it seems to give the right answers, which is good. Thank you, Max. But the point is that I just had Max Tegmark for free go through and check our code. I mean, how good's that? That's what happens when you share. The accelerating universe didn't go away, right? So the supernova search software, which was a mess, ended up going to China, and Wei-Don Li there used it to start discovering supernova. He took it to Alex Filippenko, has the most successful supernova search. That's based on a code that I wrote in 1994 and 5. And by sharing it, I lost nothing, right? People have this view, it's proprietary. I've got this thing, and my life depends on it. I personally think it's completely false economy. And I think that the biologists have done this in spades, and it's going to kill their field. And there's lots of money involved in that field. In our field, there isn't much money involved, and we do it, we really are dead. So I think it should become standard practice, ethically considered, share your code. And that's how we build on each other's work.
So first of all, wearing my hat as a beleaguered HDF guy, thank you. Maybe now that you mentioned that HDF people will listen. But my question actually, just to go to your final point of the talk. So now half of postdocs, there's a lot of coding.
Yeah.
How do I convince my bosses to hire real programmers?
Well, I hired the programmer. And I hire you because you do a bit of both. That's what I do. Because I don't have money to hire, you and a programmer. And so I'm afraid because astronomers are typically good enough programmers to get away with it and still get the science out, we do that. In biology, they hire astronomers to be the programmers because the biologists just don't program much themselves. Your PhD is not normally a Python hack within biology. And so it's, it is a culture that we have. The only way I see it really working is on the biggest organizations realizing it's most efficient for them to do it this way. And for example, if you go to ESO, they actually have programs. And they have a big program, and they do it because it's efficient.
So is it then a community solution that we can dedicate something people pulling together?
I'd like to think we will, but I think there's going to have to be big leaderships from the big end of town, because little, the small end of town just won't have the resources to do it. And it'll be problematic.
But just to follow up, do you think that we could circumvent this problem not by hiring programmers, but by buying software? So I often see people that have 10 and 20 grand they can spend on a big piece of big new computer. What if that money was spent contracting with an external company to use the software rather than...
Well, I think you could easily hire contractors. The difficulty, from my own experience, is that we tend to work in pretty cutting-edge stuff. And although we're terrible programmers, algorithmically we're very bleeding edge. And trying to hire, Joe's, code unit down the street to do what you want, I think seems hard. And the other problem is they're professional. And so, their standard of codes per, lines of code per day and hours are probably 10 times different. Because we hack out stuff that, quite frankly, we never expect anyone else to use again, and we don't. Where they have a certain set of standards. And so they're just much slower than we're used to. But you do get something for that product. So it requires, again, an engineering mentality of how you do things. And that's going to be supplied by the big end of town, not by the small end.
Andrew.
Maybe comment on this bit of the discussion from the perspective of the AAO, the Australian Astronomical Observatory, since that's where both Heracles and Andy work. It is a challenging issue. I mean, the AAO has a software team, as I'm sure the CSIRO does as well. The CSIRO has its whole IT division, in fact. The AAO software team is pedaling as fast as it can to make our existing suite of instruments function and allow the observers to actually process the data that gets taken with those instruments. Adding new resources to that software team in order to allow the astronomers to say, oh, I've got this fantastic idea, I just need someone to program it properly for me, is a little bit harder to justify. I'm not saying it's unjustified, and I think it's a really interesting avenue to explore. But it's
and it comes down to, we've made a decision, for example, to do a very ambitious Hermes instrument, and we spent every dollar we had on the hardware, and yeah, keep it code, you'll whip out something, no worries.
exactly right.
Right?
So
That's
it's
the way astronomers do things.
Yeah. Since the first Astroinformatics meeting is I think that one part of the problem could be solved just by making teaching better computer science to graduate astronomy.
Yes.
Because if they start writing a better software, we to have these two repositories will be much easier. So I think that we should also make an effort in changing the curriculum for the university, trying to use more modern things, some software engineering.
I agree. I think it's a useful thing. That the young people actually are much better than I was, for example. SVF, what's that? But you find out when suddenly you can't recreate your software tree after something bad happens. Anyway, so I think that's a perfectly reasonable thing.
And so Tony Hay, who's going to speak later, will move early and so will be a bit late for coffee. So Tony Hay is Vice President of Microsoft Research, and the fourth paradigm, particle physics, astronomy, Jim Gray, and open access.
That's right, yes. Okay, well, actually, I was at the Doctor Astronomy meeting, and I was trying to think of something that I could tell the audience that was sort of could keep them entertained and was slightly different, since I'm not an astronomer. So I would like to tell you something about how I think particle physicists and astronomers are leading the way, which actually I think is a nice thing. Thanks very much for setting it up. I also have some views on the last topic that was discussed. Since I was a particle physicist, I migrated slowly to computer science in the mid-80s, and I've written some popular books on science, relativity, and quantum mechanics. What I've been trying to do for the last 10 years is write a popular book about computer science. It's a bit of an oxymoron, I know, but you'll find that computer science is not just programming, computer science, not just software engineering, computer science is a whole lot of machine learning. So please buy my book next year, it'll be out, From Logic Gates to Artificial Intelligence. Okay, no, seriously, I'm happy to discuss it in a more serious way where we go. Right, okay, Jim Gray, particle physics and astronomy. And one of the things I care about, and I was Dean of Science and Engineering at Southampton, was about open access, and I'll explain why. So let's say a little bit about particle physics. There's this man, Paul Ginsparg. Now, I knew Paul when he was a theoretical physicist, when I was, and he had, do you remember typewriters? So we used to type our papers and then send it off to PhysRev and make Xerox copies and send a preprint round to about 100 institutions. And that was the way we communicated. People wrote papers quoting the preprint and so on. And when, in the 90s, FTP and the web, Paul Ginsparg said, I've got a spare server under my desk, now you've got it all in electronic form, send your paper to me and I'll send you the postage. And so that's how Archive grew up. It's the only thing you could look for with XXX that was not obscene. But they changed the name to Archive.
There are some obscene things on there.
Indeed. Okay, so, but this is what most particle physicists and some of the astronomy community and some of the maths community and so on actually use every day. And so, just a few comments. It's now over 20 years old, and it's 7,000 e-prints per month. So preprints went to e-prints, full text version, so it's not just the abstract, it's the full text, it's available free. 200,000 articles downloaded each week, 500,000 people. The interesting things to me, it's a new form of publishing, because you actually publish these e-prints. That's what this is. It's publication after all, because we no longer need the printing press. We have the web. Publishes e-prints prior to publication. So when you get accepted by PhysRev letters, it's like a stamp of approval after the event. So a subset of the things on Archive get approved by PhysRev letters. So it's an interesting new wrinkle, and the Sloan Digital Sky Survey has another, as I'll talk about. Talk to people, they get very worried that you've got a preprint version, you've got a published version which is slightly different, and it's all slightly confusing, but actually it turns out not to be a problem. These people did paper citing the reading behaviors in high-energy physics, you stop worrying about journals and learn to have repositories, so I'll come back to repositories. And of course the paper you can find online immediately in Archive. This is a nice quotation. Archives used by 53 Nobel laureates, 31 Fields medalists, 53 MacArthur fellows. It's kind of published a famous thing solely in Archive. So it's there. So I actually asked Paul Ginsparg before giving a version of this talk how that was accepted by the journals, because it's a real challenge. And so this is what he said. Marty Bloom, when he was editor-in-chief in the 90s of Physical Review, was incredibly supportive. They decided that the membership, it's run by the American Physical Society, and the Physical Society is its members, and the members wanted to use it, so he said, we'll make it work. And that was actually what happened. The Physical Review still exists, PhysRev letters, and Archive exists. So it's an example of an archive which works with the journal. So I asked him actually how, because in Europe we also publish in Physics Letters and Nuclear Physics, which are well-known Elsevier journals, and I asked him how that worked out. And he said, well, in the 90s, nobody had a website, no publishers had a website, they didn't know what websites were. And so by the time they figured out electronic publishing via websites, this was all de facto. And if you wanted to cut yourself off from 53 Nobel Prize winners, so they had to accept that archive exists. So it's an interesting, and PhysRev and physics letters still exist. So the other thing that might worry you is this is sort of community activity. Who funds it? Well, it's now hosted by the Cornell Library, and they actually now can check which researchers at which universities, CSIRO or whatever, download stuff from archive, and they actually ask for an annual contribution from these universities, certainly in the US anyway, by the amount of downloads, and that's what comes to a few $1,000s, much less than a subscription, and that's actually given them a sustainable model. So I think that's a very interesting model. I'll now come across to the role of my university, Southampton, in all of this. So, I don't know, has any of you heard of Stephen Harnett? Stephen Harnett is one of what I call the three prophets of open access. Don't get in an email conversation with him, because he never sleeps, as far as I can see. He writes sort of 2 pages when he writes 2 lines. So Stephen's a wonderful guy. I appointed him. And in 1994, he wrote what he called a subversive proposal. And he called scholarly papers at the time, he called them esoteric writings, and he asked them to make them available on the web so people could actually share and accelerate scholarship. And this has led to what's now known as the green open access or self-archiving, which is actually what archive is. So that was in 1994, and then in order to help people do it, they made software, and so the ePrint software was produced, and the Open Archive Initiative started, and there's an Open Archive Initiative protocol for metadata harvesting was developed. And so you could get software, free software, you could go and start it up. And the guy who wrote this, Rob Tansley, a graduate from Southampton, my department, also went and wrote DSpace for MIT. And so this is the software, you can just go and do various things. You can actually put it up very straightforwardly. Not as straightforwardly as Stephen Harnett claims, but nonetheless it does work. And in 2001, Stephen was Hungarian, and knows people like George Soros and people like that. And so the Hungarian team, of which Alex is a member, actually got together and had the Open Archive Initiative. So that's ancient history. The other prophet of open access is this man, David Lippman. David Lippman, so I should say Jim Gray worked with Paul Ginsberg. He also worked with David Lippman on PubMed Central. So PubMed Central was an archive at the National Library of Medicine in the USA, and there they had a big budget, and Harold Varmus, the president, decided that they should really, if you're funded by government money, and people who do the reviewing is funded by government money, your taxes are mine. It's not reasonable that the public should have to pay a toll in order to see the things that their taxes are paying. So there's sort of moral argument here. And so they put up in PubMed Central, PubMed is the abstract, PubMed Central is the full text of the paper. And it was launched in February 2000, and you had to put up your paper. If you got an NIH grant, you had to put the paper up within 12 months. And this is their open access policy. Makes the research more prominent, integrated, accessible, gives you all the areas, and it sort of echoes some of the things that Brian was saying. So, and they're integrated with large databases, and I'll come back to that. And anyway, the policy has been in existence. The interesting thing was that it was in 2000. It was voluntary, so you didn't have to do it. And the number of people who actually did it was about 20% of the NIH researchers. After George Bush signed it into law in 2007 that you had to do it, the compliance rate went up to 75%. And this year, NIH has said if you haven't done it, we'll delay your next grant. And now the acceptance rate has gone up to something like 90%. So actually you need to have some sticks as well as carrots. Okay, so I would like to say, again, I'll come back to astronomy in a moment. But I would like to say institutional repositories and green open access. I've been talking about self-archiving your papers, green open access. So as Dean Dean of Engineering at Southampton, I was supposed to be monitoring, you know, in the UK and now in Australia, we take all this research assessment very seriously. I was reading an article by Peter Higgs, Nobel Prize winner, who said that he wouldn't get a job nowadays. Because, since his paper in '84, he's published 10 papers, and the head of the department used to ask him how many papers he published this year. He used to reply none. So he clearly wouldn't have been returned as research answer. But anyway, we have to do all this, and I was supposed to monitor the output of 200 faculty, 500 postdocs and grad students, and each year I got a piece of paper from the library. The piece of paper said, which journals would you like to cancel? So you have to choose because library budgets are in trouble. So you could not subscribe to all the journals that my staff and students published in. And certainly that's journals, but what about the proceedings and workshops and all these other things that are difficult to find? So what we insisted that we keep a digital copy of everything in originally it was engineering, but it's now an institutional repository. And the reason for this crisis is well known to librarians. It's not well known to scientists and researchers, but the reason it is typified by this. This is MIT. These are science and engineering journals. This is the cost of living, all right, over a period 1986 to 2004. This is the cost of journals. So it's just a fact of life. It's nothing. And the thing against the journals, they will tell you that we're publishing more and that the cost per paper is less, but the fact of the matter is we cannot afford what they're offering us. Right? So there has to be a new bargain, but there's nothing to make them change. Why should they change? It's a very lucrative thing. So that's MIT. This is just to show you that this is the American Research Library Association. This again is the cost of living. This again is the price of journals. This goes from 2011 from 1990 or something like that. So it's been going on for a long time, and that's why there's a crisis. That's why we have to do something, because otherwise our research money goes into giving the shareholders of these publishing companies. So this is an obligatory slide, by the way. This is my wife. I usually go to library conferences where my talk to librarians is change or die. All right. But to say that a few jokes and stories I've stolen from my wife, who's a librarian. She built the digital repository in Southampton, which is now hosted by the library. Stephen Harmon said, oh, you could do an institutional repository in 20 minutes. Actually, you can't, because historians, musicians, biologists, physicists, astronomers, all have different cultures of publishing. And it takes a long time to be able to get everybody together and to get it so you can actually have an institutional repository. So that's what we have now. And in my department, I was head of department. This was after I was finished being head of department and dean, but they actually had the first mandate. They said it was important. If you want your research to count, you have to have your stuff in our departmental repository, and now it's actually a university mandate. So this was the first open access mandate, which is the first step towards getting people to put stuff in. Enough? First step. So that began in 2003. They also host a registry of open access repositories, which you can track the growth of various software. So ePrints is one, Keyspace is another software, and there's various other types of software. People are going to use all sorts of different software, and it doesn't really matter. It's a worldwide. This is many thousands of repositories, about 3,000 repositories on the net. So institutional repositories are going to be there, and they're going to do green open access. So it's allowed by about 60 or 70% of the publishers allow you to put a version on your institutional repository. It doesn't have to be quite the same as the published version, but most of them allow you to put a post-refereed version on your website. And it doesn't look quite the same as the published version, but it's okay. Some people say you can't do it for a while, so you can put it on. The important thing is to get it in the repository, and you can make the access internal. So that you can do. It's interesting to see what open access is worldwide. The green is green open access, gold is where the author has to pay instead of the library, so that's gold open access, like a discussion about that. Delayed access is the black. So you can see that there's a long way to go in all these fields before we get that. And you can see it makes a difference if you have a repository and you say, please will you put your papers in, or you won't get promoted unless you put your papers in, and it makes a difference. And I think it's important, actually, because there are people now who create league tables. I mean, I always used to collect league tables as head of department and as dean, and you pick the table, times higher letter. You go to Shanghai, they give you 10 points for a Nobel Prize for them, things like that. So you have these crazy things. I used to like the one that in the UK was the highest research ranking of a city with a Premier League football team. Because they immediately ruled out Cambridge and Oxford. And so on. But okay, so the point is people will do this whether you like it or not. And if you want to claim you're a world-class institution and nobody's citing your research, then it's difficult for me to see that you can be that. So actually people go and do this. There's a company, there's an organization called Webometrics. There's some crazy things, but it does actually look at your research and whether anybody's citing it, whether anybody's looking at it. And this is actually going to be an important part of reputation management, in my opinion. Okay, enough. That was my open access flavor. I would like to talk about what I call the big data bandwagon. I don't like the phrase big data. I think it's true that we're in the age of big data in many respects, but industry, I now tend to be in industry, although I'm really in Microsoft research. So there's a whole bunch of papers. This is a particularly stupid one. It says you guys are all irrelevant. You just go to use Google and it's slow digital data. You'll find all the results, which, as you're well aware, is not true. But one of the things that I left particle physics for was that we produced a series of gauge theories came out, and actually essentially the only things worth doing were solving non-perturbative problems. That's why I went into building parallel computers. But also getting your smartest students to do theoretical particle physics, it doesn't give you many options as a job at the end of the day. You know how to do calculations in QCD, but that isn't necessarily very employable. At that time, there weren't many jobs in universities. So what I like about what we're doing now is that this is using a well-known search engine, right? Data scientists. Right. Data scientists is the role of the future, the hottest job you haven't heard of. What is a data scientist? So what is a data scientist? Well, you heard little bits about it from Ryan. So I've just sort of picked out 3 skills. I mean, I should explain that nobody typically will have all of these skills. But there are people who are great at getting the data off the experiment, the sensor networks, the telescope, the satellite, whatever it is. They're the people who get it into a form that the scientists can then use. Then there's the people who do the analysis, who run the tools, who run the programs, who actually go and find the knowledge. And at the end of the day, there's people, having spent a lot of money to get the data, you'd like to be able to read it and find out about it in 20 years. If you're doing environmental science, you can't repeat the measurements of temperature of salinity of the North Sea 20 years ago. And you've got to find changes, you need to be able to do that. And I don't think this community, do any of you use Excel spreadsheets? Well, some of you do. Okay, so particle physics is never did, right? But a lot of the scientists I work use Excel spreadsheets, and what I can guarantee in 10 years' time, the version of the spreadsheet won't exist, the software operating system won't exist, nor will the hardware. So actually, how do you preserve what's in an Excel spreadsheet? So we've been trying to produce tools sort of in between sort of hacker university stuff that I used to do and sort of heavily engineered stuff that Microsoft does, trying to do it in between. And we produce things like open source additions to Excel, so you can annotate your Excel spreadsheet and tell you what's in it. So when you look at it in 3 years' time, you can remember what you did. So there's a tool called Data Up, which I recommend you look at. So data scientists, so even if your students actually have a great time doing a PhD, finding pulsars and accelerating universes and so on, they'll be able to get a job where they're paid 4 times as much as you. Right? So it's a really good thing that they have options. Universities are now giving, like this is just one example, there are about 30 courses on data science. And it does address the sort of issues you're talking about. Alex calls these people pie-shaped scientists. So they have a skill in astronomy, but they also understand in some depth what's needed in computer science. so this is really, I think, what these things are all about. And there's masters and PhDs now in data science. I should say something about big data. All right, so I used to be a particle physicist, so I used to do things like this. DNA was big data. Of course, it's no longer big data, but it was a big international consortium, 10 years to do the human genome. Now, of course, in a year or so, we'll have all our genome sequenced if we want for less than $100. The Large Hadron Collider, petabytes, this was terabytes, this is 10s or so of petabytes a year. Of course, they throw away most of the data because there's so much data, and they only pick out with their triggers interesting events which are likely to show signs of the Higgs, and that's what they've successfully done. So it's an interesting, exciting experiment. And we've heard about the SKA, and these numbers seem to me completely unreal. All right, so who knows whether they're fiction or not? But it's an exciting experiment, and I look forward to finding out when I'm retired. And this is okay, but actually, these big experiments, they have budgets. They have large amounts of dollars, and they do have budgets for software, so they can actually afford to produce software systems. Quite often, the particle physicists certainly they have to with their big accelerator, and they get big equipment. But people in the medium and small, they're the most typical, the big numbers, the long tail of science. And for them, I prefer to characterize data rather than just big data. It can be volume, but when I was doing e-science, working with the biologists, they have to make sense of things such as just sequences of letters, gene sequences, and that gene actually makes a protein. Well, what protein does it make, and so on? What are the pathways? What's the structure, three-dimensional structure of the Bill Gates? A slightly better view than him, but a slightly smaller house. But there's an earthquake fault through the lake, there's a volcano down there, there's a volcano up there. So it does seem, and it's a subduction zone. It's the only part of the Ring of Fire that hasn't gone off in the last 100 years. And last time there was a big earthquake in Australia about 200 years ago. Anyway, so it seems like a good idea that putting optical fiber on the seabed, on the wonderful plate, which is what they're doing. And instead of an oceanographer going with a professor and 2 students on a boat, trip out, trip back, take their USBs to their lab, spend 2 months writing a paper with a professor and 2 students, off they go. Now, instead of being data poor, they're absolutely swamped by data. 24 hours a day, this data streams in off the sensor network. How do you find interesting events happening? How do you find interesting signals of something unusual? So these are the challenges of velocity, if you like. And there's a fourth thing, if you like, which is the veracity. To use a theme word, I really mean the provenance. What have you done with the data before this gets to here? What was actually the manipulations done with it? So, for example, the story I like is of the ozone hole in the Antarctic, which was actually found by British Antarctic people looking up at the ozone, measuring it, and they told NASA, and NASA said, well, that's funny, we have these satellites measuring it in the ozone hole. So they went back and looked at their data, and actually it turned out that they had a thing in their software which says, if it's below this level, it's obviously a malfunction, throw it away. So the data was there all the time, the ozone. So, being able to do that, to go back and look at your data is important. This is Jim Gray. This is a photograph that I took, which has escaped onto the web. Anybody can download it for free. This is my daughter-in-law's knee. But this was Jim Gray, and that's the boat he was lost on, actually. But he was a wonderful guy, and 2 weeks before he was lost at sea, this is slides from his talk, and it's relevant to this thing. He talked about X-info. What he meant by that is biology, you have computational biology doing simulations of molecules, but you also have bioinformatics, the sort of thing I was talking about, computational chemistry, chemoinformatics, and now we have astroinformatics, and I've even been to talks on archaeoinformatics. So I do think that analyzing data is going to be a big part of even the arts and humanities subjects. They're going to generate digital things. Archaeologists is one example. And the problem is that you're going to have to train students to do different things. They have to know how to manage lots of data. Maybe they need to know about a database, know what a schema is, how you organize, how you reorganize it, you need to along, how you share it, how you visualize, how you do all these things. So these are different skills than the traditional skills that have been taught up to now. So this was another slide from Jim, the fourth paradigm. This is book. My role in this book was to bully people. I bullied the authors, which was a scientist and a computer scientist. And what I wanted to do was make them write not a scientific paper that was readable by a few hundred people, but not an old-fashioned thing. It was an essay, so that actually ordinary people who weren't experts could actually find something interesting. But Jim was talking about experimental science, the Greeks and people understanding the earth was round and so on. Galileo, Newton, Maxwell, Schrodinger, where we encode a lot of that data into laws of nature, which you then can explore mathematically, and then you can do it in a particular environment, and then you can go and test that experimentally. And those are the two ways we've done science for the last 100 years or more. So computational science in the 50s, Ken Wilson, who won the Nobel Prize in the 70s in the particle physicists, called it the third paradigm. What he meant was that you have to know different skills. You have to train people to know about numerical methods, algorithms, parallel computers, parallel programming, all these sort of different things that you don't ignore those, but they're different skills. And now, as we've discussed, data scientists need a new set of skills. Your graduate students need to know how to manage lots of data, how to get signals out of data that are needed. I did e-science, and I spent a lot of time in the first few years I was doing e-science, talking to Australian scientists from ANU, from all sorts of places. And what they did was eventually launch their own e-research. They essentially ignored my mistakes, which I made, and did a much better job. So the e-research came. My job is to go and fund collaborative research with universities around the world. I go to some wonderful places, talk to some wonderful scientists. So these are just some examples of computer scientists working with scientists to solve some of the problems. And there's some really interesting stories there. It's downloadable for free. It's a Creative Commons license, so you're encouraged to share it. And you can also get an Amazon version, but it costs you $1. I don't know who gets the $1, but you can probably do it for free on Amazon. Okay, astronomy leads the way. So we heard about. I'm getting there. I'll accelerate. Right. The Cosmic Genome Program. Well, we heard about that, and this was a wonderful thing, and I learned all about it from Alex Saleh, and Jim and Alex, put up one of the first web service since Web 2.0, where the website is more than just a passive thing. It can actually give you data, and the interesting thing is that with 300 million images at 10 to the 9, this is slightly smaller than that, but a large number of images and only, I don't know, 15,000 professional astronomers. You're not going to get through all the data before you publish it, and that handies for all work. We heard that. The other thing that I think has been interesting to me is this other thing that Jim inspired, Worldwide Telescope, where you can look not just at the visible, but the infrared, radio, ultraviolet, and X-ray, and so on, and you can see the sky and all sorts of things. And the reason I want to mention this is that when you have big data, I think you need visualization tools of a different character. And what Curtis Wong, who did this, has what he calls tours. So you can find Alyssa Goodman talking about star formation, and she starts off in a data set in the infrared in some part of the universe, and goes to the ultraviolet, and looks at dying stars and this, that, and the other. So in order to build the understanding, you go on a tour through the data, and you have to allow people to create tours, and you can follow experts, and you can create your own tours. And I think that's going to be an important part. I came to Microsoft in 2005. This was a slide by Bill Gates. New vision for reporting. You can go get the data interactively. You can update the data. You can actually go and get the code that did this. You can change the parameters. You can do this. All these things are possible, right? In different ways of tell me, hey, like this paper, and you also like this. You can also have those sort of things. And in astronomy, you have the ADS, which is a misnomer because it's actually publications, but it links to data, links to objects, and it does these sort of things. It's a really wonderful resource. And you also have Centre de Données Astronomiques, Strasbourg, and you can see lots of databases there. And this is the sort of vision of Alyssa Goodman's group at Harvard, seamless astronomy. So you have the publications here, you have the data here, and you want to link the two of them with a whole variety of tools. And they've been looking at a thing called the Dataverse, which is actually reinforcing the link between the publication and the data that it got. And they've also done some interesting studies of ADS papers. And so this is a thing for the ADS papers with the links to the datasets. 44% of the data linked from 2001 are broken by 2011. We need to do more. Open access to data. This is what NSF, NIH say, that publishing the data is part of your duty. They set up a data sharing policy where now the scientists are all very scared because they have to have a data management plan. They don't know what a data management plan is, so they've been panicking about that. This is causing a great deal of panic from the UK. This is the Engineering and Physical Sciences Research Council. Say organisations will ensure that EPSRC-funded research data is securely preserved for a minimum of 10 years. Universities have been asked to preserve the data. They have no idea how to do it. So, and they're really somewhat concerned how they're going to pay for it. The answer is, of course, the library budget, because you don't need to spend and waste all this money on expensive things. Where will you put data? This is one of the things that it's in Odo. It is a service at CERN, or you can publish it in this is a new journal from Nature called Scientific Data. So this is the vision of Jim Gray, that you go, and it's very similar to Brian's, you go from the literature, you go from the data, you add your data, you do different subsets, you have it combined, you publish a paper, you link to your data sets. And that's the sort of vision, and Jim felt that that would really speed up information velocity and the way we can solve some of the problems in medicine and environment, but also, I guess, in astronomy. And this was his vision. The National Library of Medicine has these papers here, but you can go from these to these data sets, which are carefully curated because it's a very well-funded institution, and you can actually search across these using a tool called Untitled. Okay, 3 minutes left. I'm getting there. This is, I think we've reached the tipping point in open access. Just to show you, this is the White House memorandum telling you had to put your papers and data available to the public. This is in February. This was the global research councils, the Australian Research Council, the NSF, and all the other ones got together and said they need a plan towards open access. Right? This is the G8 science ministers meeting this week, actually in London. And this is, for example, the University of California. They get 8% of all the research funding in the state. They produce 2-3% of all the peer-reviewed articles. They now have to make that available. It's obligatory for anybody at the University of California. And even in Australia, the open access movement is here. Australian Research Council now is going to be insisting within 12 months you have to pay that. Okay, so to finish, Fulkin's Park. Joke, there's a paper by Vannevar Bush called As We May Think. This was Paul's joke, As We May Read, because you never knew whether you could read it or not, because you could never know whether you could get a copy of it. His conclusions at the end of the day was that the technology will allow professional societies, institutional libraries to return to their dominant role in support of the research enterprise, as opposed to commercial publishers which charge and make a profit on these journals. Who knows? Future. Then I really will finish. But I would like to say a little bit about this. Big data, machine learning, visualization, and cloud services will be in your future. This is, how many of you have iPhones? That's very sad. This is a Windows phone. But when you speak into your phone, like Siri, or in my case, not Siri, it goes up. There isn't enough processing power to do speech recognition in this little device that we carry around. So what does it do? It sends the stuff into the cloud, it does the calculation, sends you the answer back in less than a second. And that's the key thing. So devices like these, doesn't have to be a phone, but small devices which don't have processing power, because they can access the cloud, provided they have bandwidth, are enormously important. So you can imagine the archaeology field work, you can have your whole data up in the cloud, you can do comparisons on the spot. I'm not quite sure how it compares to astronomy, but there we go. But one example that we did do was there were these terrible fires in the Blue Mountains not long ago. This was one in 2007 in Greece, and what we built with our Greek employees and Greek researchers with the researchers in the patents was an early warning system. So you could have the real-time weather data, you could have the forecast data, you could have all the topology of the island, the things. You put all this in, and each day the fire chief has a roadmap telling him the probabilities. And if a fire starts here, the wind's here, where will it go? Where does he send his firefights and so on? So the answer is that big data and machine learning and the cloud allow you to make informed, intelligent decisions. In that case, I don't know quite the example in Astro, and I hope to learn here. That's why I'm here, to learn what you're doing about getting data out. I call it machine learning here. And just because I see in my file I have free access to Amazon Web Services, so I should point out we have a Windows Azure cloud, which now supports Linux, Java, and Python. Right? So you can do all those things. Anyway, so I think it is now ready for people actually to play, and these things, just like you have your Amazon ones, this is an alternative, and you can put a proposal in a couple of pages, and we try and fund as many as we can in a very rapid turnaround. So just funded the first 30, and you can get several hundred thousand hours. So who knows? I think the cloud, machine learning, visualization, and big data will be in your future. Thank you for listening.
Tony? Questions? Tony?
If you have a question, could you please stand up closer to the microphone and talk up? We just had someone feedback from YouTube to raise the...
Maybe if it's a very quiet speaker, either Tony or I can repeat the question. Okay, any questions? Julie?
You talk a lot about open access in
Something I care about, I'm sorry.
Yeah, so that's good. Now, a lot of these journals that we have to publish in do cost money, and there are impact factors that sort of, I
Another
guess,
topic I'm interested in. Yes, carry on.
like make or break, I guess, their careers or whatever. But how do we get the impact factors for open access journals, and that should be really
Well, you notice I'm not advocating you change which journal you publish in. So you can publish whichever journal you like. And that's what the Green Open Access says. Publish wherever you like. Just put a copy in your institutional repository. So I'm not advocating that I should restrict which journals, and there are some vanity publishing open access journals which publish anything if you give them money. So I'm not advocating that. There are some high quality ones like Public Library of Science, and that's at one. And they've been looking at not impact factor of journals, which is pretty stupid, but they've been looking at impact factor of individual articles. And so that can be number of citations, but it can also be blogs, it can also be Twitters, all sorts of other impacts. So people are looking at these different metrics, which is a very interesting thing to do, and what's the most useful metric. So, no, the answer is you publish whichever journal you like, but you put a copy on your institutional repository. That's what you have to do. Whether it's visible outside, all of these will be visible within 12 months. They make all their money within 12 months. So that, and most of 12 months do that. Publish whatever you like.
Can I add something to that? So I work in some funny areas, and I publish in obscure journals that nobody reads. But of course the papers also all go on AstroPH. And so if you go into ADS, you find all these citations to the AstroPH paper. Nobody actually looks at the journal. So ARC at the moment, they ask for impact factors of journals.
They do it, right? It's stupid.
No, they don't anymore.
Oh, they stopped. Oh, right. Okay.
But it's an interesting, how do you measure the impact of research?
The world is changing. Yeah.
Also, just a comment. I would like to ask how many people in the audience have been reading a paper outside of X archive in the last 2 years?
Outside of archive.
Yeah.
Well, the astronomy community, I told you they're leading the way with the Department.
I think very few people.
Well, I routinely use the journals, but they're linked in. They're almost everything's we're going to archive first.
There are conference proceedings which are not conference.
The conference proceedings are a problem. That's why I feel it's important to have those.
But the interesting thing is that every single one of us almost certainly uses ADS, like me, to actually define what you're going to do whether you choose whatever source is available.
Yeah, but for the computer science part of that, that's a tricky job because ADS doesn't link everything there. So So you have to be aware that you put your papers in ADF if you publish something on the computer science side. So
You
that
can also put it
That's
in
where
archive.
Google Scholar is actually.
But you can put it on archive as well. And it shows up on ADF.
Yes.
Yes, of course, but you have to do it manually. It's not.
This step.
But then you can get in somehow trouble with the conference you attend, because computer science is a little bit different in how you publish. It's not just writing to a
It's a very
journal.
strange field. I found it very strange.
It is. And
George, and a question. Oh, right.
But just to say computer science, there are things like DBLP, which is where they have conferences. But you mentioned Google Scholar, somebody did. So we have a research project called Academic Search, and it's mainly computer science, and it does lots of interesting things. You can find out which are the fields, the trends, and which are the most hot topics of the last 10 years and how they've come and gone. The question is, you know, I'm not sure I'll be allowed to, but it might be interesting to see if we could make it into something that was really different and useful for people. And the only way to do that is to involve the community. So if you have ideas, then I would be keen to see if we could assist, because I want to work in a very, quote, non-Microsoft way. I do open source projects. I want to work with the community. I want to make code available and share and things like that. So what can we do?
Fine.
So do you see the opportunity for companies like Microsoft, not just Microsoft, companies like them, contributing to what I call this middleware stuff that allows people to build up toolboxes to reuse data sets? And presumably, you could do it in a way that wouldn't just be astronomers, it would be across all fields. Where right now, we don't largely think anything about what everyone else is doing, we just worry about our own stuff.
Okay, so I work for a commercial software company. People know the difference between a GPL license and a BSD license. A GPL license was designed to stop software companies existing, basically. And BSD means an open source license you can share, and that's business friendly. So if you're graduate students and you do a huge amount of work, you can go and sell it like MATLAB. So I've been doing open source. I'm not allowed to open source our basic products, but I can open source around that. Microsoft's not going to go into the business of scientific tools, but I didn't fund IPython, by the way. So I funded the guy who did IPython. So yeah, we can do a lot of things that are open, but don't expect me to open source Windows or Office. I can't do that.
Yeah, I was just wondering if there's some funding model in which, you guys have the capacity to do it, you can deliver it across, lots of areas, so you might actually be able to make some money off it.
Well, yeah, okay, so Microsoft, like Intel, has what I call the $1 billion problem. So if it's a business that can only rise to 100 million pounds, and it's perfectly good business, but it's not market. That's why, the sort of things we're doing, I can do things with the community because we're not going to go into business. I'm not treading on anybody's toes in the business groups. I should explain, I work for Microsoft Research, which is 1% of Microsoft. And we publish our papers, they're on conferences, they're on program committees, we do all the usual things that academics do. So we can do many things, and I would like, I agree with your vision of interoperable tool sets, and I'd like to make tools. If it's a Microsoft tool, that's great, but if it isn't, you need to be interoperable, and so you can mix and match and use whatever works for you. So yeah, I fund a few small projects around the world, and I'm open to suggestions. And if we can find ones that are generic, that would be great. But each field is different.
George?
On that theme, one of the many wise things Jim Gray said was that scientific computing is a $0 billion per year market. So it's a mixed blessing, because we cannot ride the scalability of massively produced stuff.
But I think we can do some better than we've done before, and I agree with much of what Simon said about the software engineering. Although doing e-science, I did find that the virtual astronomy group in the UK seemed to be taken over by these people who were software engineers who were dictating to the scientists. Now, I think you need a much more even-handed partnership. So I think they produce things that the scientists didn't want, and I think we need to do something in between. So, yes.
So just to pick up on that a little bit further, is what you're saying meaning that we could come to Microsoft Research with a proposal to develop a large project, which would be astronomy middleware, Brian's problem, and ask if that kind of thing
first of all,
that would
we don't
serve
take
the entire community.
We don't take proposals, right? So what you do is you send me an email with some ideas. You don't write a detailed proposal wasting a lot of time. And we see what we can afford and what we can do. So, but Dan Fay knows these preliminary bid. Curtis Ron would be working with Alex, we'd be working with Alyssa Goodman and a bunch of other astronomers. So we have done something, but I can't do all my work with the astronomy community. But on the other hand, if there are some tools which are generically useful, that's fine. So I'm like Brian, enthusiastic about Python at the moment. I think Python is the new basic. No, I'm sorry about that.
Any more questions or comments?
But, yeah, we took basic, you see, you made it Visual Basic, which has all this object-oriented stuff that's in Java, which makes it so much, expansion. So we really need to get something which is more disciplined than basic, but which is much simpler. And that's why I like something like Python as a possibility. It's used by people like me. It is unsafe in some ways, and it will evolve, I'm sure. Okay,
thank you very much.
Great.
There's tea and coffee and biscuits out there, and guys will be back here at 10 past 11.
Yeah, well, that's what I did initially. I ended up so
Bring it up there.
So I think, yeah, shall be cool. But that's okay. Once I work it out.
I've just changed it very slightly, but
then you hit it again. Because there's no heads at the moment.
okay. Yes?
No, it is. Yeah, I think it's fine.
Okay. It's locked off now.
There's just no avoidance of it, so it's hard to determine
Well, we're actually experimenting. We actually light up the speaker a bit more, so at least maybe dark. Some people saying it's too cold, some people saying it's too warm. So I keep it on.
Until the ring comes back in.
Yeah. It's cool again now.
Leave it until the ring comes back in.
I'll just slightly back up.
session you want to do?
I think
You said arrive in situ.
maybe just have a longer lunch hour. You can start 20 minutes earlier. Yeah. The lunch won't be ready until 20:30, but we can start. We can finish lunch 20 minutes early. Well, no, I don't really want to take that time.
CSIRO problem won't allow you to have any other project whatever. What is the general?
Can you stop interacting for a minute, please? So a couple of quick announcements before the next talk. Firstly, we have a pile of pads which ICRA from WA have kindly donated. I think they're in some of the bags, but not others. So there's a pile of pads just the other side of that wall there. That's one thing. So help yourself. The other thing is that, as well as this room here for coffee, there's another room which is called the interaction space. And so feel free to go in there and interact. And in particular, the posters are in that room. So feel free over coffee and tea to go in there and have a look. We're not having a poster session as such, but we do ask if people with posters, if you can stand by your posters during some of morning and afternoon tea. The other thing is that there's also a courtyard out there, which you're very very welcome to use. Just go through the doors. You want to stand outside instead. Right, what else? The talks are going on the web as far as possible. So Malta's busy doing that. So if you run your talk off your own laptop, you make sure you give Malta a PDF so you can put it on the web. And for those of you who didn't miss it earlier, we are doing live streaming of this and that's on YouTube. And the other thing is that I'd encourage everybody to tweet questions and comments, and the hashtag is Astroinfo2010. Astro13? Sorry?
Astroinfo.
Just Astroinfo?
That's Astroinfo.
Okay, so it's Astroinfo. Finally, somebody asked about a trip up to Parks. We can't organise it for you, but we'll certainly help with the organisation. Essentially, the only realistic way is to hire a car. So if you want to go up to Parks, maybe a group of people might like to get together, rent a car and go up there at the weekend or something. I've actually written on the whiteboard at the end of the interaction space, sign up here for Parks. And if a group of you do want to do it, then we'll talk to Parks staff and see if we can get somebody to take you around the telescope, not just go. So the visitor centre's there, anybody can go up there and go around the visitor centre. If you want to go in the telescope itself, we'll have to see if a member of staff is able to help you with that.
They should be warned that the Elvis question is not happening.
Was it expected to? Right. Yeah, Parks is famous amongst Australians for the Elvis Festival. Let's not go there. Right. Let's see, I did say, Darren Coton, unfortunately his flight's been delayed. What we're going to do is we're going to finish this session 20 minutes early, go into lunch at 10 minutes past 12, and then we'll start the afternoon session 20 minutes early and have Darren on before Yeshi Fenner's session. Okay, and now I have my great pleasure to welcome Thijs van der Hulst from, and I'm not going to pronounce it wrongly, University of Groningen. Very good. Close. Who's going to tell us about targets.
Thank you, Ray, and thank you for allowing me to give 2 talks at this conference. The other will be on Friday, basically on my own research. But this is, I thought, an appropriate topic to relay at this conference, which has to do with spin-off from astronomy. And the project that has the name Target, and I'll give you a bit of the background and the spin-off in the about 20 minutes that I have. And most of the material was given to me by the 2 people who were leading the Target project, Edwin Valentine and Gijs Klein. It all started with an effort called Omega Sen, and Omega Sen is basically the center built to provide a pipeline and a database of the data coming off this telescope, the VLT survey telescope. That's how it all started. Actually, now it has also other sets of data. But these 2 little telescopes, a 4 meter and a 2.6 meter, next to the 8 meter, 4-8 meter the telescopes of the VLT, are the ones that produce a lot of data these days, and I'll get back to this. So in the whole context of big data and databases, they for ESO play a key role. And the data consists of large ESO public surveys, which are in the north and in the south, of the Milky Way, I should say. The KIDS and the Atlas and the Vista surveys. They will produce a lot of data. This is the first basically clean, a nice picture of the VST Omega Cam system. The system itself is shown here. This is a mosaic of CCDs, which gives a 1 square degree field of view. So basically, you can take a picture of the full moon, and that fills the entire field. But this is a picture around the Hercules cluster. The center of the cluster is blown up here from this area. So that is basically preparing, and the Dutch astronomical community was involved in preparing for Omega Sen, the camera, and provided resources for the CCD chips, but also for developing the software for the calibration pipeline. And a lot of the ideas during that development is what I will focus on, because they turned out to be essential for actually building a system which can also be used by, for other purposes than just Omega Cam or in general wide field data. Now the public surveys at the VST, one of them is the kids survey. The first data release has happened recently. There's a long history, and I will not go into the details of actually building this telescope and setting up this pipeline. And in fact, the telescope was delayed by many, many years. Maybe it was a decade, I think. 4 years. It allowed the people working on the software to actually do more than they usually do for getting ready for first light. And actually that extra time, I think, to be honest about it, has led to some of these developments, because they had the time to think carefully about what they were doing. Now coming back to the data rate, I mentioned these two telescopes on Paranal. Each color is one of the instruments on the VLT, except for the red and the blue, and they are the infrared camera on Vista and Omega Cam on the VST. And you can see that Omega Cam fills about a quarter of the current data rate from Paranal. All the VLT instruments are this tiny bit here, and the VerCam on Vista takes care of most of the other 3/4. So a large fraction of the data rate is from these survey instruments, leading to a data rate of a petabyte a year. So these have been operational now for, I think, about a year or thereabouts. So the archives being filled with data are constantly increasing. Now, in order to not just get ready for Omega Cam, but in general build in Europe a system that would allow access, much in the way that Ryan mentioned this morning, to the entire astronomical community, to large data sets from these survey telescopes. The system, AstroWise, was built up. These are all the different nodes throughout Europe, and there are links with the virtual observatory. And I don't want to sort of go into all the details of this. They basically detail the characteristics of the database. I'll come back to some of these, the data lineage, the access. This is just to impress people with numbers, but I think what is more important is actually what's in the system, what it can do, and the scalability. And of course, Python, if you go and look at the inside of the system, plays an important role in the developments. But here's the basic idea. And actually, these could be iPhones. The user is in this corner, and the rest of the system is not where the user is. It's distributed around the world, or around the province, or around the country. And that's to what the user has access. But of course, people outside astronomy now talk about the cloud. And the cloud has your data, but it also ideally can compute things for you if you need something out of the cloud that has not yet been properly produced by one or another pipeline. And the same idea is built in here. And the VLT survey telescope, now by Valentin and colleagues, is basically, the name is used for the database and the structure they have set up as the virtual survey telescope. But the idea is that the user browses through the archive, wants a certain product or a certain piece of data, or maybe lots of pieces of data from different pieces of sky, and he basically extracts it out of the database. But he can also add certain qualifiers, like pieces of sky, quality of the data, and depending on whether the data reduction has already provided that, or whether that still needs to be done, the system itself will figure out whether it's in the database or whether it will have to be produced from the raw data. And that is not really something the users have to worry about in this system. it's taken care of actually by the database itself. So there is intelligence in the database that uses computing power, that uses, this is the archive that has basically the pixel and the metadata, and the database resides in a database server, and this all is interconnected, completely transparent for the user. So that is the paradigm that has been built into this Astroinformatics database, that the user, whether he has a desktop or a smartphone or a tablet, wherever he is in the world, he has access to all these facilities. And he can do local computing, but if the task becomes too big, the computer better be done somewhere else. So that is the basic idea. I think the important thing I'd like to point out is that it's really about data about data. So it's not just the pixels that come off the telescope from whatever complex instrument you have. It's also what is done with the pixels to produce an astronomically usable product. And that needs to be described properly as well in the database, because the user, in the end, maybe not all users, but wants to basically trace back, or be able to trace back what was done to the data to get to the product. And some, in radio astronomy, there are the so-called black belt radio astronomers who know really all the aspects of getting from, now this is a technical term, raw visibilities that the telescopes, the interferometers give you, to basically a nice interpretable and measurable image of, say, the distribution of singleton radio emission in a radio galaxy, or neutral hydrogen emission in a galaxy. And all these steps in between are difficult and done by these black belt astronomers. And they always want to do it their own way. Now, of course, it's possible to produce a standard radio galaxy image using a standard pipeline. And for many purposes, that is a perfect product to use, and many people will be able to do science at that. But the black belt astronomer wants to do a bit more. And you don't want to exclude that possibility with basically this type of data. And to make that possible, it's important to also have a description in the data, with the data, about how the product has been produced. So all the pixel data sits on data servers. That was the lower left corner in the diagram. The metadata sits in the database, which was the lower right corner, and basically describes what was done to the pixel data to produce the products that are also in the database, and how the different pixel data were combined. Now these compute clusters, which in the previous diagram I had up at the top left, could be anywhere, but some will be close to where the data are. And all the operations that are done to the data produce a product that is put back into the database. So a description of the processing also has to go back with the database, so that you can trace back the history of what you did to the raw data. It needs to be scalable. That came already, was already mentioned this morning. And it's a distributed system, and for Astro-wise, it's distributed throughout the EU, but there's no, or European countries, it's not necessarily, well, they happen to be part of the EU, but that's not necessarily the boundary. It could be distributed worldwide. Another thing which is important is not only the processing that took place to the data, but there are aspects of the data that change with time. There are physical changes, of course corrections. Yeah, for atmospheric research, for atmospheric distortions are made. Maybe better corrections become available later, so you want to reprocess the data. You have to keep track of all of that. The modeling, if modeling takes part of the data analysis, may change as well. And of course, objects themselves change in time. The code may change, and all this, these changes need to be tracked and added to. This information needs to be added to the database. So in this whole diagram, which I don't expect you to read, but it basically is, say, in the case of Omega Cam, data frames, twilight frames, flat fields, bias frames, and so on, that all are combined with the science data to produce a calibrated science frame, which is down here. And then at the bottom end are access for the users to the science frames, but also to source lists, to galaxy fits, to light curves for time sequences, and so on and so forth. So that's basically the standard processing line. But from here, the user querying the archive can also go back and basically extract, because all that information is stored in the database, only those, say, light curves which were done for certain objects with a certain quality under certain atmospheric conditions, because all that data is stored in the database. So in principle, there is a large variety of parameters that can be used in the query. And if a user queries, for example, galaxy light profiles for objects for which has not been done, the system will do it, provide them, and put the result in the database. So that's in principle the idea how this would work. So in that sense, it's a database which is expanding all the time. Now this is just an example of different objects with the raw frames to the science frames, and these are all the calibration, bias, flat field, etc. frames that have been used. And information about which one was used for which one is all stored in the database. Now the volume of the data from these surveys, here we have kids with the VST, SDSS, complementary UKIDS. This is in wavelength, and this is basically the area of per night, but hundreds of petabytes each night. So that has to be dealt with and be stored in such a way that it's accessible. And the Astroinformatics group has built a database which in principle is scalable and has all these elements in there that have this extreme data lineage so that for every product you get out, you can completely trace back to the original pixel data what was done to it. Now this database turned out to be very profitable for other areas of research. And that led to an enterprise which got the name Target. And I have a few folders for people who are really interested, which I'll put on the table at lunchtime. And this is just sort of the logo thing. And here is Omega Chem, University of Groningen, different research group, the medical hospital, but also companies, Oracle, IBM. This is a small country in the north part of the Netherlands. The province of Groningen, the province of Drenthe are interested in actually supporting this because they see productivity for small businesses. And so this is partly a scientific, partly trying to get connections to business enterprise. First are two astronomical applications. This basically database structure is now also imported into the LOFAR long-term archive, which is actually, as we speak, being filled because LOFAR is now operational. This is the central part of LOFAR. It will be used for MUSE, which is a 24-hour view system for the VLT, which is nearing completion. This is a picture of it, but it will also produce large amounts of data, and it also will be ingested in the same database structure built up by Astroinformatics. Other disciplines that have profited from this, one is artificial intelligence, a project that started just with basically digitizing old manuscripts, but now they have not only software to digitize it, but rather actually do character recognition, and actually they're breaking up the text in pieces and storing the pieces in the database with the idea that eventually, since you know the words, you can use that to actually do research in these texts and find, basically do things like pattern recognition. So that is, they're now in a project to basically digitize the national archives and put it into a database with the additional pattern recognition software and also handwriting recognizing software. Lifelines is a project of the medical hospital where they monitor 165,000 people for about 30 years. They basically get data for each person once every 5 years. And it's a lot of data. It's not just measuring your blood pressure, but also interviews about people's lifestyle. They measure lots of molecular and DNA type information. And basically the idea of this project is to use this data to see how people lead their lives, to monitor their health. This is not sick people, but mostly healthy people. And to actually get an idea of how to improve people's basically quality of life by studying this. Another project is a project that is related to research in Parkinson's disease. It consists of a lot of PET scan data which are manually being classified, but then the information is stored in basically in a similar database. And the idea is that this data can then be accessed and analyzed much the way these sort of analyzers are used to analyze this nullable data. And a final very Dutch project is called Eikdijk, which is Dutch for calibration dike. In north of the country, people have built a dike and do all kinds of things to it. And basically, of course, since more than half of the country is below sea level, it's important that the dikes keep their integrity, especially in the future. So there still is a lot to learn about how to build reliable dikes. There's lots of monitoring data from all kinds of aspects of this calibration dike. And this is rather small and the city, and actually it went up just recently. And it's now completed, should be finished early next year. So in summary, although the data and data structure and database and the ideas were developed for astronomy, the concept of basically not just data, but especially this information about what was done with the data to get the products is universal. It can be applied to many other disciplines, and this target project is actually showing that indeed that is successful. And also, which I haven't mentioned, but talking to the people who have been involved, the experience is not so much that you provide information to other disciplines, but you get a lot of back for that. And it turns out that new ideas basically are generated, especially in discussions and in small projects with people from completely different disciplines, and also the interactions with small companies in the region have been an added value. And an additional added value is, of course, the outreach, but that was not the purpose for doing this, but it comes along. So let me finish here.
Nice. Time for 1 or 2 quick questions. Let me ask you a question. What is it about your database that, all the other applications, presumably they're commercial companies who would like to get into those markets and build their databases for those people. So how come your database, why do they choose your database rather than a commercial product?
I think it's not so much the database itself as well as the layer around it that is built with which the user interacts with the database. The database, well, the database underlying this one is an Oracle database.
Yeah, no, the whole system. So
I
were
think
commercial companies not doing this at all, or what?
Not that I'm aware of. It's much like the interfaces that have been built for SDSS. I mean, basically knowing what the user, how he's going to interact with the data, and of course, with underlying this idea that was in this diagram, where a user could request all kinds of things, and you have to make sure that that is possible. I think constructing that is the important part.
What is the size of the metadata you have? If you store everything, like in comparison to the
What it is right now, I have no idea. But the important thing is that it is scalable. Right now, if I give a number, it would be no. I would have to look it up.
I can say something. There are something like 300 flags for each pixel.
No, I mean like more like this add-on data, like could you be able to recreate everything from
Yeah,
the
so the metadata is what is that?
Oh, all right.
You have an idea?
Yeah. Well, what I know is that you can construct the whole story of the pixel through something like 300 flags.
Is it 300 flags per pixel? So the metadata is probably larger than the data.
Yeah, but probably not a factor of 300. Because yeah.
So does this allow a user potentially to generate a new workflow based on the calibration and to produce a new image then?
Yeah,
Would be the idea.
yeah, in principle. Suppose that I'm going to the data and I don't want what is it, a quarter light radius of my galaxies, but something else.
Yeah.
I could request that. But of course that requires that the particular software to do that is there. Otherwise you would have to get the data, do it yourself, and then put it back into the system. But the idea is that maybe not right now, but ideally that should be part of the system.
And the big issue that I've looked at doing this is I/O. It's one thing to operate on a database, but you have petabytes of data. You get slammed with users all over the place. Managing the I/O into your computers seems to be tricky.
Yeah, that is something that I think they don't have much experience with yet. The idea is that, in principle, the capability is there, with a processing cluster close to the data. But I guess the experience with Omega Sen data is just fairly recent, and with other surveys, there's also, just the last few years, and not many people have done these kind of requests, so it hasn't been overloaded.
Last comment from Jessica.
I really wanted to ask a related question to Brian. So you said when it's a reasonable data volume and so on, people can work locally. But what are they doing in practice and in actuality when they're trying to work with large data volumes? Are they applying for national data storage and HPC, or how are people actually doing that?
Oh, you mean the cost for paying for the storage, etc.
Well, if they need, say, as an example, a couple of 100 terabytes to do some big project, how are they actually go about that if they can't do that locally because it's just too much to bring back and work on their own machines and things?
The storage that they use, and similar for example for LOFAR, is all from different kinds of national funding. And so in essence, it's sort of in a couple of places, like in the Netherlands, there's a big storage capability at the University of Nijmegen and at the University of Poland. And actually, Amsterdam. Physically, actually, it's not in Amsterdam, it's somewhere sort of 50 kilometers outside Amsterdam. And there is a large storage in Jülich, which is in Germany, which is basically a large physics concentration, but most of that is funded by national funding.
Okay, thank you very much. So we now have Vanessa Moss. Oh, there you are. And who's going to tell us about Archiver, which actually is nicely segued in from Tony's talk earlier.
Yeah, I just announced on another screen. Okay, hi everyone. My name is Vanessa and Aidan is there, and we're going to be talking to you about Archiver, which is a tool that we've developed. It kind of fits in nicely with, I guess, what Brian said earlier about how we build on previous work. And that has a lot to do with how we keep up with the literature as it expands. And also with what Tony was saying about archives, so how much influence it's had on astronomy and how big it is in the field of astronomy now. And also, one thing that hasn't, I guess, a little bit been touched on, but visualization is a really important and efficient and effective way of communicating information. So that's where Archiver kind of fits in, and we'll be giving you some information about that. So to talk about the literature, so the previous work. So science is built on previous work. This is common to all sciences, and astrophysics particularly. We need to know what other people are doing and keep up with that so that we can make new advances. It's currently a quantifiable output of an astrophysicist, so what literature you produce is measured to you as an astrophysicist. And also placing your work in context, so being able to see how what you're doing relates to other people in the field, as well as just knowing where the field is going in general is really important in astronomy. So to give you an idea of how the literature has changed, this plot was made by Rob Simpson, and it shows, so these are like some of the major astronomical journals, and how the number of papers per year has changed over time. So you can see it's gone huge from the 60s, and it's just continuing to climb with some fluctuations depending on different eras. But what we're really seeing is just that there's a huge number of papers. There's a lot of data coming in. It's basically impossible to keep up with all the different things in all the different journals if you try to manage it that way. And so what we're seeing is this exponentially increasing rate. It's a lot easier to publish now than previously, so there's a lot of systems in place. Moving online has made it a lot more efficient. We're seeing there's a lot more large collaborations and that, I mean, in some ways you might not think, if each individual person is producing papers, you might not produce more papers, but large collaborations work on lots of projects, and so I think the overall output would be more. And job security is correlated with publication rate, which is not necessarily the best thing, but that's what we've got at the moment. And also the digitalization of the literature, so that's both in publishing it, but also in accessing it. So this has all changed how we access the literature. So this is showing Archive since its conception and how it's grown over time. So you can see in 2008 it split off from just being astronomy into the fields that we know now. And that trend is continuing to climb, so I guess they're at something like over 12,000 papers in just astronomy per year. That's a lot of papers. So trying to keep up with that is a big challenge to try and figure out. And I think probably what happens is that you end up focusing more on your field or more on papers that are directly relevant to you. So this is showing just the number of submissions to Archive over the time that Archive has been running. So this is the papers that we've had access to. So you can see the weekends, they're not published. There's a big peak on Tuesdays, and that's because Tuesday is the day that the weekend papers appear. So anything Fridays, like late Friday, Saturday, Sunday comes up on Tuesday. You can see that also, one thing that Aidan pointed out is that there's a missing day here, and we figured out that that was Thanksgiving. So papers didn't appear there, so that boosted Monday's papers, because Friday got lucky there. So you can kind of start to see like interesting trends. I wondered if maybe October was higher just because a lot of people were trying to get their papers online before proposal deadlines or job proposal deadlines and stuff. But anyway, so that's kind of interesting. But basically what we're seeing is at least 50 papers a day, working days, and a lot more than that sometimes. Where does Archive affect this? So we found that just trying to keep up with the papers, like 50 to 70 papers on AstroPH can be difficult. You see them, it's not badly formatted, but it's just when you start to read it all, it kind of blows together. So it's difficult to digest in an efficient way. So what we've done is we present the metadata of each paper reformatted, and I think the key thing that makes it different is that we include figures. So the visual aspect, kind of getting information from a figure, is really important here, and that I think is what makes Archiver quite effective. So this is what Archiver looks like. This is the homepage. That's the address if you want to check it out. So what we've got the title. This is taken from Archive. We've also appended the main category of the paper in the square brackets at the end. We've got the link to Archive, the paper on Archive very prominently because people want to be able to access that quickly. We've got 3 representative figures, and Aidan's going to talk more about that. The abstract, the date, and also the number of papers. So this is how, I guess if someone is logging on Monday and they want to see Monday's papers, they'd know that they were up to 1 out of 48 or 45 out of 48. But one key thing we've done is we've randomized it, because we hate it, and most people hate it, that people play this 4 p.m. submission game, and they're like coding. And I submitted a paper 5 minutes after 4 p.m. because I was in the US, and it's 4 p.m. And I was like 50th out of 70. So we didn't like that system, so we've randomized all papers to make it more people. We've also got, so that the category...
Vanessa, some people may not know what the 4 p.m. business is. Do you want to explain what
okay,
that is?
so it's to do with the ranking of your papers on AstroPH is determined by when you submit after they open submissions. So 4 p.m. is when it starts, and so everyone just kind of sits at 4 p.m. I swear people have scripts to do this because like it's okay. So it's like, you know, and then the actual ranking at first will be, I think GMT it's 8 p.m. So it'll be 8 p.m. and then it'll be 1 second past 8 p.m. So it's a pretty.
You get more citations.
Yes. That's the idea. I think people have done studies, and you know, yeah, you're more likely, I guess, to be at least looked at or read. But overall, I think the effect is not super huge. I think it's just.
I think it is huge. It's,
is it?
You get twice as many citations if
Twice?
you're in
Okay.
the first second.
Well,
It turns out you're better off being at the bottom than.
Oh, right, than in the
Yeah.
middle. Right.
So anyway, that whole we don't even know why Archive doesn't randomize it, but they don't. So we did. So we've got the categories, the cross-listed things, and then the categories appear on the side. So if you're only interested in galaxy astrophysics, you can click that and just focus on that. We've also got cross-listed papers, so anything that's say computer science, but also tagged with astronomy will appear. And if you're really keen on say pulsars, you can search pulsars and that'll come up. You can search days, anything searchable that's in the text table will appear. So this is just showing a few examples of how it changes how papers appear. So this is what it would appear on Archive, and this is on Archiver. So you can see the key thing is the figures, and they really, I think, communicate what the paper's about quite quickly. So another example, and another example. So this is instrumentation, so you can see how that algorithm works. But yeah, so that's how Archiver changes the way that you view literature. To give you an idea of the flow, so we scrape, at the moment we don't use the Archive RSS feed because that's delayed compared to the website, so we scrape the information from the actual Archive site. We download each paper's files, so that means we have access to LaTeX, figures, pretty much everything, and so there's a lot of potential in the future to go further with this and do more. We find all the associated images, so because we have access to the figures, we Fourier transform them all, and that becomes part of how we determine which figures we should display on Archiver, and Aidan's going to talk more about that in a sec. And then we pick 3 figures, and so this is where, I guess, what the Fourier transform tells us about the content of the images comes into play. So we can pick the 3 best figures, and then we post that to WordPress using the Python package. Alright, so Aidan's going to talk about that.
Right, so as Vanessa was saying, one of the things we found out early on was that the images are a great way to summarize the information in the paper. And it's a very good way of quickly getting an idea of whether or not you might be interested in that particular document. So we put a little bit of thought into exactly how we could go about choosing which of the images to display as being representative of that particular paper. So how do we automate a process which is essentially very subjective? You've got different people with different opinions who all want to get a sense of what this paper means for them. So we thought about applying some sort of machine learning algorithm to the process with a training data set. This is the kind of thing the military would do for the satellite photos. If you want to spot a tank somewhere, then you train the machine with 1,000 photos of tanks taken from different angles, and it starts to learn what a tank looks like. But we don't really have a specific target that we're interested in here. So that kind of process would probably be needlessly complicated, and you would have to deal with very high variances in the opinions of people involved. So instead, we just went for a very objective method. So harking back to the Claude Shannon 1940s information theory type approach, where all we're really interested in is the amount and the content of the information in terms of its very basic characteristics, rather than what it might mean in the scientific context, which you can't really judge without having a brain to interpret the information. So this all is based on third-year Fourier analysis, very simple and straightforward. What we're really doing is trying to work out how much of the spectrum of the image is required to represent that information. So we take the Fourier transform, and the basic idea is that images which are smoothly varying will have very simple spectra. Anything with lots of sharp edges and foot-like features will have more complex, more filled-in spectra. So what we really want to do to make a ranking system is to condense the information content of the images into one number per image, so we can very quickly just go through the list and make a selection. The easiest thing we figured to do was just to add up all of the amplitudes you get from the 2D Fourier transform, and then you can normalize that by the number of pixels in the image, so they're all compared on an equal basis. And we found it was also useful to take the log, because otherwise the complex part of the spectrum due to the fine features tends to dominate quite heavily. And we're probably more interested in defining the large-scale structure of the image. So So we came up with a metric which bears a reasonably strong relationship to the content of the image as you would judge it by art in terms of, let's say, smoothness. Here are some examples of the results. So starting with smoothest possible case over here, this is an image composed just of sinusoidal components. And as you can see, there's very little in here whatsoever. There's a couple of points right in the center that you can't make out with the resolution. This is a log measure. This actually goes negative. It's a very, very small number indeed. So moving on to something like a photo, which you can see there. More complex information required to represent the image. Now we get 0.45 occupancy parameter here. Going to more complex types of plots or images is a random noise field, which gets up to about 0.8. And most complex thing you can imagine, a single point source in the center there. Well, a little plus sign, and you can see the orthogonal structure in the Fourier transform there, which gets you up to about 0.85. So there's a reasonable spread across the different forms of images, and we figured this was a good way to go in. So testing that on real data shows that it's borne out in practice. A picture of a star field like this with some diffuse emission in the background gives you an occupancy of 0.44, but something like a scatter plot here, which is mostly lines and points, gives you 0.59. So it's fairly easy to tell the difference between those two kinds of figures. Now it's a little bit hard. The range that you get from the real figures that people publish is not as great as the test data, mostly because if you're a good scientist, then you always put access labels on things. But there's always a small amount of fine structure in any of the images. We do, however, have the ability to make a reasonable comparison. And things that are more photo-like do tend to clearly stand out. So now the final thing is, how do we actually make the selection? And this was something we debated for some time. But we thought it would be best to go with the extreme cases so you get a good feeling for the range of information in the paper. So we choose the image with the most fine structure and also the most smooth structure, and then the one closest to the median. So you get a selection of 3 that represent a broad range of what's in the paper. The idea being that if the authors include something like a map of the field, and also a line plot or a scatter plot describing an analysis of that field, then you should get both of them. Here are some examples of what happens in practice. So you can see relatively smooth image, relatively compact spectrum, and so on down to something like this, which is all lines, and you get a very fluid spectrum. So it does seem to work reasonably well, but we'd be open to suggestions as to how this could be improved, or whether or not the idea of putting the extreme cases is in fact the best way to go. So I'll hand back to Lisa.
Okay, so I guess the next question is how have astronomers responded to archive.org. So originally we were just kind of developing it in secret, and then the first announcement was on Twitter, and so that's the Twitter bump here. So this is us doing testing. That's the Twitter bump. But the real kind of like inflow of people came when we announced it to the Facebook astronomers page. So that's this bump here. And so what we found was that it was really quite popular. We got a lot of likes, which is cool. But it also caused a lot of discussion. And one of the points that, which I'm going to talk about a little bit more, is just the fact that we chose to leave out author names, which was not intended to be controversial in any way. But a lot of these comments were to do with that point. So we'll talk about that a bit. And so you can see that that was the spike, the Facebook spike, and then it's kind of trailed off since then. So this is our current usage. So that week 41 is just the week of the year. That's how I decided to show on WordPress. So it's gone down. It's kind of like in a steady state now, maybe coming back up. So I guess we'll keep promoting it and developing it to make it better. And we do have, so the blue, I should have said the dark blue is the unique visitors, and the light blue is the number of views. So we're finding that people are coming and they are viewing quite a few papers while they're there, and they're pretty consistent. So it's even on the weekend. Yeah, so this is the distribution of views across the world. So this gives us an idea of what kind of people are accessing the site. So we've got the US standing out quite a lot. This is a horribly unuseful scale that WordPress, I don't know, it should be log or something. And Australia's quite prominent because we're in Australia and we tell people we know. Europe's kind of coming up a little bit. But yeah, and we actually have, there's quite a few countries all over the world that have accessed archive, so that's pretty cool. This is the current status. So we've currently posted 2,495 papers, and that's over about 60 days, I guess. There's a few more tweets because we've tweeted other things. But yes, we have a Twitter feed which basically syncs with the WordPress, so it automatically posts to Twitter. Some people follow it that way, and some people follow it through the blog itself. So this kind of goes into the role of the Archiver user. So we built Archiver mostly for fun and also just, I guess, to kind of help us keep up with the literature. But we see it as a tool for the astronomer. So if you're trying to learn about new literature or just keep up with new developments in astronomy, you could use Archiver to do this. And so to kind of, I guess, gauge what people were feeling about Archiver, how they felt about different things we've done, we had a survey, and that's been running for about a month. I think it's still open. If you want to go fill it out, you can. This is based on the results we have so far. And the goals were to gauge opinion on author names, to identify what people thought would be the best features for future development, so what we should focus on, and also just to figure out how people felt about Archiver, so if they felt like it was useful, if it was not useful, if it could be improved quite a lot. And so we had 158 responses from around the world. This is the distribution of them. If there's multiple ones in the same location, it doesn't show. It's just showing where they are. So we have US, Europe, and Australia again. Europe features quite prominently there. And so the question of author names, which I kind of mentioned before. So this was, like in the post, we have the title, we have the abstract, we have the link. So the author names are literally click away, you click the archive link, you get the authors. But we chose not to show them originally because the idea was that with the abstract, the title, and the figures, that if you were reading it yourself, you might be able to judge whether something was scientifically interesting to you, regardless of whether you knew who wrote it, whether you didn't know who wrote it, just to avoid, I don't know, any kind of biases that would come up with that way. And so we did that, and there are arguments on both sides. So there's ours, which is avoiding bias, focusing on the science, so whether that's relevant to you or not. But also, we don't, like, you know, the other side of that is we want to give credit and, you know, acknowledge people that have produced these papers and the work. And also, if you don't already have familiarity with the authors, then you could build that familiarity by reading it over time. So there are arguments on both sides. So we used the survey to examine how people felt about this on a more statistical level. So these are the results. We've divided it by category. I'm not really sure what other is. We figured maybe honours students, maybe technical stuff, but we're not 100% sure. We probably should have had a box that said what you are. But we've got professor, postdoc, and students. So the interesting thing here, I think, is that the students are the most divided. So you can see half of this bunch say show, half say don't, and there's quite a large number that are different. This is all normalized percentages. And then as there's a trend, as you increase in academic level, you're more likely to insist that author names should be shown. So this could be a trend that's changing over time. It's not, you know, there's not a huge difference, and overall the majority does say to show names, but there is the influence of academic level there. So we asked how many should be shown, which is also an important question. The first thing you notice is not many people think first and second, so I guess first and second is not, you want 3 or all or something. The majority say first, second, third. Quite a few say none or first. And I think the other interesting thing here is that the trends kind of switch. So students are the most likely to say all authors, and we wondered if maybe this was because they all further down the author list. So if it was, you know, the first 3, they might miss out on accreditation. So, because we did ask people as they were filling out the survey to think about how they would feel as authors. So overall, we're seeing that people do want author names, and they do probably want all or at least the first 3. And that's functionality we want to build in the future. Where should the names be shown? So most people argued for a prominent position, either under the title or at the bottom of the post. We've also gotten the link to archive, which was suggested on Facebook, none in the metadata. Ironically, in the figure names, so this is the only one we've actually implemented so far secretly. So if you're dying to know the first author in archive, you can hover over the figure and it'll tell you the first author in the archive. Because we didn't want, like, if the figure got spread on the internet or something, we wanted that to be built in. So that was the least popular, so maybe we'll take that out. So we also used the survey to identify paths for future development. So we're going to use the results of this to prioritize what we develop next. So the 2 most popular things were distinguishing types of papers. So this is accepted, submitted, not accepted, I guess, or as well as conference proceedings and journal articles, and also specifying the plots. Because we have access to the LaTeX files, it wouldn't be hard for authors to have a commented thing that said, you know, at archiver, and then the figure names, and then we can go and access them. And so there is opportunity for authors to control which figures display. We asked people how they felt about archive. We got pretty good. Like, no one gave us 1 star, which was reassuring. I know, you know, we got about 2/3 of them gave us 4 or 5. I think the average or the median was about 3.8. So that's pretty good. And I guess what we see here is that most people are pretty happy, but they do see room for improvement, which is good, because so do we. So that's what we'll be working on next. So the future, we're hosted on WordPress.com. We're currently at 24%, so we're not nervous yet, but we're slightly nervous. So one of the plans we have is to move to a server, so a dedicated server. It's not a huge capacity a year. I guess it would be a few gigabytes or something. So it's not a huge demand, but it is something we need to do, and that will also give us more control over changing things like the author things. One solution to the author names is having an option or a button that says show or hide author names, and that pretty much solves everyone's problems. But that's the kind of thing we can do once we move to our own server. The survey has helped us figure out what to focus on next. We've got a list of things to work on and which things would be best. And it would be good to collaborate in the future with other open data. What?
Sorry.
Is that my time? 2 slides. Maybe it might make sense for something like this to be hosted on Archive itself. We haven't heard back from them, but hopefully we will. And also, the Fourier spectral occupancy is an effective way. Like, we found that's really effective. You get a nice range of images. And this could be applicable beyond Archive. So I guess if you have large surveys where you want to figure out where there's interesting things in images and you don't have time to have a lot of people look at it, then that could be a useful thing. In Astroinformatics context, what we found is that just the response of people's Archive has meant that it is really important now, more than ever, to consider how you present your information and how relevant it is to your audience, because astronomers don't have a lot of time, there's a lot of papers, so you need to make it as digestible as possible, and this obviously applies to pretty much every kind of sharing information that there is. So finally, please visit Archive. That's the link there, and let us know if you have any ideas or feedback, if you like it, if you hate it, everything. And yeah, thanks for listening.
Thanks, Vanessa and Aidan. Right, questions.
The thing about allowing the authors to select which figures they believe are most representative of their work is, I think, a very good one. But I wonder if you could actually even go further than that, that there's more tagging that you could encourage authors to do to, link to other things or highlight broader keywords or concepts or that sort of thing. There are already some tools out there which work with Archive to do that sort of thing already. And then that links you into the linked data and ADS and all this sort of thing as well, which, there's been some sort of suggestion on earlier today.
Yeah, well, that'd be
but maybe you want to think about that as well as something to look at.
Yeah, I guess that falls into the kind of collaboration with other projects. One thing we did try, as well as just the Fourier analysis of the images, was counting the references to the figure in the paper. So that's kind of defined by the author. Aidan's idea was that, if it was referenced a lot, it's probably pretty important or difficult to explain. And so we tried that, but what we found is that people reference in different ways. Some people don't use the latex referencing at all, some people do, and so it needed a bit more work in terms of categorizing how people reference.
Not just the figures, also the text.
But yeah.
The text you can parse through, figure out which are the most popular 3-gram.
Yeah, no, that would be.
Should that be in the abstract?
In theory.
No, not necessarily.
Yeah. But no, actually, that's one of the things, because someone asked, I guess one model would be if we move towards a user service like ADS has, and if we were able to pass it in that way and determine what keywords were interesting to people, then people could say, you could log in and have the top 10 papers recommended for you in a meaningful way. So that'd be really cool to work on in the future.
Right, George.
So, just going through it, it gives you a nice, easy way to read, but the thing that kills me on Archive is I have to go through about 95 things for everything I want to read. And so having a user-specific interface that would read the abstract and would train through some sort of neural net would be the thing that would absolutely make me an adopter, and I would not ever go back. This thing is this thing, and this is. I have a little Perl script I know that steals it and did that for a while. My point being is that type of thing I think is what's really missing from this issue.
Yeah, so I guess identifying which thing would be making use of.
You just have to have a cookie that you train.
George.
Have you thought of crowdsourcing collecting of tags or keywords? Ask your users to contribute tags, and then if you are getting consistent ones, you can use the transactions.
Yeah, that'd be cool. I guess, that would help with the identifying.
I think that actually has already been done by a separate
Was it? Which project, do you know?
Science-wise.
Cool, yeah, it might be useful to get in contact.
The science-wise, it's all about semantics and ontology.
It is, but
things
from the
like that.
but it uses user-provided tags.
Durable in the beginning and spend time on this new things like having machine learning or more intelligent tools that can help the assist calling data instead of asking the people because they have different opinions and you never can comply with all of them. So just
so I
make
think
it
having options and things. Yeah, so that, I mean, I guess the key thing for us from now is to move to our own server because that will allow us to install plugins and run scripts and stuff, so we'll have a lot more control.
Giuseppe? Comment on the question. First of all, in my experience, I read in production conclusions. So I think there should be a weight given to figures which are referred to in the conclusion, especially when much more significant. The second, just, did you try to have any feedback from the authors of the paper which you have indexed in order to see whether you pick up the right three features?
Yeah, so we haven't specifically asked anyone. We did have a comment from Brendan Brewer on Twitter who was like, oh, I love the figures lecture today. I asked him why, he hasn't replied yet. But we haven't had specific feedback. We've shown, I think there was a Molt 90 paper that appeared quite early on and they said, oh, those figures are good. But yeah, it might be good to like, I guess, send out emails or something to the people that we've already archived and see what they think. That would be really cool.
Sorry, Andrew next.
Well, I was just going to pick up on the linking to other facilities idea. I think Andy already mentioned Fox Charter, which is a tool that lets people rank archive papers to feed into journal discussions, journal club style discussions, which we've recently started doing at TAO as well. So that might be a way of kind of identifying feedback on specific papers where they're ranking and you can
So do a lot of
present
people
them.
rank papers? Like what's the average number of rankings per paper?
It's not high.
Okay,
It's
because I
not
saw
high.
some papers like most of them had none.
Most of them had
and a lot
zero.
had like 2 votes.
But then
But
the ones
I
that
guess,
have a few dozen ranks,
Yeah.
a few dozen votes, clearly should be highlighted.
yeah, that could be, I guess if we had like a user interface or something, it could be like, you know, the top 10 papers on Vox Charter recently or something. That'd be cool.
So I have a suggestion, rather than crowdsourcing keywords and things like that, which does rely on a lot of people giving the information, and as well, if you had authors log in to select which figures and stuff, instead of doing that, since you have access to the LaTeX, have you considered having something on your frequently asked question page or something like that, where they could just put in a comment into their LaTeX file or something like archive preferred figures, and then the file number for the tweet.
Yeah, so that was one of the things we were planning to do.
And they could put in keywords into the LaTeX themselves as well, and then that would rely on anything else. So it would just be there as well.
Yeah, that's true. So yeah, I mean, the figures, that was one of the things we had on the survey, which was, you know, having it like at archive or in curly brackets, the names of the 3 figures, and then we don't have to search for them. But we hadn't thought about the keywords, that'd be cool. I guess in some ways we could also just pull out the keywords from the journal article that are the tags to some extent. But yeah, because I always have, when I'm doing paper and I have to do keywords, I have no idea. So I don't know if authors would do that. I guess it would be easier to say which are their 3 favorite figures. But yeah, as an option.
So I'm just curious as to whether what's important here is showing 3 good figures or just 3 figures.
3 figures at all, yeah.
And can you just randomly select, you've got 12 figures, so you take 1 from the first 4, 1 from the next 4, 1 from the next 4, and you still get a reasonable representation of what the paper was about. It seems a lot of extra processing, which is maybe interesting in its own right for learning something about figures. But I'm just wondering, is it really,
Yeah, so the
is
first thing,
randomness good?
the very first thing we ever did was we just like, you know, did an LS for figures and took the first 3. And so that was not quite random, but it was the first 3. So that would pick, I guess, if there was a set of 3 figures at the start, then they were all the same. What we were finding is that like a lot of papers might have like 2 pretty images or, you know, images of the field and then like 20 line plots. And so we were finding that if you did it randomly, your chances of selecting a less or like a less variety of figures. It depends really on what the ratio between like low spatial frequencies and high spatial frequencies in the paper was. So we found that, I mean, on average, like I think we did when we first implemented the algorithm, we did a comparison. So we did it randomly and then we did it with the algorithm. And we found, there were some cases where the random was a bit better, but in general the algorithm did a lot better because it just picked a variety, because it sorted them based on that factor and then picked the variety. So you're more likely, I guess, if you're really interested in line plots, you'd see something. If you're really interested in images, you'd see that. But yeah, it's something that we do want to test in the future, I guess, to figure out, or maybe that could also be an option, right? Like to just write it or something like that.
Okay, let's say thank you very much to unfortunately, let us get way beyond time. The discussions were too good to stop. But let's have a quick discussion session anyway. First thing this morning, I asked you to think about what do you want to get out from this week. Maybe we should broaden that slightly. What should one want to get out from a week-long conference about Astroinformatics? First of all, I'm going to ask the speakers for this morning if you would like to. I'm not going to force you to thought of anything, but I'll give the opportunity to the speakers first. Right, anybody? Andrew.
I think what I'd like to see coming out of this week's discussions and presentations is a way forward for the Australian community specifically to build on the very preliminary efforts that we currently have at putting together data archives for our own big facilities, which are really just coming online now. This is a new territory for Australian astronomy, I think. ASCAP and SkyMapper are really forging the way ahead here in particular. And as a community, I think we still have a lot to learn in terms of how to curate and host the data resources that these things are going to provide, but also to interact with them and do science with them more broadly, because while I think most of us here are probably quite familiar with how to play with the Sloan data archive, for example, as a community we're not in a position to replicate that type of infrastructure. We're developing our own ways of doing things and trying to build on a lot of the lessons that have been learned since then. So I think one of the really good things that I would like to hear a little bit more about over the course of the week is what is available now that wasn't when the Sloan archive was developed, that we can take advantage of to make the interface between those spatially distributed archives better in a way that can allow us to maximise the kinds of science that we can do with them and how we think about doing that science.
You don't come to a conference just to hear about stuff. You said, indeed you will hear about the databases and so on during the week. But the function of a conference, in my humble opinion, is the interaction, actually. And so, from this week, it's not about us just sitting here, listening, finding out bits of information we might not have otherwise. And that's part of it. But it's also about changing the direction. You've got people in this room, some of the best experts, and the people who are working on this stuff. And so what would be really good is if the people in this room who are actually designing those databases were having conversations with the people who are actually thinking about future directions and what we need to do, which might actually change the direction of where we're going. And that's the sort of thing I think, why you have conferences. So I have pick on Alex actually, who's been very heavily involved in that sort of thing. I mean, is that how you see the function of a conference like this? Why do you come to a conference like this?
So in a sense, I think we solved the problem of kind of the archives of surveys on the existing sites. It has yet to be seen how the LSST archive will work, and also how we will be able to scale up to SKAs like this. But I think people are now also comfortable. So I was really pleased to hear how many people mentioned already just in the discussions that yes, this will archive is easy to use. But it would be nice now to be able, it would be nice to enable, and this is kind of, I think, my one sentence outline, to enable people to take their own small to mid-sized data sets and be able to work with those in the context of the big surveys. And I don't think there we have a very good story yet. and the other is that how could we use actually simulations in a way we use surveys today, in survey design, etc. So right now we still design survey, like putting our fingers in. So it would be nice if we had a suite of simulations where we could really assess the statistical properties. If we cut our sample this way, if we cut our sample that way, how would that change actually survey strategy? But every dollar counts. We could use these optimization tools to actually influence how we conduct our future surveys.
Okay.
And it would be nice to talk more about those in free-form.
Anybody else like to comment on that?
So I don't really see this thing with databases solved for the moment. So if you want to apply machine learning algorithm, it's for me always a lot of work to transform the data, to work with that. So really one reason why I'm here is to start a little bit more discussion in that direction, how we perhaps can enable the old appliances somehow to provide the data I want to have as a computer scientist to apply machine learning algorithms to solve problems astronomers have. And so I really think that is still an issue we have to discuss on and start discussion.
Yeah, no, I would say what I meant is that we solve I think we solve some of the basic plumbing problems. Jim used the word always plumbing.
Yeah.
And I think, I agree that the machine learning is very far from being solved. It would be nice if, for example, to launch a challenge where we would ask basically the machine learning field to rediscover some of classical astronomy. Just discover astronomy the way it was a little after Hubble. We have infinitely better data sets. So it should be easy to discover, stellar evolution, etc. from the existing data. The machine learning tools today are still, or many of the machine learning tools and the toolkits, including R, are not really scalable to the sizes that we need them. So typically up to 10,000 points, most of the R modules crash. So others understand this and are rebuilding it. So, but there is indeed a lot of low-hanging fruit there.
That's what Pascal just said.
Just to continue along the same line, I agree with you that that is also one reason why we keep organizing this conference, because I'm looking to see that. I am forward to see the moment when we will switch from the data-centric problem to the information extraction problem, which is still in the making. That contest hasn't been run. We rediscovered that the Hubble law together with Mary Madonna, you understand. It's, what I really think is a hot issue, since we are doing data mining application every day, is the extraction of reliable basis of knowledge. It's not only the way to access the data, but it is in the scalability of the algorithms. Most of the data mining algorithms do not work with 700,000 records. And the type of information which you can extract depends very much on the quality of the piece of knowledge which you're using, and the quality depends on the quality of the flags you have in the databases and so on. So it's a really wide field which should be explored if we really want to extract the information from these huge surveys. So this is why I'm here to answer your question.
Thank you. Tony.
Yes, well, of course I'm not an astronomer, but I attended recently the DOT Astronomy Conference, which is an unconference. Now, with no structure predetermined, I sort of like a halfway house, personally. But it did have sessions where people actually were comparing tools and writing some code and doing things. And maybe there's a room in a conference like this for some hands-on that people can demonstrate tools. Maybe everybody knows them. But I would be very interested personally to find out which algorithms from machine learning, which is a whole complex set of algorithms, which ones are used, and what do you use them for, and how do you compare red with things in visible and so on. That's what I would come to learn. But I liked the dot astronomy because there was some hands-on stuff. But I also like having some structure as well. So,
interestingly, that we actually had a discussion in the SOC. Darren Curtin, who's not here yet, he'll be here later today, was actually pushing that we should have a dot astronomy type thing. But I think not everybody in the SOC agreed. So that we felt we didn't really know how to run that, and I don't know. It would have been nice, I think.
Having something in the middle, I think.
Yeah, I think
session,
these.
I think, is,
Pardon?
I think having a session,
Yeah.
like a half a day of it is quite effective. 3 days of it, having done it is a little tiresome.
Maybe that's something to aim for the next session. I like the idea.
But if I can say one more thing, so echoing on what Tony said and also what Brian picked up in his talk, is that if we could somehow increase the agility of astronomy, and so it means that we should be able to come from an idea to something like a new service in a matter of weeks, which is what Google and LinkedIn and all these companies are trying to do. But this also requires, and Microsoft, maybe in 6 weeks.
Microsoft or Microsoft Research?
but somehow, and this requires probably a very well engineered and a very well documented toolbox, so that people can patch the models together extremely fast. But also there is a mentality issue that some, and this is where I think the data astronomy, the people are the makers. That attitude should be encouraged, and maybe sometime we should talk a little bit about this, what could we do as a group to actually encourage those young kids who otherwise leave.
Hello everyone. My name is Shudlin. I'm not an astronomist, but I'm an engineer and enthusiast about Lagrange data. Well, I'm just around this morning, and someone just noticed like sleeping into the room. Well, I'm here representing a company called USB Lab. It stands for like Research Shell Programming Laboratory, and as it is, it's all about shell programming. Well, we are just one of the sponsors here, and we want to show some solutions for organizing your data with the shell program. There, Professor Brian introduced the Python this morning about the shell programming that we provide, which is just much faster, 100 faster processing. It's really easy to study. I'll be here for a week, and I'll be around this table. So we also want to show some demos, live demos, and if you're interested, we want to see some live demos. And so far, I've listened to your presentation. You guys are at the point. From now, we want to decide your direction, which direction you want to go, which direction could be your future. So the solution that we should introduce might be one of a selection. So there are lots of companies like Microsoft, Google's. So just take a look at what we show at the tab.
I should explain. These guys are funding the wine tour tomorrow, so thank you very much.
It's my pleasure.
And so if anybody wants to talk to you about this, you'll be around and coffee and lunch just next door.
We're going to be around.
Yes.
So,
okay.
Thanks so much.
Any more? Oh, okay.
Challenging problems like data and sharing, because have been already mentioned. What I would like to see maybe by the end of this week, we could come to some common understanding in terms of what education we need to add to astronomy to make our students, and agility was mentioned as well, that doesn't come as granted, needs to be educated, students need to be educated. It would come maybe can send a message to the community what needs to be done to make our students be better programmers.
Any more? We get too hungry. So all the sandwiches, there's sandwiches and wraps and things like that out there. Let's thank all the speakers this morning. Can we be back in here 20 to 2? 1:40.
Только, скажем так, все свое предназначение. Если мне надо написати переконаний, типу світню, то це можна зробити вольно. А якщо мені треба, не знаю, якісь серйозні не раз зустрічав веб, це така штука, яку не знати було, якщо в ньому там 3 роки подряд Ні, так я тільки начав, я то полгода назад начав.
Yeah, absolutely. I'm sure it's very parallel. All the government initiatives all change names and package you put it in this thing goes down and this one starts up. And then they're exactly the same. All over the place. Space. Thing to know. It's just good.
So she's already
Наших людей, які говорять англійською, я нормально приймаю, навіть на сьогодні конференції, тобто все нормально, слухаєш, що саме. Вообще просто невероятно. Как бы вообще, скажем так, с носителями языка английского вообще в принципе никогда не общаться. Все, кто у нас, то есть всі, хто у нас на конференції, то есть це большинство людей, це англійська, це не їхня річ. Тому що там, навіть якщо з-за кордону приїжджали, то це там, наприклад, поляки, серби, теж не їдуть. Ну і тим більше русські, коли у нас половина людей на конференції, це наші і русські. Вообще так слухали, просто не співаю просто Никого открыли, я не думаю,
Yeah, the people on synthesizer speak
bigger distance size vector is not actually a single line, it's many lines. Yeah, so it's actually somewhere in between. So I just said, maybe there's a single line, these are what the best vectors are, and we just use that. But we're just guessing, like we don't have the real wavelengths yet. So when we get the high resolution data, then we can resolve some of these blends. Then we can say, okay, that's a line there, that's a line there, which one is it? Look at this for the best version. And then you just
At some point, you know your value is analyzing. You're not exact. You don't have the meaning of your body.
That's right. And it turns out it wasn't.
That's what I assume.
Тебе възможно няма да...
Exactly, yes. And that's exactly what was happening. The reason why was because there is one icon right at the edge of the CCD, which is useful, but wasn't being used. So it was a good way of calibration, okay way of calibration, part of it. And then the last bit was just screwed up. It was, we don't have to. So it was just really getting more fixed. I think when the high resolution data comes in, and then you can start measuring the velocities with these styles, then we can start to see the precision is
Do you think, do you know how intelligent we are? Does that scaling? Do you know the algorithm?
I don't know the algorithm that they use. I wondered that actually, because I just did the calculation myself. I just wrote something in Python. And so, I don't know how they do it, but I did say that my mail was but I haven't tested it out on new
So in theory, assumes some form of wavelength density along the trunk that becomes the wavelength.
So, I like if I was breaking it, I would say, yeah, so you extract each of the spectra from the channel, and then I would just look for the peaks, and just look for the and then cross-match the pixels that I have against the wavelengths the spacing and try and fit that.
Because if we have, I was when I was talking to the starts reducing the flap. And by the time we reduce the flap, which I think guesses from the range of the yeah, so that's like a linear, okay, that's my limit.
I noticed that too actually, and I think that must be what it uses for its initial data set. It must have to capture that. And that must be how it which is okay. I mean, when I did it separately, I had it just so you can
we need to move both a little bit too far to that way again. Some speakers are in here.
It's good there? Yeah, it's right on the edge. Malta, come and have a look now. Malta's in shot. Oh, sorry, you're in shot. I'll come back.
Do you have okay. Right, and you said turning that one away from the speaker, or? No, you said before that you should turn the microphone away.
No. Oh, was it me?
Several people requested a hand around microphone.
Okay, we have one.
Do you have one?
Yeah.
But yeah, we would need that.
And then tells you, gives you the
everybody's going to apply the
distribution. So you can pretty much decide who you think about what's going on. So it's easier to decide.
So yeah, that's the
So almost just that, but
yeah, so how far
to know where all the light is going on each of these. It's actually a channel, and they need to be able to do the extraction of all the fibers and then calculate the smart box means.
try and show that on something that is easy to see. So I'm almost reached that.
So yeah, the only thing is really the smaller light.
You see the numbers? I've seen, yeah, I've seen interesting data. It was just that, and then use that signal noise given channel and compare it to the other two. I'm not sure whether it's calculating the signal to look or if maybe the extraction I'm doing isn't quite accurate. So it's coming back with more of a signal to just need to try that out to the other So how are you doing the timeline yourself? No, I thought about that. It's already done. Yeah, so what I did is I just reduced every channel into the so basically I just had to which I may need that yeah, it's a few kilobytes. It takes 30 seconds to reduce it to 4 channels. So it's just a quick little you know the thing, I don't know, you mentioned that when it's done with the first principle. And my supervisor is very keen on I don't understand it. I can't see the whole picture, so I try to see. He sees that if I can similar thing for him, I'll have a meeting good from the sense that he's from
hopefully you're publishing it so anyone can watch it.
This is what we're trying to do. And then that. And what way corresponds to his infinitely precise pixel. So that's unrealistic. This is the theoretical. So I'm keen on testing it and seeing if I can generate something representative. Generating whatever format in whatever part of the process to the as soon as you actually do that last polynomial and says, okay, this is what I'm doing. So try to cut that down. Yeah, okay. You can use that for the extraction. You could do the extraction and the evaluation of templates. If you have a model, for example, where all the light is going to fall on the CCD and what the wavelength would be, as you say, like, even though you pixelate it, you can actually map the entire thing, extract the and then have know what the wavelength is of each. But that's not good for reading. But yeah, I think that's what my check was assuming that 2D-FDR was already smart. Yeah, that was my design. Rewrite it like that. No, I have to practice that. I just see what is there. Because there's so many, for example, the optimal structure, things like that. I'm not going to be able to that with things like rewriting the wheels. And you say, cross information is a good way, but optimal structure is going to be step up from that. So what is optimal extraction? Is it just keeping the portion at a sort of angle and then extracting along that perpendicular line? I don't know what's I think because I got to the I was doing that program workshop on the initial reality. That I don't know you really want to workshop get some there's actual communication in PASA. It's called and it's it was a new involved, so I think we discovered it. But what I understood based on the earlier on the way it's building up this part is it takes in consideration the cost of
I was also going to ask everyone if they actually had shares on the first of the because otherwise, if you can't sit on the front row,
it seems to me that
it might be a hassle when you get in the one around. So I'll see whether I can actually see.
Yeah, I'm thinking that. I mean, the other night when I was doing this before,
Okay, thank you for thank you for the it's really interesting. And relevant. And just the problem
Yeah.
it going? Okay. Sorry, I flipped around. I'm sitting in the conference hall, so if I get kicked out, for being loud and boisterous, I'll let you know. Yeah, so I just wanted to chat a little bit about the CSIRO stuff before we broke up for Christmas, because if there's anything I need to be thinking about getting started with immediately when we get back, or doing before we break up, then yeah, I need to just kind of get that stuff sorted. I know. I suppose it's up to us to some degree, right? Because being at the same institution makes it a little bit easier to do a smooth transition, at a point when it's suitable for us. But I assume that you're not burdened with anything. Sorry, go ahead. Okay. I think that makes sense. I also think that like the key to help out where I can, while you're doing that, sort of tying up loose ends, because for one reason is that it gives me insight into exactly what I'm supposed to do, so, which is always helpful.
And obviously it's extremely overloaded and it's really complicated stuff.
Actually, yeah, that'd be great.
We've obviously got an
So that's for the 2015 research highlights for the annual report. Is that the idea? Okay, cool. Yeah, I think that's going to be really, really difficult because you can't know outside of your own project, right? It's going to be the big conference or the big is it worth asking the PIs? Yeah, it's really kind of quite speculative stuff, right?
I think if we can try
yeah, exactly. Yeah. So do you think it would be worth getting PIs for the projects to I don't know, give one research highlight each for 2014 or something? They're second in commands, yeah. Awesome. Okay, cool. Yeah. Okay, no, that's really good to know. So suppose you've been continuing on until January or whatever. How about if you kind of decide what it is that you need to do and what you want to try off, and what bits and pieces you want to do before we officially hand over. And if there's anything that you feel like you could delegate and tell me like exactly what to do, then I'd really be happy to help. But if not, that's fine as well. It's no big deal either way. I'm just a little worried that I don't really know how to do it. Yeah. Okay. 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 I think I did get that, yeah. So there's two from scratch essentially for evolving. Yeah, so I asked Kate who the PIs were, and she sent me a list, so that's okay. But again, it's figuring out who under the PI to go to get most of the content, I suppose. Right. Okay. Yeah. 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 Yeah, I think Kate was saying. Yeah. Doesn't sound overly compelling either. Okay. Probably everyone had the same problem, right? So why have it in the first place? Okay. Yeah, it's just not something we're used to doing, really, is it? Okay. 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 And so, would you put that under your heading of stuff you want to wrap up before January, or before end? Okay. Okay. That's fine. Okay. Okay, well, I tell you what, maybe when we come back after the break, we could chat about, like, phasing things in and out, as it were, between you and me, and, you know, we could just pick a date, and by that date, you know, if you haven't got everything done that you want to get done, then that's fine, just tell me what the stuff is, and I'll just do it. But, you know, yeah, I was thinking it might be a good idea to start that off sooner rather than later. Okay, so they'll be able to get a skeleton together pretty quickly. Yeah. Like the content. Okay. Fair enough, yeah. Yeah. extra like carriage returns and stuff. Yeah. Okay, so I'll aim to send an email out about the 2 new ones this week, and I'll CC you on those, and just sort of get those going. And then, depending on what we get back, maybe we could chat again in January and figure out the lay of the land for all the other things and how everything compares.
So,
cool.
It's lunchtime at the moment. So this is where the talks are.
Yeah, I think it's just probably a case of putting this on the list. I hope. Do you want the email that 2014 research highlights as well, or what do you want to do with that? It's a really tough one. It's actually from a strategy point of view, yeah, as opposed to sort of individual project highlights, sort of strategic highlights might be a bit more what they're after. Yes. Well, let's just say that you'll do that, and I'll start on the evolving, the new from scratch ones. Yeah. Sounds like it's probably, one of those things where, they're takers, so what are you gonna do? Yeah, exactly, right, so it's good. Cool, awesome, good. Okay, at least I sort of understand things a little bit better now, that's good. It was the simulations one. It could have just been me. I've been having internet issues at CIFA with my Ethernet cable. So the Wi-Fi works fine, but the Ethernet just drops out randomly every like almost once an hour. It just drops out, and I'm left without internet for like a minute or so. It's very irritating. So it could have just been something like that it just didn't load for me. But if you check it on your machine and it works, then it's probably not a problem. Oh, okay, cool. Okay, just be sure, will do, absolutely. And thank you for calling me at lunch. Oh.
Might be covered by
Unfortunately, got delayed by.
At least we can describe it in intricate detail. So we can build a simulation that just plays the laws of gravity in a cosmological background. This is what we're doing here. So we'll take something like that. So here's just a slice through a simulation like that. This is called the cosmic web. And for those who are not astronomers here, the scales here are billions of light years. Okay, so very, very, very large scales. And so what we would do is, on top of this numerical simulation, we would paint an analytics simulation of the galaxies in, because we don't obviously observe the dark matter, we only observe the galaxy light. So we have to paint
light. So there's the galaxy light for a particular model. And what would we do with that? Let's say we might zoom in on this region here, and this big supercluster, and we have the galaxies color-coded here by some of their properties. And then we might go and compare this to, say, some observations, for example. Okay? And we would hope to try and understand this by exploring this. And the advantage of doing it this way is we know how we got to this point. We have the full histories of all the objects in here, where they came from, why they look like they do, given the assumptions that we put in. So these kinds of simulations would follow up to 20, 50 million objects at a time. Okay? So we can use this to try and understand this, which is just a photo. That's all we have. Okay? Now, of course, the data challenges involved here are becoming very significant. And this is just a plot showing the number of particles in a simulation against the year. And this is following some kind of Moore's law scaling. And we're in the tens, moving into the hundreds of billions of dark matter particles that we're following when we simulate these objects. So we need massive supercomputers, and probably more important and more relevant for this workshop, in order to use this data, in order to make it available for other people to use, we need cleverer tools, because we can't just dump a few terabytes into a directory that give people a link for that or create a table. Of course, it doesn't work that way. So theoretical astrophysics is not the only one with this problem. I think observational astronomy is facing a worse problem, because at least we can recreate our universe as if we have to throw some data away. When you're observing the universe and you've dumped a whole lot of money into a new telescope or instrument, and you have to make choices about what data you keep, because of these data sizes are massive. Right? You don't get that data back. Right? It's gone. So we have to approach this very intelligently, and I think the theme of one of the themes of this workshop, a lot of talks that we'll hear when we're discussing these kinds of problems. So the wonderful thing, though, is if you can find a way to store it and put it online, you can have a huge impact. Right? So one example here is the German Astrophysical Virtual Observatory, which has put theoretical data, like what I showed you, online with a simple SQL interface. So you can go there and you can query the databases and just pull the information out of those live columns that you want. Okay, so this is quite common now. And the impact of this has been huge. You know, hundreds of papers from a single model. So, as I said, I've paid with 1,500 worth of citations. One of the reasons for that is because you make these models available to people. And they go and use them, because there's so many ways that these models can be used. Okay? So it's great for them, it's great for me. Right? And so data access is becoming very important. And many thousands of citations. And of course, we have Alex Soleil here, and Sloan Digital Sky Server is, the Sky Server is basically the poster child of this kind of data access. Observational data is definitely moving in this direction as well. Right? And HSD, just to point out, this is showing the impact of the Hubble archive, and this red region here, so this is a year and the number of papers. It says science papers. I'm hoping they're not all published in Science. And the red basically is the number of papers that come from data reuse. Okay? You can pull that data down from online. And so you can see that the blue is from observations, and that's kind of flat, because it's only, it's 24 hours in a day, and Hubble takes however long to go around the Earth, and so there's a finite amount of data that it can observe, and hence there's a limit on the number of individual papers just from the original proposals that can be put out. But when you put that data online, other people find creative ways to use it. That's why this line goes on. So I don't need to convince you data access is important. So how do we do this? Well, a while ago, a few years ago now, the astronomy community here in Australia recognized the importance of bringing these data sets together and making them accessible. So this was from a working group that Astronomy Australia Limited put together. So Australia needs to build an astronomical data fabric that links these massive data sets, right, so we can fully exploit them. The midterm review of the decadal plan, reinforce this. We need investment at national level e-research and construction. Right? So how many people have put this into a proposal? Something like this, give us money, right, to take our data and put it online or do something clever with it, make it available to other people, and it's really, really hard because often there's no direct scientific outcome out of this. Right? People pull the data down and do science with it, but you can't write that this is going to understand the red sequence of galaxies or how certain stars explode or whatever. And so governments like to invest in hardware, and they often like to invest in pure science, but that bit in between is very difficult. And so luckily the Australian government recognised some value in this at least, and they established this NECTA program where they basically put down $50 million for the entire science community in Australia to build virtual laboratories. And astronomers from England competed for some of this money and were successful. And out of that came the All-Sky Virtual Observatory. And the goal for the ASVO was to take SkyMapper data and theory data and put it online for the masses. Okay? And then what we're doing there is building infrastructure that you can bring other surveys, other wavelengths in, start from the ground up. So this is what a number of us in this room have been doing for the past year and a half, is trying to build some of this infrastructure and bring the data sets in. So I'm going to talk about the theory side, the movie I showed at the start, how we do that. All right, so let me just, so we do have examples of this. So Garbo is one example, the German Astrophysical Virtual Observatory, which is an SQL interface. So our vision was a bit broader than that. So we wanted to broaden it, but at the same time simplify the process. So here's the idea. So you have a data store down the bottom, down here, and take some simulated data, drop it in. Okay? And that would be one. This is an example of how Garbo works. For example, then you just put an SQL query interface on top, and people can pull out bits of that data that they want. Okay, that's great. But you can do more, and this is what we'll really do. You can dump some tools on top of it. I'll show you some of those tools in a minute. And if you make it modular, you can add another tool. You can say, oh, I don't like that tool. Switch it out. And then these tools would do something to the data. They would enhance it in some way. So they wouldn't do your science for you. I found astronomers like to do the science themselves. But they'll enhance the data in some way. So for example, this tool might take that data cube, that simulated data cube, create a light cone out of it. Right? As if the telescope was observing the galaxies rather than just in a Cartesian coordinate system. This tool here might build images. This tool might work out the spectral properties of the galaxies in this data cube. And the nice thing is, if you change the data set, everything else changes on top. You don't need to reinvent all these things, of course. Okay, so this is the underlying paradigm of the Theoretical Astrophysical Observatory, or TAO, short. Basically, it's very hard to read, but the idea is just to have a simulation database at the bottom level. Access is not through SQL. Okay? My experience is that astronomers, although we're learning, are not that great at learning new languages. We would like to, if we can avoid it. As someone whose data originally went into the German Astrophysical Virtual Observatory, I would get emails all the time saying, can you write a query for me that would pull out such and such data out of Garbo? And I would say, I have no idea how to program SQL. I don't need to go in there to get my own data. So I didn't know. I've since learned, of course. But we want to make the bar as low as possible, right? Access for everybody. So it's a web form data query interface. On top of that, we build spectral energy distributions. These are the science modules. We build light cones. We can build images, and these combine together to basically simulate the telescope. Right? And so the nice thing here is we can put different data sets in. So these are just 3 simulations of Quinian, Millennium, Bolshoi, and Eagle Z. Eagle Z was the one that you saw at the start. Right? This is actually really important for the science. For those astronomers, non-astronomers here, what I'm showing here is 3 different slices of time. So this is the present day. And so as I showed you before, the slice of the cosmic web, the large-scale cosmic web, these are slices of time going back in time. And these are different cosmological models. Right? And you can see that the evolution with time and where they end up looks different. So we can test ideas of cosmology by putting different data sets in and allowing people to access them in an equal way. Okay, so I'm going to skip this and I'm going to go straight to a demo. Okay, so this is Power Live. We expect to go public next week, next Monday. If anyone's interested, you can sign up in the URL will be at the end, which next year we have a continuing program of enhancement. But here's the idea, right? Let's go and build a catalog. Okay, as I said, no SQL programming is involved. Let's take the Millennium simulation. It's only one galaxy formation model in at the moment. What redshift do we want? Let's just take the Sloan medium redshift. Here are all the properties that the model produces. Let's take them all, but let's say we don't want that one for some reason. Okay, just go on to next. Okay, we'll build some galaxy magnitudes, some luminosities for these galaxies. You pick your stellar population synthesis model and your IMF. Let's take Conroy's. Let's take contribute to Alex. Let's take Sloan filters. Okay, we can add a dust model. We've only got one dust model here, but we'll be putting some others in. Let's not build an image at the moment. So how do you want to select that? Decide your fits, outputs, for example. Right, this is what you requested. There's errors because there's a couple of things I didn't put in. But you hit go. Actually, what I didn't put in was selection. So, and you hit go, right? And what it will do is send it off to the supercomputer at Swinburne. It will build this for you. It might take a few hours or it might take a few days, depending on how complicated your universe is. And you'll get an email when it's done. And when it's done, you can just come and pick it up by following the link. For example, here's some of the ones that I've done. Right, and you can just go download that data. Oh, there's much data in that one. Okay, so the neat thing though here is we have survey presets. So let's build gamma mock. Here we're building a light cone now. Right, so you have RA deck opening angles, some formatting squishing going on here, but redshift minimum and maximum, and so on. Right? So you see how this works. So what this interface does is it goes and constructs the SQL query behind the scenes. Sets up the supercomputing, goes and runs it, sends it back, sends you an email. Right? Teams can create accounts and build their mock catalogs, their official catalogs for the teams. They can build it for multiple simulations and multiple models. If you want to test theoretical uncertainty in certain scientific properties, for example, there's a whole host of ways you can use it. Here's a line that's generated. I didn't show you the mock image generation, but for example, you can build mock images in whichever frequency or wavelength you're interested in. So HST ones we build. So let me just finish up by saying the future. My vision for the future is really ultimately that you'll be able to build your own models, not just access other people's models, but be able to build your own models, and it will be descriptive. So in the same way that you can access these models by not having to program SQL, it's hopefully more intuitive. You can build new galaxy formation models by describing some kind of natural language interface where the code is generated behind the scenes for you. We're already there to do that. Not in astronomy, of course, because you don't have the resources of Google or Microsoft, but that can be done. That's already a solved problem. It could be deployed in field of science. What's really important is that we work with common data formats so that we can exchange our tools and our resources. Too many people are reinventing the wheel in their own particular corners because their particular needs are a bit different than somebody else's, and it's just easier for them to do that. We need to stop doing that, and one way to make it easy is to make sure we have common data formats. Same model on different simulations, different model on the same simulations. This is actually what I was saying before, that we, theoretically speaking, we need to test the uncertainties in the models. Right? Too often in the science paper you will just see one theoretical model compared against the data, and at some level that's almost meaningless because those models are complicated. You need to test a range of models, so you need to have a way to go and get a range of different models from the one place. And online natural galaxy formation modeling and transparency is key. So if you're interested, go to this URL and register, and you'll probably be accepted on Monday. And have a play, give us feedback. We're still in beta, and there's still things that don't work, it falls over. But let me just finish by thanking AAL and NECTA, especially the Australian government, for their wonderful funding.
to ask about the common format. You said, which one is it? Or how does it work?
There is no common format at the moment. That's the problem.
Okay.
We need
because as you mentioned at the very beginning, you can use like different data sets as a source, like from completely like.
Yeah, so we take care of it behind the scenes.
The compatibility is assured.
Well, what we do is we take the data from the teams, and then we convert it by working with those teams into something that will sit nicely in our databases, and then we just deliver it up with a well-described, in a well-described way, either in bits or VO table or just ASCII or however you want it. But in terms of people generating the data in particular, I think it's very important that we start agreeing with how things are ordered. You know, are they horizontal or are they vertical? That's confidence in itself. So it's very important. It's one of the big barriers that stop people working together.
So, you mentioned the Garbo efforts with stock data on from Millennium. Are there any VO protocols, the theory VO group, yes3, and stuff like that? Are any of them available through what you're producing here, or is the intent to put those in place at some future date?
So, have you ever felt the imposter syndrome? Right? So, there's a level of this which is I'm very unfamiliar with, and that kind of stuff. So my goal in doing this is to get these models out so that people can just click buttons and get data that they need in the simplest way possible. We do have requirements that they can put in. We're compliant with a lot of standards and so on, and the Intersect software team is making sure that we are. But I've been focusing on the models and the interface and the accesses. So I would say yes, but I can't give you any details.
Okay. Let me ask you a question. Ultimately, what we want to do is to observe your data and see if it looks like real world data.
Yep.
The trouble is the instrument we use to observe the real universe are imperfect. Besides, this comes to a shock to everybody. Telescopes aren't perfect actually, and they have bugs, and they have mistakes, and they have incompleteness, and all this sort of stuff. Is there any way we can simulate those observations on your data feed?
Yeah, so Tau 2.0, we're already starting to think about this, how we would do that. At the moment we don't, because we just wanted to get it working. But for example, in the image generation, there's so many options and parameters in the software package that we're using, which is SkyMapper, to simulate instrument noise, and there's a whole host of stuff that you don't have access to at all, right? So in the spirit of keeping it simple. But you could imagine advanced tabs or things flipping around, and then you do have access to more sophisticated tools. Or you could come in underneath through some kind of programming language and come through the back end and actually access those features directly, not going through.
Is that possible at the moment?
It is. Sorry. You can get access to the.
Are they engineers? I mean, how do you build a team to build something?
Good question. With money. You like do that when they appear. So the science team are all astronomers, and the technical team are actually Hassan is an astronomer who did his PhD in visualization. He has a software engineering background. Luke Hodkinson is a software engineer who used to work with particle physicists on similar kinds of things. He could almost get a PhD in astronomy now. He knows enough astronomy. Alistair Graham is more of a project manager. Again, he's a steep learning curve for him. Alistair Graham, sorry. But so there's a mix, and it's been fun. Scientists working with software engineers, and I'm sure there's been a lot of angst and frustration on both sides. But yeah, there's a culture. But essentially, we could, as astronomers, we could have never have done this. It just would not have been possible. You know, the idea that you get some smart grad students, and you can hack stuff together, but it just doesn't scale in the way that you want. It's not stable. You know, it's a whole host of issues. So basically, you have to pay people real money in order to do it. Essentially.
Probably just one more question, Mark. So George,
mine is a question. Mine's actually an answer to Matthew's question from about 2 comments back. TAP is one of the RBI protocols which has been implemented behind this in order to allow there may well be other IDI approaches.
Yeah, the tab stuff's working. It is working, but it hasn't been tested very much. So actually, it's one of the reasons why it's not been a tab is because...
Announce it to the VO and they will test it for your health.
Well, good. I mean, yeah, that's what we want. So we want to test it.
Okay, last question, George. No? Okay. All right, let's thank Darren very much. And so now that's the end of this morning session. We move on to this afternoon session, and I'm very pleased to welcome Yeshi Fenner of Astronomy Australia Limited, who's very kindly organised this afternoon session on cross-disciplinary connections. So all between astronomy and lots of guys and other fields. So, over to you, Yeshi.
Thanks, Ray. Yeah, so welcome to the cross-disciplinary connections component of this afternoon, which I think flows nicely actually from some of the talks that we heard this morning that touched on some of the other science sort of disciplines that are data intensive and have similar sorts of issues to us. In particular, I think Tony sort of really set the stage nicely when he described how various different disciplines, science and humanities, all different research disciplines are becoming so much more data intensive that new sort of ways of storing and managing and analysing data really need to be developed. And that has tended historically to be done in silos within each discipline. But it's really reached a point where it's clear that there's a lot of generic challenges among the disciplines, and again, I think Tony touched on that. And so, astronomy will have a lot of very IT savvy people, which is great, and so we've actually had a reputation for sort of being at the forefront of developing solutions to these sorts of data management problems, because we have to deal with very large data sets. We've got an IT provision community and a culture of openness and sharing, but other disciplines have been also facing the similar challenges and developing their own solutions. So there's a lot of opportunity for sort of cross-pollination and leveraging of other disciplines, ideas and approaches. So this afternoon we'll be listening to 4 non-astronomers who are going to tell us about their experiences within their various fields. And we'll start with John Zick, who's actually based here at CSIRO ICT Centre. He's a principal research scientist here. Yes. Oh, sorry.
Yeah, constant state of reorganisation.
Oh, no. And he'll be talking about his experiences deploying e-research tools and services here at CSIRO to support scientific collaboration. So, I'll pass it over to you, John.
Thank you. Okay, so this is a talk that follows up really nicely with this morning's presentations. So it's all about the sociology of work and sociology of science. Now, I think some people are familiar with this image. Essentially, Norris people are interested in this image because it's an observation of the sky done by the indigenous Australians thousands of years ago of the Great Indian. Just think about again what they were trying to do by these observations. They're not necessarily trying to predict how the stars were going to move, but there were stories around that Indian and where it came from. Similarly, we have the Chinese people going through and mapping this observationally, mapping the skies. Again, exchanging information, but perhaps not in the sorts of stories that the indigenous Australians did. Then some Greek dude a little while ago formulated, let's try and predict the motions of some of these interesting objects in the sky. All of you are familiar with this, so I'm just elaborating. What I'm trying to extract out of this introduction is that there is actually a particular sociology of work that is happening here. Okay, so how was the information exchanged in these models that were formulated? Okay, what was actually exchanged? It was between a small set of people. It took many years of observations and theories to be developed. Copernicus basically took the same observations, arguably the same sky, and developed a different model. Okay. So again, that revolutionized how things were predicted and what was seen in the sky. We've seen the constant evolution of basically observations and different frequencies, and I think somebody this morning said astronomers are unique, that they can differentiate according to wavelengths. Well, that's certainly happened with the introduction of Jansky's merry-go-round. We had, so this is getting now to giving us better images or different images of the sky, and that then opens up a whole new range of possible observations and validation of those observations. Of course, you need advanced sort of calculating power. So this is a little machine developed by CSIRO. I believe it was the 4th computer in the world, which was used for these astronomical problems.
The software engineers wear suits back
Only for photos. When they weren't, they were in overalls underneath. This was an early image from Chris Christensen, who I was fortunate to have as a lecturer at the university when he developed an image of the sun, the radio spectrum. Again, we're seeing the universe through different eyes. And I came into this sort of world in 1979 as my first job as a young engineer on Siding Springs, where of course, during the training exercises, you know, the astronomers, you go out and wander around and have a look at different telescopes and making sure the spectrographs are all working correctly and all a sophisticated computing device, PDP-8, onto, or a PDP-11, and onto a magnetic tape. And they could share this information. A little bit before that time, these people in the US decided it'd be fun to connect up some computers together in a network, a small network of 4 computers. University of California, Los Angeles, Berkeley, SRI, and Utah. That was this thing, the precursor to the internet. Again, what it was, enabling the sharing of information at a more rapid pace. So, again, if you looked at this is the current map, and this is the current map of the internet at the autonomous systems level. It's at the very highest sort of structural entity of the internet. You don't see individual machines here. What you're actually looking at is entire regions, like Sydney Basin and so on. So, you know, in the 1980s, we were in Australia still thinking about, well, internet, yeah, maybe this would be good. I think some of the community here were sort of interested in it. We had our own version, ACSNet, which was used for exchanging information once or twice a day between the various universities in Australia. Things have changed. I mean, the way that people exchange information, the amount of information that we're gathering, you all know this, so I'm preaching to the converted. You know, the compute power now is, you know, pretty silly, 10 teraflops, and that's the 5th fastest machine in the world, K computer, which I was fortunate enough to see in Kodak this year. You know, just compare the computational power that we've got on offer here compared to, you know, the PDP-11 with 8K memory, right? What you can do with this compared to that. So essentially, what I'm trying to progress here is this view that, sure, we've got this wonderful technology gathering underneath us. We've got this more powerful observations. We've got better telescopes. We've got better equipment. We've got more network connectivity. We've got better computational science happening. You know, so just to give you a point, the computer models are basically used to get prizes. Right. So, what are the challenges? I mean, what we've been hearing about a little bit this morning is that, you know, there are these technical challenges of exchanging information running a computation. So running a processing pipeline on a supercomputer is not necessarily the same as running it on a small laptop, or indeed on the same as a PDK. So you have these technical challenges, but actually, it's actually a little bit more subtle than that. Because these days, because we're actually exchanging information a lot more, basically taking responsibility for the data information and the curation of that information and so on, you've actually got all this other stuff sitting on top of it. Organizations, disciplines, groups, you name it, it's in there. And you have to factor this into any sort of work that you're going to do with it, collaborate. I mean, in the astronomy world, it may be relatively straightforward. In bioinformatics, these things get in the way significantly. Ultimately, you do still have, the one constant that we still have is that we're humans. There's humans involved. Humans doing what? Essentially in a social setting. So, just to give you a highlight again, some of the e-research technical challenges, and again, I know most of you are familiar across all of these. Computational science is being applied into many domains. Data challenges, again, how do I shift 15 petabytes of data to my supercomputer cluster across some other part of Australia? Well, you don't, is the answer. Advanced imaging, visualization, dynamics, all of this, again, is communicated here well across. So what I'm going to do now is sort of break into, well, what we have done inside CSIRO in bits and pieces of trying to address that. And so, again, this is from the IM&T point of view. Our Information Management Technology Group have provided some of the pieces of this puzzle, actually how we exchange information, how we curate information, how we provide facilities for people in the astronomy community and the other communities as well. One of the significant pieces of work that's been done is this data access portal, which is actually a web interface to a large repository of different types of information. So we've got pulsar observations, we have microscopy, and we also have sensor network information. All curated, all managed, permanently in storage for 10 plus years. If you have an issue with one of the things there, you go and talk to our IMT people and they'll help you fix it. We've got cloud computing facilities. Again, this has been properly managed and resourced. And this is the key. There was a joke here about how, again, we managed to put things, well, you actually need people involved in the support of the science. So, again, this is a bit of a sales pitch for the LMT guys, but really they are a very important part of this puzzle. Okay, so we've got our own GPU cluster. It used to be pretty good. As things progressed, of course, that no longer was the case. We're now 5th. We're the 260th in the top 500 and 10th in the green 500. We provide toolkits and services. So this is the Nectar toolkit to allow workflow to be created and managed. We have our own version, again, for image processing. We have our own workflow tool developed in-house and supported to allow people to actually connect up their workflows, processing pipelines. Okay, now at the highest level, that's what you'd like to see. Underneath that, of course, there's many levels down till you get to the infrastructure, to the iron, and you better have a complete mapping from here down to the bottom and consistent mapping because, for example, if you say, I want to create 1,000 pipelines now, please go, and run on my parallel computer, well, the results that you get out of this and the actual iron may actually be different because of essentially synchronization errors or workflow overflows or basically I/O bounds being exceeded. So there's still some work to be done in this. So I'll skip over these next parts, but essentially there are a group of people inside CSIRO dedicated to supporting the science that we do.
Can I ask a question?
Yeah.
This is a really important one, I guess, to scientists. I'm assuming you have that because it's written into that's
Yeah,
where
no,
we face a lot of these problems.
And it's again being highlighted in the discussions this morning, that basically you need to convince the government that this is important. You cannot progress the science without having the people to support you. I mean, sure, you can go and buy a big telescope and, you know, make some instrument and all the rest. You can buy the supercomputer part. That's not sufficient. It's not sufficient anymore. You cannot do this on your own. Okay? And the story that needs to be told is that, you know, you've got to have some successes. Okay? So if you can have some successes, then you've got a much more coherent way of going forward. And luckily, CSIRO has had some successes. We're working on some more projects that hopefully will directly inside astronomy that will have hopefully some successes there too. But I think that pointing decision makers that no longer is science done as a cottage industry, I'm sorry, you know, with a person sitting with a white lab coat behind a desk, you know, a la Copernicus and all these, but well, I don't have a white coat. Right. But the important thing is that it is the amount of information that we're dealing with, the quality of information. You know, you cannot have a cottage industry anymore. You've got to get out there and collaborate in all senses. In the astronomy peer-to-peer, in the verticals as well, okay, with the technical side. And having people embedded, okay, inside projects. So one of the things that we found inside these sorts of activities inside CSIRO, and I've sort of come to realise that, you know, you design, say, a repository. Okay, it's great, repository done, right? It's great. Oh, you want to access it programmatically. Okay, well, we'll get right back to that. But you need somebody to actually take that step and do the work, okay, and actually enable it. I hope that answers the question. So, again, support stuff, just actually, you know, library services, all things, you know. Actually, library services are getting cut all over the place. And this is really silly because where is the value for an organisation, a research organisation? It's in information. And who looks after information better than librarians? So, hands up to librarians. And again, one of the things I'd like to point out is that, yes, we have used this infrastructure, these bits and pieces of the puzzle in various domains. And we've had a few successes in various material sciences, bioinformatics, and so on. And I point you to the need to have that in place. Again, what is it about? These days, science is collaborative. It is about a group of people working together in a very intensive way to actually share information, do computation, and come up with the science results that you need. And this, of course, depends on the relationships that you build with your collaborators at the individual, organisational, specialisation, etc. levels. I'll give you an example here of my own experiences in dealing with, I guess, what you call the biosecurity community. Many years ago, I went down to Australian Animal Health Laboratories, which I'll speak about in a moment. But I asked them the question, so tell me, when you have an outbreak and you want to do a quick response to an outbreak, what do you do? Well, actually, we have a protocol in place. And this whiteboard picture, this group that is here, is the Consultative Committee on Emergency Animal Diseases, convenes. But there's a whole protocol between different organisations around it, okay, that basically locks these people up in a room for a week until they, or whatever time it takes, to basically debug what they're trying to fix. Debug, I mean, get rid of the viruses, attack the Hendra, come up with a plan of management for that outbreak. Okay, so there are these protocols established between these organisations already, okay, that should an incident occur, we know what to do. So, whoops. So here's, again, a bit of a dig down into that committee. It consists of, again, different internal organisations. So you've got the chief veterinary officers from each of the states, you've got industry representatives, a whole bunch of people coming together. And the way they do this right now, by the way, as I said, is that the meeting is called by the chief veterinary officer of Australia, gets approval through those various bodies outside, and they convene this meeting by locking people up into a room, which is not terribly nice. Okay, so in my dealings with these folk, originally we were doing inside the ICT centre, no longer this, inside the ICT centre, we were developing advanced collaboration systems in 2008. And we had this project between Defence Science Technology Organisation, NICTA and ourselves, looking at how people could actually collaborate in an intensive way as a group. So you have groups of people standing around these desks, systems, and face-to-face collaboration was enabled. And, well, as I said, we had wearing these bubble suits to actually access the instruments inside. Okay, I'm sorry, but standing around the table and doing all this wonderful gestural stuff, no, doesn't work. So, okay, so they said we like the idea of being able to somehow work with the people inside and operate the instruments inside while still being on the outside. And it'd be even better if we could do it by having, say, the Department of Agriculture in Queensland or the federal people being able to give them access as well. So we actually listened to them, and over the many years, actually a long time, and I'm sorry to be flogging this from the CSIRO people, but we developed this platform. And look, the important message is here that we listen to these people. This is how they work. These people on the inside of the screen here, on the inside of the screen, are sitting inside the containment facility, not with their bubble suits on, because where they're sitting like that, that's at level PC3. PC4 is the next one up. Now that's more dangerous again. But the way they work is, as you can see, they've got basically notes, books, they have instruments being displayed up on the screen there, so that's our confocal microscope actually sitting inside the facility, that the people on the outside can actually not only view in real time, but control. Fine. So this has been sort of a success story because we've managed to work out with them of what they wanted to achieve. So here's another way, and one of the interesting things with the system is, yes, some groups like to see this. Okay, they have the really personal interaction between people and data. Some people don't really care too much about the people and they just want to have more real estate for the data. Okay? And then finally, there's the people that just don't care about people at all. Which is, they're all focused just on the data. Okay? That's all they want. And maybe audio, okay, fine. But the ability to be able to swap between these different modes was absolutely critical in the way they work. We understood the social aspects of their work. And this is what the whole point of this talk is about. You have to understand how you're going to work together, what you're trying to do. Okay, so I have to wrap it up quickly. So here's our current systems installed. Okay, and this is sort of where these purple ones are outside CSIRO. They're the Departments of Agriculture, and the Queensland people use it pretty regularly, about once a year, when Hendra comes up to talk to our colleagues in Geelong. And the system is actually spreading. It's being enabling research across different organisations, different parts of the organisation, even across to the US and possibly Singapore. So, successful adoption of virtual laboratory type systems. Yes, you've got to have the good technology. Absolutely critical, right? I mean, I'm sorry, I'm a technology freak. I love technology. But you've also got to understand the relationships with the people and the technology that you're going to need. So, like this. Right, so right now, my current project inside CSIRO is looking at two specific use cases. One in astronomy land and one in biology. biologists are actually a continuation of the animal health laboratory work. Astronomers, well, we're working with pulsar group here. Again, the interesting thing is that we're merging together 4 different types of specialization inside CSIRO. Astronomers, biologists, computational informatics, me, and IIMT people. And finally, there is a related project that I won't have time to talk about. That's actually seeking to understand the relationships, the complex relationships between organisations and actually put in place authentication mechanisms to support that, which astronomers I don't think suffer from too much. Astronomy use case, again, I don't need to elaborate terribly on it, but essentially it is about connecting these various components, the data access repository, the demand scientific computing components, the instruments, and the workflow services together to suit a particular need. Okay, so, and the focus is, believe it or not, to maintain the good science and enable good science to occur. Similarly, for the biological instrument imaging use case, what we're actually doing is bringing together various components, confocal microscopes, workflow tools, etc., and trying to understand how complex organizational relationships work. So we've got some very good partners in this, IBM Research, Tennessee, etc. I point you as a wrap-up to this paper. This is a quote from the paper that really is, I can't emphasize enough. I'm happy to circulate. I mean, you should actually see it on the slides that will be available. But it's not just the technology, okay, is the message. It is about understanding how to work together. And that's not trivial. Thank you.
Sorry. Do you find that scientists, so I mean this challenge of knowing how to create a tool or a resource or something that scientists will use, right? Because if they don't use it, there's no value in it. How do you figure out what scientists want?
Okay, so
or is it only a process of elimination because they keep telling you what they don't?
Well, again, our own experience has been that by working closely, okay, as the technical people, so the technicians, working closely with the scientists, you produce a prototype. Again, say the biosecurity platform, that was we produced a prototype, we evaluated it, we ran it past many iterations, we incorporated features and feedback as they wanted. So it isn't necessarily a fast process, but basically having a tight coupling and doing proper evaluations on the quality of what is perceived by both ends.
So I thought I might just talk to the same comment a little bit, John, if that's all right. So some of the work that John just showed there was to do with the data access portal, and that's where we provide an archive of data from Parkes Radio Telescope for pulsar data. And we've worked very closely with another part of CSIRO, Information Management and Technology in particular. And the way that works is really that the science knowledge comes from here in astronomy and space science and really drives the requirements. But the project management and the technical aspects of it has come from IMT, and it's, as John says, it's that very close working together and managing to bridge the cultural divide that actually can become very successful. But the overhead up front is very high because it takes a long time to start understanding each other's language. But once you get through that, then you can become incredibly effective, I think.
But just to add to that, it actually has to be an ongoing engagement.
Yeah.
And as soon as you lose track of each other, sort of everybody goes off one way, and the IMT folks go another way because they found another.
Yeah.
So you actually need that continuous engagement. Absolutely right.
Hi. So I didn't know about the data access portal, but I would like to use it, which would be really cool. So we have like a catalog. So if you have a catalog of data and objects and payments and stuff, how would you go about, as part of CSIRO, uploading to that?
Okay, so you contact IMT, and say, we've got some information that we'd like to put into the repository, and they shall make it happen.
Is it object oriented? Like,
No.
How many petabytes can you take?
How much money have you got? I mean, seriously, that's what it comes down to, and that's one of the issues that the pass-up people find it. Oh, we need to put more stuff on. Okay. Pay as you go.
So for a few years, some of us have been experimenting using immersive virtual reality as a collaboration platform, and we found it to be remarkably effective considering the primitive state in which it's now. But if the technology is growing very rapidly, have you experimented with
Yes, we've actually got work happening at North Drive in basically another group, Thomas Pedmar's group, who's doing advanced collaboration for mining, I think. Certainly for visualization of astronomy and so on.
One last question.
Well, it seems like you put a lot of thought into fine-tune the solution for how easy is it to generalize what you're doing? Because otherwise it's not.
Okay, so can I just, I won't dismiss it, but I'll say I need to have 3 solid use cases before I generalize. Okay. So we need to go through the process. We've had one, okay, with the collaboration platform, and that's trivial because all it is just a shared workspace with some telepresence. There's nothing else than that. We're working on the second one, which is this virtual lab type services idea for the pulsar people, and the third one is going to be the imaging stuff for the microscope people. Once we have a feel for that, I think we'll be able to write papers and say, if you follow these steps, this is what the outcome will be. But until we've done it, I think that certainly the research program inside CSIRO is very, very keen to make these platforms generalizable across a lot of the CSIRO sites. And certainly components are, but again, it depends. I need to do at least 3.
Okay. Thanks again, John. So now we've got Stuart Minton, who's the Chief of Environmental Geoscience Division of Geoscience Australia within the Australian Government. This division is the custodian of national environmental geoscience data, information and knowledge.
Spent too long in public service and you lose the ability to dress casually. So, I'm actually a water scientist, which is why I put the word deluge in there flat, and I try and work it into all of my presentations. So, I thought to start with what I do is give you a very quick background video on Geoscience Australia and what we do, because in a new community like this you can be unaware of what happens. I want to talk about how I explain to ministers about big data. I'm going to talk about a specific case study, which is the Earth observation and Landsat data cube that we've been developing, and then challenges up for the future for our community. And I think you'll see some real parallels with some of the talks that have taken before around data cubing and virtual workflows and a whole bunch of interesting things. So without further ado, I'll just play this video. Hopefully give you a taste of the sort of data we deal with in geosciences.
We're looking at seismic work to determine the structure and ideally storage capacity of potential reservoirs for CO2.
We can pick up on things like vegetation communities that use groundwater.
We use airborne electromagnetic data, AEM data, to help us map near-surface variations in electrical conductivity. And from that we can infer a number of things, including the nature of the geology, but also the nature of the groundwater, the presence of saline groundwater versus fresh groundwater.
We also deploy seismic in the search for potential hydrocarbon resources, both onshore and offshore.
The geoseismologist analyses earthquakes as they come in, and they're required to alert on those earthquakes within 10 minutes, and we issue tsunami warning
buildings based on that earthquake advice.
We also acquire MODIS and ABHRR data, which we process on a daily basis to extract hotspot information, which provides indication of potential where there could be fires in the landscape.
We're collating flood studies and satellite information into one spot so that we can actually have a look at the place and see over time what's happened there in terms of flooding.
And this gives us a really good understanding about how things have changed in the past and gives us some really good foresight as to how things may change in the future.
Australia happens to be in a hotspot with these augmentations. When they become available, you're going to see sufficient satellites to get really good positioning, even in the middle of high-rise CBDs.
We hope to be able to deliver a product that will enable users to position their mobile phones to around 2 centimetres. So we're taking its scientific infrastructure and making it available to the general public.
The ability for people to access remote sensing product through their mobile phone has effectively transformed expectations from the public about the access to environmental information from remote sensing.
We track GNSS satellites, we track remote sensing satellites, bring data back from remote observatories, including observatories in the South Pacific and Antarctica. It then goes to the international community where it's used for a whole range of things.
We have a growing archive of over 30 years.
30 years ago, it was a difficult task to process one satellite image. Now we can process tens of thousands in a day potentially.
And with the launch of Landsat 8 now, we've got a continuation of that.
I can look at one spot and I can say, find the water, go all the way back through time, and I can do it for all of Australia in one go. We've taken all of our imagery right through our entire archive, and we've made it available in a constant, accessible way.
In future, I think it would be really exciting to integrate new satellite sensors and to use methods of data interoperability to look at the landscape in new ways.
Now that we're actually working in a supercomputing environment, we're enabled to include other agencies all around the world in collaborative environments. That means a lot more accessibility of data, a lot faster outputs, and a lot broader impact of what we do.
In the next 5 years or so, there are going to be some amazing satellites.
It used to be the domain of scientists and technical specialists only to make use of this information. But the combination of satellite remote sensing and high-performance computing is transforming our ability to make use of the information that we collect from satellites.
So that hopefully gives you a taste for what Geoscience is doing, Geoscience Australia is doing in the data realm. So I just wanted to give you, and this is old news for you guys, but I found this really useful in explaining to ministers in really simple terms how big data we're talking about is. So how big is big? This is what I used to explain in the past. You take something like the US Library of Congress, which is a wonderful facility with most of the written works of mankind in it. If you digitise the text in that library and burn it to disk, it's about 10 terabytes. Right? So they go, ooh, well, that sounds big. And then you go, well, what's a petabyte? It's 1,000 of them. Okay, so if you burn a petabyte to CD-ROM, and you actually start stacking the CD-ROMs up in a stack, it's taller than Mount Everest. Okay? You start talking, how many Mount Everests do we need to fund, Minister? And they start actually getting that it's a big issue, and it's not simple anymore. So it's just a little aside. We've had a few ministers go, oh wow, when you tell them that. When you talk petabyte, they don't understand what you're talking about. So Everest of data. All right, an example. This is how we are tackling the Earth observation challenge and how the size of the data that we're dealing with is changing our perspective on how we deliver that data. I'm turning you all 180 degrees now. You guys are used to standing on the Earth and looking up, right? We're now talking about floating cameras in space and looking down, effectively. Earth observation satellites all over surround the planet. They take photographs of the surface of the Earth. They're not just photos, though. Of course, they're depending on whether it's a hyperspectral satellite or a multispectral satellite, you're talking about measurements in the various bands that are depending on the actual instrument. In the case of Landsat, each scene is about a CD-ROM size. We've been taking these photos of the Earth over many years, and we've been dutifully archiving them away in a hierarchical storage system on tape, because we can't afford the petabytes of spinning disk, and that's served us pretty well for a number of years, because most people were interested in the latest scenes, they weren't interested in the deep archive. And we've built our whole processing chain around this process. So let me take you through how almost all Earth observation science teams in the world currently do their work. Right? They have a client that's interested in a product. Tell me about something on the face of the planet. We then ask the client to identify the footprint in space or time that they're interested in. It's simple. I'm interested in Tasmania this year. We then sit down and start working out what we've got in the archive or in the hierarchical storage that actually matches that time and space footprint. Then we send off a very frazzled robot to extract the scene. The reason he's looking very frazzled is because it takes a long time, and we've got more than a petabyte in storage in the basement of GA on tape robot. On average, the poor little robot has to go and find the tape, load the tape, spin up the tape to the right part, extract the scene, put it onto disk, put the tape back, go and get the next scene. So if you're talking lots of scenes, it averages about half an hour a scene by the time you've actually extracted it from the tape archive. It puts all these scenes, which are effectively just photographs, just the raw data, uncorrected, uncalibrated, onto a disk, and then we set a team of people onto auto-rectifying it, because many of the scene, if you're looking at the edge of a scene, you're looking through a lot more atmosphere than the centre of a scene. If you've got cloud masking, everyone's excited about clouds, we don't like them, can't see anything under them. Atmospheric correction, mosaicing, all the standard kind of stuff you do before you get to do the fun stuff, which is the science, where you do feature extraction, looking for patterns or trees or spectral unmixing, looking at algal blooms or bathymetry, extracting electrical satellites. So this is the fun stuff, but you've got to do a hell of a lot of work before you get to it. And then you produce a product. The problem is then the client says, oh, actually I was interested in the bit next door, can you give me that? Right? Or they say, oh, well, I'm not sure about this algorithm, can we run it all through again with a different one? Right? And you start the whole process again. This takes a long time, and if you're taking lots of scenes out, it's a very labour intensive, and this is what the cycle we've been in for many years. So at Geoscience Australia, what we thought is, can we actually arrange the data in a different way so that we can actually shortcut all of this process and get right to the interesting stuff? And that's where we have.
Last question before we move on.
Sure.
Does the client always ask the right question? Something like,
no. Almost inevitably.
It sounds to me like they're asking for a map. Actually, what they wanted was the answer to a question.
Yeah.
What goes here? Because even if they'd actually asked you the question, then you may have got the right answer.
Possibly, but often you learn a lot through what you observe as well, and that adjusts the question that they're asking. And so it's not always as simple as that. But having to run through this process, there are whole teams of people in these remote sensing science centres that just do all of this bit. Right? The interesting bit, which we'd all like to work on, is to actually extract something useful from that data, not to do all the recalibration, etc. So what we've done in GA is create a data cube out of the Landsat data. And to give you an example of the size of it, I mean, the Landsat pixel is 25 metres in resolution. So to cover Australia, you're talking about 191,000 pixels that way by 149,000 that way, 575 months of data by 7 spectral bands. So it's about a petabyte of data cube. What we've done is put this all on spinning disk deliberately because we don't know exactly how we want to look at it. The other thing we've done is made sure we've done all that pre-correction, calibration, auto-rectification location. So you can actually line up any one pixel in the scene, and you can look right back through time for the entire 40 years, and you're looking at exactly the same part of Australia. Right? So we've done all line, and we can actually be confident that you're looking at the same place. It's a lot harder than it seems, because while this looks very idealised, that's not how the data is. The data is actually in these individual strips of satellite imagery that go across. Some of them have clouds in them. What you've actually got to do is align them all to the consent. So it's great, but any one pixel might be a very edge pixel on one scene, it might be a centre pixel on another, it might be cloud mask on the next, etc. And you've got to actually extract all of that data, and you've got to start thinking about pixel-based quality, because when we've done metadata about these scenes in their collection, we've given the metadata on the basis of the whole scene. You know, it's 70% cloud code. Well, that's a useless scene, except if you're interested in the 30% that's not cloud code. Right? So actually, you've got to be able to deliver the data with pixel-based quality. This, once it's all stacked, and we have done that for the Landsat archive now, you can do some amazing things. But what we're effectively doing is pre-packaging all of this work. So we're getting straight on to being able to run this kind of stuff across the whole archive, both in space and time. So here's an example. This is the first one that we did when we built the first 15 years of the data here. So this is an area of New South Wales, the Menindee Lakes, Broken Hills up here. This is the Darling River running down. This is a series of lakes that are important for Broken Hills water supply. In this example, what we did is we just took 4,000 by 4,000 pixels, and we looked through 15 years of time, and we're looking for the water footprint. Right? So using the spectral bands for water, picking up the water signature. To do this analysis, if we did it the traditional way, would have been 1,200 individual scenes extracted from the archive, so a few weeks of the tape archive wearing away to actually get the scenes out and in place. What you'll see here is the progress as we move through time from 1998 to 2012 with the drought, and you'll see that these lakes are gradually drying up. So you can actually pick out the areas that are only rarely inundated and the areas that are always inundated from that kind of analysis. Now, I mentioned that 1,200 scenes would have taken us weeks to extract that data. Because we've got the data already arranged in the data cube and it's sitting at our National Supercomputer Centre, the NCI in Canberra, this analysis took 15 minutes. So it was bang in the parameters, thank you very much, runs it over 4,000 pixels either way, and it doesn't really care that the data came from 1,200 individual scenes because the data's already arranged in an agnostic form. Sorry, before I move on to the next one, I'll just mention, until 4 years ago, we used to sell the Landsat data. Right? It used to cost you $1,000 a scene. So that analysis would have cost you $1.2 million. Took 15 minutes. I wish we were paid like that now. But, all right, so take that example and do it for the whole continent. So that's what we did next. We said, okay, we've proved that we can do it over a little area. Let's run it over the whole continent. So in this case, we're looking at 15 years of data, 25 metre pixel resolution across the whole of the Australian continent. We accessed 133,000 individual source scenes to do this. 21 by 10 to the 12 pixels visited by the algorithm as it went through. And to run that took us 2 days at the NCI. Now I can tell you, apart from, you can do the sums, $133 million that would have cost us to get the data originally, just to get that amount of data out of the tape archive, even if we could store it anywhere, it would take 8 years. Okay? And we're able to do that in 2 days. The reality of how we've been working previously is we couldn't do it in 8 years. Effectively, you'd have to extract small bits, run that through the algorithm, extract another small bit, run that through the algorithm, at the end of the day, tie the product together. So you get to the end of that process and go, well, that's not quite right. We need to run a different algorithm and start another 8-year process again. Right? We're able to run that algorithm over a 2-week period 6 times. Right? So that's equivalent to running 8 years of work, starting from scratch, 8 years again, and learning from that process. So we've just accelerated the innovation process. enormous amount. So it's truly incredible in terms of what it's able to do. Here's another example. This is a time series of vegetation in a Queensland farming area. What you're looking at here, green is green crops, red is bare soil, and blue is dry crops or cured crops. And you can see as we progress through time, you can actually track for the whole period of time when that field is being cropped, when it's being harvested, when it's being fallowed, and you can look at that over 40 years at a field scale. So the potential for using this to crop forecasting, to look at accounting for what we think is going to happen this year, given the history of what's...
Are there privacy concerns with this?
There may be, but the data's already freely available.
For insurance reasons, for example.
Yeah. Well, yes and no. Perhaps I'll take that at the end because there's a few nuances there. So there's a good example of using the cube for cropping. What have we already identified things for use as? Vegetation change in the Murray-Darling Basin. So we've already done a little project for the Murray-Darling Basin Authority looking at the response of vegetation to environmental watering events. When they put water down the river, what happens? Does it make shallow water bathymetry? We can run algorithms to detect the strip of coast that we don't know, which is the sub 30 metre portion between the shore and 30 metres. Nationally, we've got a gap, effectively, we don't know what's there. Land cover mapping and change detection. And importantly, just as an aside, because we've actually arranged this in a cube now, you can actually deliver just the pixels of interest. You don't have to deliver a scene. If I want to download Landsat data on my mobile phone at the moment, I've got to download a gigabyte of Little Searcher to a model of co-located data with federated custodianship. We all put the data into a supercomputer centre or somewhere equivalent, and we bring the users to the data. It's too big to move around anymore. We just can't do it. And we're arguing within government that this is our telescope, the environmental community. Right? We need to put all the data in one place, and we need to be building the models and tools on top of that, rather than the current paradigm, which is I'll hang on to my little bit of data and I'll give it to you if you convince me to. Right? And when you talk big data, you just can't do that anymore. It won't be on the network. It's got some other advantages. Data's getting too big to move, of course. When we add data, we improve all the products. You guys know this, you've been doing it for a while, but I can tell you in the environmental community, this is heresy. Really difficult. Computing can be next to the data. We all benefit from each other's investments. We can integrate remote sensing in situ and model data and services. People can value add without the overheads of that entire chain we've got to run through. We can share common workflow environments for modelling and analysis. So there's some real benefits there. I just want to end with one little taste, which is, you saw the bushfire stuff that we have in the, we run a national bushfire monitoring system. This is a great example, not very useful though, because we only get updates a couple of times a day at the moment from satellites. But there's a new satellite going up in about 18 months' time, Himawari 8, a weather satellite. It's going to give us 10-minute updates, which will turn that tool into a real-time situational awareness tool that will assist people in deciding whether to run from their house or drive down that road or that road, right? Total game changer. 2 terabytes a day of data today. How do we deal with it? And how do we make it useful? We're arguing, well, that just slots into the data cube, right? So it's just a new layer, and all of your tools benefit from the update. So if we've got that paradigm and it's not going off to a disk somewhere in deep archive, then we can actually turn these things into really useful things. And just to end, this community, our community, just really doesn't know what's about to hit it, because in terms of Everest of data, we've got a lot on the way. So are we ready? No, we're not. Thank you. Questions? Perhaps I could follow up on that question Look, it's a really interesting question. The reality is that there have been, you've seen the Google Street Map and that sort of thing, those things have come up. At the resolution this is at, it's not, it hasn't come because of 25-metre resolution, you're not looking at individuals. What you're measuring is change in the landscape, and that's viewed as an item of public interest, regardless of whether you're, if you're stealing water, for example, so you can pick out the fields that have been irrigated very clearly, right? And if there's no irrigation right on that farm, then that sort of thing is possible, absolutely. There are people looking right now at the provenance issues around the legality of using satellite imagery to prosecute people, because it's been challenged in the past on the basis of no continuity of custodianship all the way through the chain. Can you make sure that nobody's got in there and fiddled with the data along the way? So there's still some legal challenges around all that, but we're viewing that as stuff to be sorted out down the track. This is too useful to let that lie on the basis of maybe someone will get wrong.
Oh, sorry. Brian.
How do you limit access to the data right now? Because
where we have collaborators, so at the moment we're opening it up to CSIRO from GA, and we're aiming to expand that to a broader group of scientists. And we're going to have, we've separated different, everyone can have read-only access. Some people can go full with the contents, but we're trying to sort through the governance of that right now.
If you have like an allocation system,
oh yes,
if you have a bunch of people wanting to go use it,
that's right. So it's currently the processing across the whole queue is scheduled in that way. So it's not a delivery mechanism that we just open up to everyone. We do have delivery services sitting on top of that in virtual infrastructure, so that we can spin up the service to allow access to individual packets of the data. But the processing of the whole queue is something that's tightly scheduled. But we are, I'm sorry, I should add, we are thinking about how do we scale this in terms of, if we're currently using Landsat, which is free to air, but there are a number of companies interested in looking into that and selling value-added, finer resolution data, and they may set up queued infrastructure next to ours that's linked in that way. So researchers might make use of the public queue, and if you want to run an algorithm for commercial gain, you spin off to the cloud or some other infrastructure that's built nearby.
So I guess I had more of a practical question for you. Your data structures are very, very similar to the kinds of things that we deal with in astronomy in terms of data cubes. Your multi-dimensional data is analogous to the kind of spectral data that we have, and of course you have time sequences as well. What specific data formats do you use, and what kinds of archives backends do you use?
We're mainly using NetCDF at the moment as our storage container. I'm not the right person to ask. Leslie Whitehorn, who's not here, but tries to play a role linking these various communities, is right on top of all that detail. But we're settling the environmental communities gradually gravitating towards NetCDF as a generic kind of tool set and a standard for container storage in that sense. What we have got away from, we're using the database almost as we're structuring the data in relatively small blocks, but in an interface where the database that allows you to run across that just interacts with each of those individual blocks. Sorry, I can't. I can certainly follow up if there's detail.
Well, there's, as you probably know, the SkyMapper project, which is the database, which also lives in NCI. So, I think there's a lot of commonality.
Well, perhaps if I can make a link to the previous talk, one of the crucial elements here has been the interaction between our staff in the geosciences and the staff at the NCI, who are playing a real brokering role and helping us deal with these kind of things. And CSIRO has been a key partner as well in the informatics space, allowing us to bridge those things, because we are dealing with a new domain, you know, in that sense. And I can tell you, it's hard to explain to people what the benefit of this is until they actually see the numbers and they start going, oh, that project that would have cost us $1 billion and taken 10 years, we just did it in 3 days. Well, that's sellable to government.
The way that we've changed the process is really how you serve that.
Yep.
So I think that sort of gives you maybe some hope as far as wider adoption and understanding, because it is a simpler data product that you're giving to people.
Yeah, look, I think that's true. I mean, what we've done is we've moved the whole remote sensing imagery has been a paradigm of scenes. Right? They think that everything is a scene. It's primarily, I think, driven because the remote sensing community has primarily been propped up by defence over many years. And for a defence use of remote sensing, they want to look at a picture and see if there's a tank rolling across the road. The value becomes immediately visual, right? What Landsat's done over many years and similar missions have actually got a lot more spectral measurements out of that. And what we're trying to do is abstract those so that they're scene independent and sensor independent. So build them into a cube that is actually a representation of a measurement at this point on the planet, as opposed to extracted from this sensor and has to go through all this. So there'll be different approaches and better ways of actually abstracting it over time, but rather than waiting for the perfect one, we thought we'd jump in and give it a go, and then we'll learn from that, and we'll go through and we'll reanalyse and come up with better versions down the track. On other kind of types of data, I mean, we are building a radar cube at the moment, based on some of the radar satellites. So we don't envisage that one cube will do everything, right? And we're also building we're actively working on a process to get point data into the cube, so things like LiDAR and individual point measurements, LiDAR clouds and radar clouds into a cube infrastructure in the same paradigm. So we're still a long way. I mean, we started this project back in May, right? So we've got a long way already. We're pretty happy with the progress we're making, but there's a long way to go yet.
Let's follow up on a throwaway comment you made. One of the motivations for this conference is the feeling that maybe we're inventing the same wheel in astrophysics as you guys are in geophysics and other people in biology, whatever. And are we learning from each other enough? And you made the comment that NCI acting as brokers for techniques. Is that sufficient? So, how effective are they? Do we need more than that? And if so, how?
Well, it's certainly been very effective for us in that what we're having to do to move into the supercomputing environment is think a lot more abstract, in a much more abstract domain, and that forces you to actually step back a little bit. And in our domain stovepipes, we have our favourite data formats and our favourite tools and whatnot, but in order to move into actually making use of it in a supercomputing environment where you may want to run things in parallel forms or whatever, we're having to step back a little bit and say, well, actually, a good example, bathymetry data and elevation data is actually the same stuff. It's just some of it's wet and some of it's dry. But do you think those two communities have anything to do with each other or any common tools? No, right? So we're actively moving to, and Geoscience Australia with ANZLIC, our National Land Information Council, has got a common data theme now for bathymetry and elevation. We're actively working to put those together. It's only through the interaction of those people that sit between the hard computing and the science that can actually translate one community to another. We need to invest in them, absolutely. Whether they be sitting with us, people that are scientists that talk, computational science, or whether they're sitting at NCI and hard computational science, that'll
exactly is, so you mentioned the end-trip results, which have taken 8 years to go and get the things off tape, presumably. So how many petabytes, gigabytes, or whatever is that, and you put it on hard disk?
Yes. So that's about a petabyte.
Okay, and then you have some sort of relational database for the metadata?
Yes.
Which goes then to the files?
Yes.
And then
Which
you
are in
preload
this,
that so you don't have to access it with SQL?
That's right. So it allows you to run, because you could actually store the data in more optimized ways for particular queries. So if you wanted to only do spatial queries, then you'd subset the data in little bits of space, you know, and be really quick for spatial queries. But if you only want to do temporal queries, and so we're going to have to come down a lot further. But we're building a nesting grid specification that allows you to align any bit on the planet with through time and space that deals with dynamic data moves, the movement of the continent, and changing land surface shapes that allows you to keep referring the imagery that you're taking, which is very well positioned by GPS and everything else. It's greatly positioned, but actually then lining it up to say that we're looking at the same bit of the Earth is actually really quite difficult. That's half of the challenge.
So there'll be, I guess, more opportunities for questions later on during the panel discussion and also over afternoon tea. So I guess since we're running a bit over time, we should probably break. And I'm not sure what time we should have that break.
I'm not sure.
Oh,
That's it. No.
okay.
We're having a group photo, so can you get out there?
That's caused by the resolution of the UV and then we're trying to do like one spectral analysis. You copy it, shock the problem, and in astronomy, you guys do too. Right now, we have essentially it'd be like us bidding everything in the blocks like that. And you should be able to make it easily one year. These are low-level satellites. What's a geosync?
Landsat's maximum resolution is 120.
That's clearly a decision on that based on cost of sensor as opposed to any
I think some of the
and then
what we are doing is trying to
Хочешь имя подать вычислитель разных зон?
we need to go
haven't got my own. I think this one is spare. Pardon?
Do you have anybody in your link?
Yeah, we have some people watching this. Yeah. It's just up there on YouTube.
Oh, YouTube?
Yeah. So you can go to it. At the top of the program, there's a link to it. Don't be scared.
Yeah, it's a bit scary.
Well, pretend you don't know.
Okay.
I agree. I was
Just before we start the afternoon session, I'll just make a quick health and safety announcement. There's one of you may have found it's really easy to get your arm caught in the tables on these chairs. When you close the table, just keep your arm well away from them. There we go. Okay, really are.
We have an eye to left light on the pinch point. Use your left arm.
Alright, well, welcome back. We've just switched the order of the next two speakers. So we're going to hear next from Jonathan Hodge, who's the Deputy Director of the Australian Coastal Ecosystems Facility at CSIRO up in Brisbane. So his background is marine science, environmental information systems, data management, data visualization and project management. And he leads a number of projects that are using linked open data concepts and online technologies to progress environmental science. So take it away, Jonathan.
Thank you. I sit within CSIRO Land and Water, within the Environmental Information Systems Group, which has got a collection of people in Canberra, Brisbane and Melbourne. And a lot of what we try to do is to try and bring together coastal information and environmental information and make it more accessible and usable and discoverable. And when I'm talking about coastal information, the question was asked before around a single data product. What I'm talking about is a huge number of different data products. In the coastal space, unfortunately, anyone who can get to the coast can go and do some monitoring, water quality monitoring, seagrass, whatever it might be. In the ocean space, I assume in the astronomy space and in the satellite space, you need a big bit of kit to go and measure things. So in the coastal space, unfortunately, it's very easy to get to, and there is every range of organisations, from community groups through to federal government agencies and research organisations, all monitoring in their own way and all storing and collecting their data. And also onto some of the more recent projects we're working on, projects like e-reefs, and really where we're seeing the evolution of data interoperability and the information space. So in Australia, in the environmental space in Australia, there's been, as I said, a huge number of organisations collecting environmental information. Every university, every state government, federal government, local council, regional body, catchment group, take your pick. They've all got some interest in the coastal space, and there's information being collected on all sorts of things. A lot of the government organisations, at least, have been very risk averse and very slow to adopt technologies. So it's been a
very gradual process in getting out of their internal silos out into sharing information. But there's been a really big push towards Creative Commons licensing in the last few years, and a lot of that's been led out of Queensland, and we now have Creative Commons Australia through the Ausgol project, which is the Australian Government Open Access Licensing Framework, which has been mandated at the federal level now that all publicly funded data should be released under open licenses. And that's slowly happening and is being replicated at the state government levels as well. And we've had lots of investments in all sorts of different environmental information projects. We've got the Terrestrial Ecosystems Research Network, Atlas of Living Australia, things like the Australian Ocean Data Network, and IMOS, which is the Integrated Marine Observing System. Lots of big activities to improve how we collect and deliver data. Most of these tend to use pretty standard services. Open Geospatial Consortium defines a whole heap of ways of delivering data, and there's standards for map services and catalogue services, feature services, all sorts of different ways to deliver a range of data types. At the moment, a lot of the metadata and catalogue services are pretty common, but some of the more complex ones are a little bit less common. When I'm talking about metadata, I think it's a little bit different from what was mentioned before around metadata that was mentioned before, around 300 flags per pixel. Our metadata is at a catalogue level, single metadata record for an entire data set. So there might be one catalogue record for tools that aren't connected or interrelated. They cross over between a few different environmental domains, and the ocean space and coastal space tend to be a little bit separated at times, and the terrestrial ocean and coastal are all quite separate. Occasionally we have some systems that bring some of this together, and the Australian Ocean Data Network is one example, which is really providing a connection point for a range of catalogue and map services so that people can start to trace down and find different data sets. So we're starting to get these up here. The problem though is that these services these systems aren't connected to other systems. So we don't have a lot of connection between maybe a terrestrial system and an ocean system, even though a lot of the data is used by the same scientists, same researchers for topics that cross over. Coastal space is a key area where this crosses over, and there's been this traditional terrestrial and oceanographic divide, and a lot of people have just kind of left the coasts in the middle. So, as I said, there's a few different areas where there's been significant investment in the environmental and earth science space. TERN is one of those, IMOS in the ocean space, Atlas of Living Australia for biodiversity information. That's got quite a good public profile now, and there's a lot of use from the general public as well as quite a good citizen science volunteer portal, and the Ausgol project in the earth science space. So these are all large nationally funded activities that are bringing together data in a number of domains. So I'll talk a little bit about TERN. TERN is really focusing on building the infrastructure and the networks to make data more available and more accessible, as is setting up systems to store or to hold long-term collections and storage of information. A little bit similar to what we've heard before around making data accessible and available using some of the similar kind of services and systems that others have talked about. One of the maybe the slight differences in the coastal and ecosystem space is that some of our key clients are policy and management. I'm making a guess, but perhaps in the astronomy space, the immediate clients aren't the policy and management level. We're quite often reporting directly to ministers, directly to decision makers who are trying to use information and get better information, literally to have a button to manage something. They want to manage the reef. They want to manage they want a report card that uses the data and gives them answers. So there's a very real connection, and unfortunately, if we don't have the systems to deliver to policy and management, quite often they'll just use whatever they can get at hand, which may not be Turn is really about building both physical networks but also human networks. It's about connecting scientists, connecting scientists to management, and using data to achieve that. And really trying to improve the community and improve the understanding of how to use information and what we can do with services. But also to achieve some of the things that Stuart was talking about, and the ability to answer really serious questions or ask serious questions of our ecosystem data. And once we get it into somewhere that's accessible and usable, we can start to tackle some really interesting problems and cross domains and start looking at issues of climate change and really long-term patterns. So Turn's been funded by the Australian government through all of the buckets of money that lots of people are probably familiar with through NCRIS, EIF. There was a small bucket through CRIS, and now through NCRIS 2, which is the latest round. And it tackles everything from the instrument and sensor level, and that can be people out in the field taking vegetation measurements, to large arrays measuring flux, carbon flux from forests, through to data from satellites as well. It defines a whole heap of standard methods for field data collection, trying to fix some of the problems around the diversity of methods that are used. But it also gets into the processing and analysis side, and of course the data storage, data curation, data sharing. So there's a whole swag of processes that have been put in place to improve data storage and data sharing. That then of course enables much better cross-domain usage and into modelling and analysis and synthesis, and ultimately policy and management. So really Turn's trying to tackle all of those areas. One of the ways that this has been done is through trying to educate the ecosystem community about data sharing. So we've had a push for Creative Commons licensing. Depending on the domain, that's been accepted or not. Some areas have been very reluctant to release information, and that's been a very gradual process to educate different groups. But things like embargoes on information or data release, having a 2-year period so that people can publish, and there's lots of ways to work around that. We've heard similar things before. So Turn actually came up with its own set of licenses, which are based around the Creative Commons licenses. The reason for this is that there's certain interpretations of the licenses that mean some types of data and some types of information aren't subject to copyright and therefore can't be licensed by the standard Creative Commons license. Creative Commons is part of that suite as well. So through Turn, we can license data either under the Turn licenses or under Creative Commons licensing. Something that has been a little newer and is solving some of the issues around licensing is around data citation. And it's now possible to get a digital object identifier, a DOI for data, traceable, citable, referenceable URI essentially to attach to data so that people can actually get attribution and get recognition. So this is starting to get used a bit, and people are starting to see that by putting a DOI on their data, they can actually start to put that in their reports around citation history. So that's definitely starting to take hold in the ecosystem community. So Turn offers a DOI minting service, which is offered through the Australian National Data Service, who do it through Datasite, which is the international organisation for data citation. Turn itself then is a collection of different facilities which cover a whole range of information, from biophysical data to ecological data to the processing and analysis and synthesis. So the coastal information sits in that top group in the coastal ecosystems facility, but other things are tackling, as I said before, flux towers in forests. AusCover looks at land use and satellite type information. Soil data, multi-scale plot network is around long-term ecological monitoring systems where it's established methods for monitoring vegetation and all sorts of things in what we call super sites around Australia. So each facility focuses on a particular domain, and they all connect together through a number of overarching facilities which try to bring together the integration between all of the components. So coastal facility tackles a number of elements primarily around water quality and coastal habitats, but is really providing a whole heap of services and servers to allow people to contribute information. We use a whole swag of mostly open source solutions, which are sitting on both CSIRO infrastructure and Nectar, the National Research Cloud infrastructure. Lots of websites, portals, services. Most importantly, the most important bit is web services. It's all about providing service-based access for interoperability. The big issue, though, is that TERN is just one community. And there's a whole heap of communities that we need to deliver coastal information to, whether it's for climate change, for ocean research, for terrestrial research. Coasts really need to cut across a whole heap of areas. So in order to do that, we need better discoverability. So if we think about what we understand as discoverability already, we need to think about what do we expect out of something like the internet. And with websites right now, we can pretty much go and search for anything we want, in the format we want, and get any price, any phone number, any bit of information we want, and traverse from website to website very, very quickly. So why don't we do that with data? We need to be able to get to the same point. In general, it's not available in the same way. It's not available in the same formats, the formats we want. It's very hard to search for. It might not exist. It's probably not up to date. So we need to bridge the gaps between what the internet is capable of right now and how we deliver data. To do that, we need to build a bit of a structured approach to discovery and interoperability. And we need to be able to ask a whole heap of questions of the data that we want to find. And most importantly, we need to be able to get the answers to that consistently. We need to be able to ask the same question of different data repositories and get a consistent answer from them. And this then crosses over into concepts of linked open data. People like Tim Berners-Lee are working very heavily in the open data space around trying to get data structured in a way that it works in the same way that the internet does for what we know right now for words, pictures and video. So there's concepts of what is good linked data. And there's a concept of 5-star open data, which moves from a single star, which is get your stuff on the internet, and it's available. It doesn't matter what format it is, just get it out, but license it. The next level is making it accessible in some sort of structured format. It could be as simple as an Excel file. The next one is to get away from proprietary formats and to make it openly accessible. To start to use URIs, consistent, unchanging URIs, so that you can always go back and find the same information, and ultimately to link data to other content. And this is what is linked open data. So at this point I'll introduce our eReefs project, which is about linking a whole heap of different types of data, modelling information, satellite remote sensing, continuous water quality data where there's real-time data coming back from probes out in the water, spatial information, all sorts of things. And it's about building an interoperable platform to support all of this. So to do this, we need to build a structure for our data providers to contribute information. So we already have, as we saw before from TERN and similar projects, we've got data and metadata services, and these are pretty well established. We've got standards for these. But there's also a whole heap of other things that we need to make sense of that, like vocabularies and provenance services. And so that we can start to track from one data set to another, we know where a model was run and what data we need to it, and start to actually trace through and link through things. But in order to have all of these sitting side by side and linked to each other, we need something over the top that basically gives a hierarchy to these systems. So we should be able to start from a vocabulary term and say, what does this relate to? Go up one level, come down to a data service, track back over again to a metadata service, or link over through to the provenance information. So by building this hierarchy, we can start to link these data provider nodes together and start to make things properly discoverable. So in doing this, there's a very the start of an ontology around describing what a data provider is, what a data set is under that, the services that belong to that, and all the other information that sit with it. And importantly, it also sits alongside, there might be a website for the data, so we need to incorporate elements that already exist on the internet, like traditional websites, alongside our data services. So in doing this, we can then start to set some rules around how to access that. And this will make a little bit more sense in a second. But essentially, we can start to come up with some conventions around how to access a data set or a metadata record based on what to put in the URL or what to put in the URI. There's components, and you can go and edit the components that are linked. And essentially, it's a collection of redirects. It's actually not too complex, but it provides a mechanism of providing signposts to information. So we might end up with a server, some hideous URL like that, which really should look something more like that in the future, so that we get away from these terrible server endpoints, and it should be a much more generic URI. We're getting to this point. We've now got permission to use the data.gov.au namespace, and this is where we'll be sitting a lot of our information. For now, though, we use terrible URLs. But you should be able to go to that URL and say, give me the data for that code, it's a data set, give me the data. Instead of finding whatever the actual data service is, you should be able to ask for the data, or you should be able to ask for the metadata without changing anything else. And that's what this hierarchy is about. So what that allows you to do is to build some automatically generated web pages so that if you hover over data, that will point you to the data, and that one will point you to the metadata. And this is all automatically generated once you've created the structure. When you click on something, it then takes you off to the data service. Ultimately, it should take you all the way down to the data rather than just the service endpoint, and it should also relate into all of the rest of the vocabulary terms. The interesting thing that this also lets you do is once you've got your standard structure and it's well defined and it's discoverable, you can actually start testing it. So sure, you can just test that the service exists, but you can also start to test that the configuration is correct, that it's got the right OGC service enabled in it, check if the metadata conforms, check if it's got the right vocabulary terms, and check to see if the provenance records actually follow through to correct endpoints. So once it's well defined, we can actually test all the way through the system. It's actually very similar to how a lot of certain non-Microsoft, possibly Google search providers let you log in and actually control the information that you have on the internet about your website, things like webmaster tools. You go in and tell it, this is what I've got, and it then gives you the information about the errors it's found or the information that you've got in the search engine index. So this means we can start to get to real multiple reuse. So for eReef, we'll have our standard stack of data, central node and portal, but we can start to plug in other consumer nodes very, very easily off to the side of this. Other data providers can come in by meeting the same sets of requirements, and we can keep delivering all of the things that were already existing, but have this additional layer sitting over the top of it as well to enable much greater reuse. So this then means we've got much greater discoverability and availability, and you can, through these services, you can start to really discover what exists, where, how, when it's available, and when it's updated. But the ecosystem community and science community really needs to change how it thinks about data and needs to think about data as being online rather than offline. We've been through this transition with email. Everyone used to download their POP email and protect it on their computer and synchronise it every now and then. We're now used to email on tablet, phone, webmail, Outlook, etc. So the same transition we need to have in data. And through attribution and licensing, I think this is starting to happen a lot more. So in summary, we've got the standards already, we've got the services and tools. A lot of the base level OGC type services and tools already exist. The attribution and licensing is mostly solved. But we need to start connecting this into the way that the internet already works. And some of these standards and tools are now in development and on their way. Thank you.
So you're using ontologies essentially for doing data management. Have you done any inferencing across that to see if there are missing data holes in your data collections, or whether there's misrepresented data collections or things that have been tagged which are inconsistent with how you've done your ontology?
This is mostly, it's not so much about ontologies at the data level, it's ontologies at the service level, which are a much smaller set of things to define. So quite often, ontologies and semantics tend to be done, it's a triple store of detailed data and individual bits and pieces. But defining a service in our context, we need to stay to the OGC standards essentially. So we've got a very discrete set of things that we need to define and a discrete set of services we need to describe in that semantic layer.
Right, so you're not actually describing the individual data sets in terms of
possibly we will get to the data set level, but not the data point level.
No, not the data point, but even with the data set, you could imagine that you could identify data sets which are inconsistent with each other because of the data models behind that.
That may be what becomes possible once people start to analyse it, yes. So we're not going to be doing that in advance. We're not trying to build a single consistent water quality layer for the country, for example. We want to provide a discovery layer that allows the next level of processing and analysis to happen by researchers.
Right.
Okay.
Yeah, I'm always amazed how much is going on underwater. So, and I just figured out there was a talk on INET, I think, on the Canadian Ocean Network. Are there any interfaces between countries? Because of course, it's the same ocean we're measuring, of course, on opposite sides, but there must be some interesting correlations perhaps too.
Yeah, and the ocean space especially is actually quite well coordinated, and I just went to a marine data and informations conference in Italy a couple of months ago, and that was all about ocean data information and ocean data management, everything from QA procedures to sorting out problems with ship names and duplicates, and so the oceans community is actually quite well integrated.
But no common interfaces to
No, definitely. There's common data standards. There's some ocean data standards. That's in the ocean space, so you need a big ship to go and do ocean stuff, and it's a nice small community.
Okay.
Coastal space is a mess. So that's where we need to be much more generic in the coastal space.
Brian mentioned this morning already that having different data sets together produces a lot of additional science. You mentioned sort of the coastal data, you mentioned other data. Isn't already at the point where you basically for a piece of coast you would request sort of the measurements, but also the metadata and so on.
No, we're not even at a point.
You guys going to end up curating this stuff?
Hopefully not.
Because the ironic thing I noticed is you said, oh, we're going to give it to environment, not and then I said, well, but we're not the environment in the next ministry. So.
That's not the word environment as a ministerial sense. That's the word environment as a domain. So that's not actually, there happens to be a Department of Environment now. That's a coincidence rather than anything else. So it's really the domain is data.gov.au. And we're using that namespace. We're not putting anything with them. The idea is a discovery point and a master catalogue rather than the data itself. Which is a slightly different model from Stuart's approach, but the
Why will they be lucky to survive 10 years?
Because you have even a smaller size community, it's completely fractured to tiny little astronomy. So that's
But it is actually what you want environmental data to be.
Well, it is, but you probably want it stored at an organization that has a long half-life as opposed to a short half-life.
The benefit, that's true, but the flip side of that is a lot of the groups we're working with are government organisations, and they have a legislative right to maintain that information. Actually, a legislative...
They have a legislative...
Sorry, not a right, a legislative need to maintain that information. Requirement.
But I would argue, having just watched what's going on in Queensland right now, that could change like that.
Yes, it actually, in Queensland, for example, there's actually a legislative requirement to release, and there always has been, all data that's collected by the state government. It just hasn't actually been done before. So
it could be released, but if it's not curated, then it's going to die. That's the problem. Because there's not big enough organization.
And that's what TERN is also trying to do. So TERN then is the other side of that, trying to create national collections where there's really significant information to try and bring it together. And that's where we do manage infrastructure. So it's a bit of a combination.
Last question about linked open data. I'm still trying to understand whether it's actually going to deliver things. You talked about it, you talked about ontology at the service level. Have you any compelling examples of wins that you've generated doing all this work?
That's the discussion we're having right now. We need to build some real demonstrations of the components we've got to show the what you can do on the discovery side. So that's in process at the moment.
Has anybody on any data set in the world any convincing ones? I haven't seen any.
Yeah, I'm probably not the right person to ask.
Then why are you doing it?
Yeah. My team is probably the right group to ask.
Sorry, can I just ask you to expand on that? You said that you don't know of any example of any environment.
There's a lot of people doing linked open data. Like John Berners-Lee in the UK has convinced the UK government this is a good thing to do. I actually don't know of any convincing examples where you've had huge wins by doing all that.
Is that just too early days?
Well, early days, it's a few years. I mean, how many is early days? And I think semantic web's been around a long time.
The best example I know of, whether it's successful or not, you'd have to ask them, the entire BBC website is linked data, and their entire data system is linked data. So whether it's successful or not would be a very interesting question for them.
British Library has also done it. I should ask them.
Yeah. So there are examples, but maybe it's not linked open data, it's linked data. BBC would be relatively internal, but they're not public delivery. But yeah.
What are you looking for, Tony? I mean, are you looking for scientific discovery, or are you looking for, I managed to do this one before?
Well, I mean, okay, so whether it really is useful, or whether it's an over-ambitious thing, because, the ontologies change, and you have to maintain them and all that. I just don't know, right? And so I'm trying to figure out, and it would be nice if I had some examples.
Yeah, well, linked open data is not ontology. Linked open data is a much simpler system.
Well, so they tell me, but you still have to have a vocabulary, and you still have to have these object interrogates and all this sort of stuff.
Yeah.
So it's very similar to RDF.
Yeah. At that level, yes, but...
And I don't understand whether there is real value. There may be.
Yeah.
I'm agnostic on this. But I keep waiting for the killer example.
We'll build it for you.
No, yeah, okay, great.
Environment data, we see more and more integration across the disciplines to better understand the Earth system as a whole. So, especially in terms of the ocean, and connect with the other parts of the biology and chemistry of the oceans. And this can be done directly by using the data, or indirectly by assimilating the data into the models, or even using the data to evaluate the climate models that are used to do predictions and projections for future changes. And here, I'm going to give this talk on behalf of our working group and international partners. So I sit here in Melbourne, but I work for the ACRC in Hobart, but I also do a lot of international collaboration. And this first slide is just to highlight the importance of the ocean for the climate system. So just to remind us that it's 70% of the Earth's surface and has an average depth of 4 kilometers. And temperature and salinity data is really essential for us to understand the energy and water flows within the climate system, and also to understand the influence of natural changes, but also human-induced changes. And if you look into where the excess heat that comes into the planet is stored, you can see that very little, the planet atmosphere have very little capacity to store heat, and also very little heat is used to melt ice. And so most of the heat is actually stored in the ocean, and this kind of slows the surface warming, but at the cost of ocean warming. And once you start warming the ocean, it causes thermal expansion, and you can also contribute to sea level rise. So as you can see, the understanding the ocean is really key to understand climate variability and change. Very recently, a vision of a few oceanographers turned into reality when the Argo profiling floats array was deployed in the mid-2000s. And this is the first ocean observing system designed to monitor climate. And this was only possible due to technological advances, but also because of international cooperation. And this is kind of a step change in terms of accuracy and coverage. So you can see that before the Argo floats in the mid-2000s, we had poor coverage, and we also have, I'll tell you in a minute about the historical database. And you can see up there that most of the floats here come from different countries. So each color is defines one country. So it's really a truly international collaboration. And most I think of this data is funded through projects, science projects. So at the moment, the design of the array is to be, the optimal design is about 3,000 floats. We have a little bit more than 3,000 currently. And what happens is these floats sit at 2,000 meters, and every 10 days they make a profile up to the surface, and with that data is transmitted to the satellite, and the satellite to the computers. And the 10-day profiling cycle is to average over noise. And each float lasts about 3 to 5 years. And that data is available publicly in many different websites. And there are two types of quality. The real time, that's once you get, and the data is transmitted to the satellite and is available on the web. But then if you want to do more serious science in terms of climate, you have to wait for the delayed mode that takes a little longer to become available. And there is also a system to track the impact, the usage, in terms of what kind of science is being done with the data and the citations. Once now that the system is in place, the challenges are to sustain the number of optimal floats and also to expand the array. For instance, below the 2,000 meters of marginal seas, the coastal areas, and also under the sea ice coverage. And also to include other types of sensors that can look at biojet chemistry, for instance, like oxygen depletion. So this is, although this is a very successful effort, it depends, it's not error-free, and it depends on the user, the scrutiny of the users. for the data and the metadata to give feedback on the problems that are found. So one of the problems that they found and that initially they attribute as a recent cooling was actually a firmware problem. And one type of the Argo float was American float, and it was mostly deployed in the Atlantic Ocean. And this firmware problem caused the whole Atlantic Ocean to be cooler than everything else. And once they found this problem and was corrected, and then that was okay. But it intrigued, it caused a lot of problems too, and intrigued many people.
But you remember recently they discovered a particle that was moving faster than light. It turned out to be something similar.
Yeah.
Sort of technical glitch.
Yes, it was a technical glitch. And then more scrutiny, also in the dominant type of Argo float, they found that these pressure sensor drifts. And they kind of knew about that, but they didn't know that there were so many different types of pressure drifts. And this has caused some impacts also in the science. And once this was made, this kind of thing was made, they paid attention to the Argo steering team, because the Argo data management had a system in place that was very effective. They were able to fix all these little problems, for drift correction in a very timely fashion, because they could track everything they've done, and also because they had a system that was working well, but not perfect, but and with this kind of feedback, they were even able to improve how they operate and keep track of things and make the people who provide the Argo data to comply more with the specifications that they need, because some of the mistakes also were just they were putting the wrong technical information. And this also translates into science impacts that were like artifacts. But then the story is very different before the Argo array, because the Ocean Observer System was never designed to monitor climate, and it was mostly opportunistic and to do weather forecasts or for Navy operations. And it contains a variety of instruments, and the mix of instruments changes with time, as you can see in this plot. And they also have different biases and different accuracies. So, for instance, the top instrument there are two actually, the bottles and the CTDs are the most expensive, but the most accurate. So those ones you only get if you go on the ship. And the research ship. But those down there, the XPTs and the MPTs, they can be launched from any vessel, commercial vessel. So ships usually collect along ship lanes. But they don't measure depth directly. They infer depth by a fall rate equation. And this has caused a lot of trouble as well, because we need a longer record to understand climate. And so these instruments were never really, the observer system was never really designed for that. And as you can see in 2007, very recently, when these XPT data were closely scrutinized, compared with the most accurate data, they also found bias problems, and that led to this big bump here, that climate models couldn't do it, so it generated a lot of trouble. And it was a key uncertainty in the IPCC AR4 report whether the models were good enough to simulate variability or not. And it turns out that that paper that found the bias in the observations just came just after the IPCC report was published. So we start paying more attention, and since the bias were discovered, up to now there are about 8-9 corrections that were proposed, and they all kind of differ from each other a little bit, as you can see here. And the frequent question asked by the users: what we should do, what we should use, what is right, what is wrong. And one of the major problems we face is because lots of the data in the database they were provided without metadata. And it's really hard to track what type of XBT data you're collecting, from which instrument. So, and you need that kind of information to devise a bias correction more, or at least refine it better. And then, as you can see, the red on the top figure shows that lots of data in different ocean parts have missing metadata. It's about 50% of the XBT data. And the other problem is the substandard data quality. And there are many groups that do automated quality control, and we kind of duplicate efforts, but at the same time, these automated tests are not really effective in removing the bad data, as shown in this figure. So they have this long tail here, while once you clean the whole data, they should have more like this Gaussian distribution. And a complete, Susan and Anne performed this pilot study in the Indian Ocean, so and that colleague, so they manually quality control all that ocean database. It took about 2 or 3 or 4 years, and they show that about 16% there is about 16% of bad data included in the database. And if we translate that to the world ocean, that's about 1.5 million profiles of bad data sitting there. And this has implications, as I showed before, for analyzing climate signals that are very sensitive to even small errors. So with that in mind, some oceanographers decide that we need to do something about the historical database, and we starting to propose a coordinated approach in the way Argo kind of operated to quality control these about 13 million profiles in an effective way, and so we can maximize the consistency and improve add value to this irreplaceable data set. And one of the things we would like us to do is to include proper uncertainty, because in some scientific areas we need not only the data, but we also need to provide the errors. And it has not really been done that before. So we had our first workshop back in June, very recently, and we have another 2 planned for 2014. And we are going to start discussing more about the next steps. So just to provide a quick overview, we will have a global data assembly center. There will be the input point, the start point, but also the end point for the delivery of the product. So we will start already with this World Ocean database that has consolidated about more than 18,000 data sets into one format. And then we have a strategy to tackle how we are going to work back with the data. And then as I said before, the World Ocean database will be also the reassembly point where we will put the things together and be available to the public. At the moment, we are discussing in terms of the automated quality control. That will be the first step once we get the data. So we need to agree in terms of standards. So to to get there before that, we are running benchmark tests. So we have a data set with known quality, and then all the different groups are running their QC tools on that known quality data set. And then we are going to discuss the results and see what's good, is bad, and try to come up with perhaps the best approach for automated quality control method. And then this method, the automated method, is going to flag profiles, which will have to be manually QC, and we estimate it will be between 10 and 30% of the data set that will be looked at by hand. And we will need local experts that design it based on certain criteria. And after that, we will have to deliver the data. And for the data we cannot recover the metadata, we agreed that we might be able to provide what we call intelligent metadata. So it's in a way of trying to come up with an estimate for the error for that kind of data. So we are still in the very beginning, and we will not be able to do this without having a different mix of people, from like scientists and technical personnel and managers. So we need all these type of people to make this happen, and similar to what happened to the Argo data for the recent time. And that's it. Thank you.
Thank you. So this actually reminds me of what we're not always good at doing, comparing data sets through VO framework, because we use, obviously, uniform data standards, but this is interesting because you're going sort of that step further with uniform sort of processing quality control pipeline, which sounds like it would be very difficult to get sort of agreement amongst all the international groups. So has that been a challenge?
Actually, not so far. Like, everybody seems to agree in that the automated, what we have in place now doesn't work well, and we need to improve. And it seems that we are all talking the same language in terms of how much we want to get that improvement. So we didn't have any problems so far. It has been very harmonious, and that has helped us to keep going. Yeah. So that makes a lot of difference.
Yeah.
So my question is, who pays for this? Because scientists get a paycheck anyway. Technicians and managers expect to get paid to produce something, and don't only get paid by universities or similar. So how do you get this level of expertise to deliver?
I think our strategy is going to be like this, because there is government doesn't invest this in the long term. Like all the Argo data is being collected by project, short-term project. So it science is driving that, not the other way around. So in terms of this, our strategy is to put a project proposal together and get endorsement from some intergovernmental institutions to give more weight for what we plan to do. And then with that, for instance, I'll get that and use that to apply for funds here in Australia through grants. And this will be done at a country level, so that's the number 2. And so the project will be funded at a country level, not at own. Because that's the only way right now. So, because I don't think we have any other way, do we?
If you know, please put a slide up.
Yeah, I think this is something that has to change.
I mean, for this kind of project, though, is the UN a source of money to feed results in, or is that a conflict of interest? Or?
No, I'm actually, we are getting sponsors, but to help us get the working group discussions and get the plan together and what we need together, the proposal together. But when it actually comes to doing the work, then we will have to individually submit proposals. Just
That will be increased type funding in Australia, most likely. In
Yeah.
Europe, it's EU funding. In the US.
the framework, in Europe they have a pretty big effort in terms of infrastructure. It's more like, because like my supervisor used to say, this is not sexy. so it's hard to get money for this. But Europe seems to be heavily investing in infrastructure, and the guys that do understand the importance of having infrastructure support for doing the science, and they have this Earth system way of thinking. So they are putting resources together in terms of computers and everything. So they don't, especially now that the budget is tight. So they're trying to eliminate duplication, see what the community needs and invest. So I think the next framework will be 8, actually 7, 8. Yeah, Horizon 2020, yes. We hope to get some money out of there.
Time for one more question. Alright, get ready for the panel discussion. So for the panel discussion, we're obviously going to welcome back the speakers from this session, but also Tony Hayes, who spoke this morning, and Darren Croton, who also spoke this morning, and also George, and I hope I get your name pronounced correctly, Jogowski. So for those who, I guess everyone's been introduced today except for George. So for those who don't know, George is a professor of astronomy at Caltech, and was actually one of the co-founders of the Virtual Observatory Framework, as well as helping sort of develop the field of astroinformatics. And he's interested in challenges and methodologies sort of relevant across scientific disciplines in this sort of big data era, which is exactly what we're going to talk about now. So this is very much intended to be sort of a panel and audience discussion. So I encourage lots of questions and comments, don't hold back, and I guess just to frame the sorts of areas that I could see there being a lot of sort of commonalities and overlap across disciplines. You've got sort of, I guess, a number of broad categories. There's sociological sorts of challenges, dealing with sort of community skills, uptake, things like that. There's the actual data infrastructure itself, where there's a lot of challenges in storing and analysing and sort of transferring data sets, or big data sets, and also a large number of different data sets. And then actually extracting the data from the sort of information and knowledge from that data through data mining and also visualisation. So there's a lot of sort of ideas and areas where we could sort of have a bit of crosstalk. And since George hasn't spoken yet today, I thought I would open with a big picture question directed at George on the sort of main sociological challenges from your perspective, both community sort of, I guess, uptake of these new technologies, as well as community contribution through things like providing data and tools and skills, and any other sort of cultural sort of barriers to getting the most out of technology.
So how many hours do I have? Another wise thing that Jim Gray used to say is, may all of your problems be technological. And certainly that's true. If you think that doing, say, unsupervised clustering and visualization in 300-dimensional parameter space is hard, try dealing with established astronomy professors. it's actually very frustrating to see that relatively slow uptake of technologies and methodologies which I think are one of the most profound transformations, if not the most profound transformation in the history of science that's brought by computing information technology. And so I don't need to preach to this particular choir, but I've been thinking about this for some time, and I think the fundamental root cause of this is the discrepancy of time scales. That we have never in the history of humanity had transformative technology that evolves so rapidly that people cannot adapt to it in an efficient, fast fashion. That education is way too slow. It's like 20 years for sitting in the classroom. Career is 50 years. Universities evolve on scale of centuries or millennia, if at all. And very soon, after not too many Moore's law cycles, you have a real problem. And I think that's the ultimate reason. We do not teach students these tools that are necessary for the 21st century because professors don't know it. Most professors don't even know that they're needed. That has all kinds of consequences, not just the slow uptake, but also the professional recognition, which is, I think, a real problem. That people who straddle the main field like astronomy and applied computer science engineering are the most valuable people in this era, and yet they don't belong to either pigeonhole, and they tend to get screwed in career sense. And that is inevitably going to lead to a brain drain, and so we're going to start losing the people we need most. And there's all manner of other things. So what you can do about this? Scientists respond to two different stimuli, resources and results. And even though we all complain about funding, in my experience, actually governments do get it, and funding agencies get it. They recognize the connection between information, computing technology, and prosperity, and so on. It's the professors who don't get it. People like Alex and Pepto and myself, we're freaks. Our colleagues think we're nuts to do this kind of stuff. And most of them just couldn't care less. When we started these meetings in 2010 in Pasadena, it was a nice meeting, about 100 people, everybody had a good time. We had a panel just like this. And I pointed out that the number of Caltech professors in the room, other than myself, was 0. Because they know what they're doing. They didn't need all this new stuff. And so that's the problem that we're facing. Okay, so that's as far as generic stuff. And in terms of bridging the gaps in different disciplines, I always keep hoping that other fields have solved many of these problems, so you have to go to e-science conferences and talk to them. And much to my never-ceasing amazement, astronomy seems to be in cutting edge. So we got our act together much better than most other fields. And bioinformatics, medical informatics has infinite amounts of money, and they look at astronomy with awe. How did we get our act together that we can share the data and have common formats and don't clutch to the data? And of course, there are many reasons for this, but it's a big struggle. All sciences have more or less the same problems dealing with knowledge discovery and management of the data sets, and I think it's crucial to have as many interdisciplinary connections as possible. I think that's the best thing we can do in meetings like this.
So you didn't answer any of the questions.
More data are needed.
Well, I mean, maybe I can just say something provocative. So how do you make these people change? I mean, you're forcing them to change by giving them something they want. By don't give them any choice about how they have to get it.
Resources and results.
So Apple is a good example, I think, because they created a product that was highly desirable, but locked everybody into their ecosystem. Everybody was happy to jump into that hole because they wanted that product. So if you produce something that they really, really want. So Tau is, in some sense, one example. It's not the motivation, of course. The motivation is to make data accessible, but by putting it in this place and in a particular way, we're forcing everybody to go there to pick it up. You know, so if you give everyone too much freedom, then you don't get anything.
Jim had another phrase, you wait until they become desperate.
So you ain't rather
SK.
So, I'll make a comment and then a question. So, two comments, but one way to do it is to force the issue. And in health, it's going to be much easier. You're the NIH and you're putting $80 billion a year into health. I think you can demand, say, this is the data format you will use, get on with it, and you need to have a nice open data format, something like www come out there that I'll use. I think an interesting question to me is, right now we are doing this. We see lots of fields that have e-data problems. There's commonality. Industry, as near as I can tell, is largely uninvolved in this. And if you're going to really make something take off, we need to somehow get industry involved. And I don't really know how to do that right now. I guess I'm interested in the industry side, there's at least one of you, but maybe the people who interact with industry. How do we get industry to go in and say, this is actually $1 billion problem? Because my guess is it is $1 billion plus worth of stuff going to happen in the future. It just hasn't happened yet.
really. Okay. I would say a couple of things. One is that I think industry is concerned about big data, obviously, and there are two initiatives that I can talk about. I mean, I spent 5 years of my life trying to do a standard in GIBS, and that was really the most unproductive meeting I've had for a long time. So I don't wish to do that again. But industry, SAP, IBM, Microsoft, and a few others, with the OASIS standards body, are doing something called OData. This is a very lightweight, minimum scale of interoperability of data sets based around XML and Atom and various other well-known web standards. I don't know whether that's sensible or not, but there's one thing that they're looking at. They're not really looking at RDF at this moment. I don't think they've made a decision. There is one, I usually joke that it's the only thing Microsoft and Google have agreed on. It's a thing called schema.org. Does anybody know schema.org? Okay, so it's a very, very lightweight sort of semantic information. So if I'm looking for Casablanca, from my history of what I've been looking for, I'm really looking for the movie rather than the North African town. And yet the web search engine has no knowledge. It just goes Casablanca, it doesn't know what this website contains. So what schema.org is some micro format that the webmasters can put into their websites, specific vocabularies, so the search engine knows that this is a thing about movies, this is a thing about North African towns. And you can extend it, and that's at least a pragmatic first step towards something semantic. So I think something semantic is needed. I'm just not sure whether we need the whole of the semantic web type technologies. But that's industry certainly looking at that. And schema.org is a pragmatic first step. And the other thing is a lightweight standard that big companies can agree on, because interoperability between these silos is important. And maybe OData is interesting. I funded a small little project in Ireland, which was actually looking at how the British Library have a lot of linked open data in RDF, and how could we make that compatible with OData. So if people are interested, I can make that available. I'm not sure I can summarize the conclusions. And the last thing I'd like to say is that, listening to your talk about the dirty data, I worked with the AmeriFlux community. These people have flux towers. So typically a professor and a couple of students own this flux tower in a field outside Chicago, or a field wherever. All right, and they measure various things every 6 hours, and it's stored in flat files at Oak Ridge National Laboratory every few hours. And not much data, but if you want to get a weekly average from that site, it's very easy to do. You know what you do? You tell your student to go and get data, and they spend hours compiling the weekly average because students are cheap. So we actually borrowed the thing from Alex and Tim Gray's SkySIRO, and we put it all into a relational database, disguised it with a data cube, so even a university professor could use Excel and not have to ask his students to do the analysis. And that had two effects. A, it made it much more visible, and it's now supported by DOE. And B, much more useful than data from one tower is data from 10 in a region. But that has other reasons, because instead of a professor and 2 students on the paper, you now have 10 professors and 20 students. It's a 30 author paper. And some communities have changed, like particle physicists, write in hordes and have pages and pages of authors. Other communities haven't changed, so there are sociological changes that need to take place. And I think in SkyServer, the most cited author is a grad student who left the field, right? With the Sloan Digital Sky Survey.
Probably so.
Just thought I'd follow on that one. Just in the example of the Earth observation domain, there are a couple of changes that are occurring that are engaging industry strongly at the moment. One is I was in Paris for the commercial satellite conference, which is all the commercial satellite providers there, and I was asked to talk on where I saw things going from a government perspective. And I highlighted that they were working on an old business model. Their old business model was sell a very expensive scene to a very deep pocket customer, and that they really needed to have a look at where mobile phones and the web and everything was moving. It's all apps. It's all people paying $1 for something that does what they want, rather than paying $1,000 for something that does what they want, plus a million other things they don't want. Right? And that they needed to get into selling pixels, or time series pixels. And it was really interesting. I've had follow-up from a number of industry sources, industry big players in the satellite community since. One of them, the DMCII consortium from Britain, is actively planning launch in 3 years' time of a Landsat equivalent set of satellites, a constellation, and their business model is selling daily revisit at 4-metre resolution for every part of the planet. And their idea is not to sell scenes, they're going to sell a service to an individual farmer. Get your farm imaged every day throughout the year. You might be quite willing to pay $1,000 for that to track your crop vigor and that sort of thing, but it's totally changing the way they're thinking about the kind of big data services from, it's all about giving people the data and then they do what they want with it. It's actually selling services from that community. The second thing is I had a phone call this morning at the airport from the head of Digital Globe, which is one of the biggest, is the biggest commercial satellite provider that sells primarily to the US military. And they're following what we're doing with the data cube in a very interesting way, because they see the opportunity to on-sell, in-app purchase style thing where you get your shallow water bathymetry using Landsat at 25-metre resolution for free. But if you wanted a 10-centimetre resolution, you press a button and you buy the digital globe and bathymetry, and it feeds it through the same algorithms. So they're quite interested in integrating with governments in that sense and having seamless commercial, so government provides the basic infrastructure, just like we do with roads and rail and everything else, and they build and value add on top of that.
I think the other thing with the industry question is that what's happening in the environmental data space is that we've all delivered OGC services. Industry doesn't care about OGC services. We're all kind of build all these systems, delivered our data, and got fantastic.
Can you say what's OGC?
Open Geospatial Consortium. So OGC defines a collection of standards. Probably one of the more familiar ones is KML. So it defines a number of geospatial standards for how to deliver information. So it's the common way to deliver environmental information, at least. And you can get open source tools to deliver OGC services, which deliver you a map layer, a rendered map layer. You get catalog services to deliver metadata, and it can be either open source tools or commercial off-the-shelf tools. So in the GIS space, most GIS servers, things like from companies like Esri, allow you to publish these services, web services for delivering data. But search engine providers, Microsoft, Google, Yahoo, etc., won't traverse a web service to make your data discoverable. There's no point in a search provider working out all of the different command demands that it has to pass to an agency service to return something that can be indexed in a search engine. So I think we need to step up in our information delivery space to understand what industry wants as well as industry hopefully understand what we do as well.
You would think there would be a huge value add to take your satellite providers, Microsoft or Google, which do use KML type stuff, and manufacture data from disparate sources to give you something that goes beyond just the satellite. And that's the thing I don't see happening. And I would expect there to be a huge commercial imperative to do that, to make a lot of this stuff happen outside of Australia. I'm just amazed it hasn't.
They all want to control the entire value chain. That's the problem. They want to own it from the data to the end product because that's where all the money.
Presumably the SMEs, so some SMEs are going to come in and make a split.
Well, there are companies like Esri who deliver services which, unlike some academic communities, the geo community is prepared to pay for these commercial services, a bit like MATLAB. I mean, Microsoft's problem, and Jim Gray actually put the Terra server, it was the first web service which actually had geographical data. And he tried very hard to convince any of our business groups to take it seriously. They just weren't interested because they didn't have a business model. What's the business model? How are you going to get money from this? They didn't realize, as Google did, that getting people's eyeballs on the site is very valuable. So he was then consulting for a small startup called Keyhole Technologies, which was then bought by Google. We served them data from Terra Server. We created Google Earth for them. Pretty good, huh?
So I think we've got a couple of questions from the audience.
This is probably in continuation because I think SAE offers an interesting example how an industry can be engaged because we have very high interest from the industries and very large companies such as IBM, Intel, SGI, Amazon. And we have a lot of help and a lot of resources coming from their side. And the interesting comment was from one of the large companies. They said the SK itself, in terms of the money that you have, is not very interesting because what is $2 billion for IBM or for Intel? But what they are interested is in the public profile project. So if we have things with high public profile, the industry can come forward. So and I would probably even reverse that. As community or as astronomers, I think we are quite conservative in technologies. So we could use ourselves a lot more what's available already in the industry. So the example of that is fixed format that we've been using for 30 years, and the only reason I believe it's successful that it doesn't specify anything. You can use it in any way, but you can't really read it back. And there are lots of good industry examples how you can address that problem and produce a real standard with advanced capabilities. So we should, I think, as a community to be more, and it goes back to actually to education. So as the first professors were educated in the 60s and 70s and kept the same technology on and on and on, we've become a conservative community. So we need to go back and start educating our students modern technologies. Then we'll see the industry.
The students need to educate the professors.
I think that's right. It is happening, but I think we need to reverse it.
Yeah, exactly the point you made, George, concerning the strain. So probably the $1 billion problem could be an advantage. So if you think of getting involved in projects together with business, as you said, and something sell classification of customers to a company that is not worth $1 billion, and have the scientists sitting next together with the computer science guy working on that topic, doing your stuff, could be a solution for the problems we have. So we could get money like they get in biomedicine or in...
Once they're commercial, they never come back.
Could I slightly different? It depends. If it's a project, you start a project with a company, of course it's for a student perhaps a way to get into business, But on the other hand, it's money for the institute somehow, and a project at least that is financed and can get you a little bit further. So I think it might be an option. Of course, it's
Well,
probably
okay, yes.
or a challenge.
I mean, I'm working now with people at JPL, and they're actively looking at possibilities of working with the private industry on problems of big data. And so, but that's an institutional level. I mean, I had students, collaborators who just disappeared in Wall Street or wherever, and they don't come back. They don't even make any donations.
People
because
from
they
the
lose money.
people from the first Astroinformatics disappeared within the last year.
But that's not necessarily such a bad thing if your students go and get things. And I haven't known particle physicists who went and, did these mortgage-backed securities. You remember those things that caused the collapse? Well, they've actually been making donations to science and things like that. So the thing I wanted to bring up was reproducibility. I was deeply impressed that you gave your code, that you've done your analysis. I think that's really brave. Because no,
Max Tegmark.
I don't know. But there was a study done by Amgen. They looked at 53 landmark life sciences experiments done by published in Nature and Science and things. They were only able to reproduce 6 out of 53. So reproducibility, I think, in your field looks much better than in the bio field, which looks actually to be in crisis.
Oh, you want to hear fast testing? So in the galaxy formation business, which I work in, even groups who update their model, 4 years later they publish a new paper showing this new advanced model to compare to their old one. The code has evolved sufficiently that they can't reproduce their results from 5 years ago with the same code, just working them back with the same parameters and stuff. Which is one of the reasons why in science we need to put as many online as possible to make them available. And then you get that theoretical uncertainty in there, that it's not just the scientific uncertainty in how we're producing this data, but there's the technical issues and just the version creep and all this sort of stuff, which changes the numbers and how these results are interpreted.
Well, I think it's not the codes for biomedical stuff, it's the messy experiments and hidden variables. And
Well, 95% is considered competent in that field, but there are 19 experiments which aren't significant that aren't published for everyone that is. And, I feel we were given a lot of crap because our experiment for the accelerated universe was about 99.9% competence, which within astronomy is, we said evidence. Fortunately, the team had the same level of confidence, and together we got 4 nines.
Wow, okay. That's very
So
interesting.
certainly within the project that we're doing right now, this is a serious concern. We're looking at our IoT funds of how do we actually ensure that we've got reproducibility, not just over 5 or 10 years. How do you, the infrastructure is going to change, the computers are going to change, the code is going to change. How do you actually run the same experiments over and over again in a time?
If I could use an example from the environmental space, and Jonathan pointed at this before with the provenance service, and it's a really critical thing for us in the environmental space. I was previously with CSIRO and played a role in the Murray-Darling Basin Sustainable Yields project, which was a massive project commissioned by the Prime Minister, who stood out on the steps of Parliament. CSIRO will tell us how much water there is in the Murray-Darling Basin and who it's going to and who's going to have it in the future. We put together a whole bunch of models, existing models, tied them together, ran scenarios, various climate scenarios, IPCC models, generated 50 terabytes worth of results. Now, I think there were something like 8 billion individual records generated. So even for a scientist to look at one per second for 8 hours a day, 365 days a year, you'd be there for 280 years before you'd even cast your eyes over it, right? And we were producing stuff that was going to result in people's water rights being taken away potentially, or purchases being made, legislation, and facing the real possibility of standing in front of a judge
putting your hand on your heart and saying, I can reproduce that number, Your Honour. We did somewhere in the modelling 3 years ago. I can tell you it's not possible, and that says to me it's not science. Right? We've actually got to get to the point where when we run models, we've got full provenance of the data, the assumptions that went into it, and we can actually reproduce the numbers. And we're actively doing that at the moment, trying to tackle that problem. We've got the same problem with coal seam gas and
Good at. They keep everything under SVN. Data under SVN.
You're showing your age.
It's called GitHub and stuff. Yeah. Whatever, but it's the moral report.
You can't do it with SVN because the problem with big data is that once you start SVNing, you start coding branches that are as big as the original data set, and you quickly run out of space. So we're trying to tackle how do you deal with that in a dynamic data set that's growing all the time. How do you go back 2 years ago and say, if this engineer designed a bridge on the basis of the water data in the system, I can actually tell you what answer he would have got on that day.
But presumably something like what I would say we all use, or all Mac users, Time Machine, which has an incremental.
Potentially, yeah. But
well, that's how I deal with mine, as I actually don't use SVN all the time, but I do have that, so I where it looked like in my machine on that day.
But I was in University of Melbourne on Thursday, and the Deputy Vice Chancellor of Research said they had all this data from the Murray Darling Basin, but they've lost the metadata. And so it was 50 years of useless data. It was exactly as you were describing it. And they were trying to reconstruct the metadata. Scary stuff.
Oh, it's much scarier.
At least I had it
We know it existed once. It's the guy sitting in the corner.
Okay.
We've got one here and then Chris.
It's just a comment. One thing which I never see coming out of these panels, since the process of informatics, well, besides these big problems, which do not change much our daily life, we have other problems. Here we have people from the oceanographic community, from the coastal community, from the geoscience community. And I always have the feeling that there is a lot which they can learn from us and which we can learn from them. But this never happens. So I think a good question which I would like to be addressed in this system. Let's forget about companies. If they have interest, they will come to us. Or if we have an interest, we will go to them. It has always been like that. It's not to us to change this pattern. But how about beginning to understand how to exchange information among different communities? This is different thing. For instance, he was mentioning something about the georeferencing thing. Astronomers have solved that with the ELPs or multi-scale resolution. I think with a higher degree of precision. We never interact with that. The coastal stuff is a sort of virtual observatory situation. You know? So there is a lot of lessons which can be learned reciprocally, and we don't have the space, the venue where to organize an effective exchange of information. I would like to discuss also that.
Okay, so just to answer you, I think that the way that I'm doing it in my little project, I've got basically biologists and astronomers working in the same project and actually talking to each other. They're doing imaging. Okay, so hey guys, let's compare those. But that's the only way that I think it will work. If you actually see people into a common project to address a common goal, that's the way.
This cannot work on a large scale.
On a large scale, that's an issue.
Yes, matter way to do it on a larger scale.
On a large scale.
Yes, I had one more question on the reproducibility side. Are we actually archiving enough? Because it's not just the software that changes, it's the personnel, and it's also the hardware, as John's reminded us with the PDP-11, just a little bit before my time. But I started with a TRS-80, so I love cassette tapes. With new cloud computing infrastructure, one of the options is virtual machines. And should we be archiving the virtual machine that we performed our experiment on as part of that reproducibility?
What happens when the service provider goes away?
It's also quite difficult to reproduce something which is using multiple virtual machines in the cloud because the load is unpredictable, you don't know who else is using the machine. So it's actually even more difficult, I think.
I should add that Murray-Darling example, we had 80 different models. Some of them were running on Windows 95, some were running on DOS, some were running on Unix, there were a whole range. We had to use virtual machines to get them all to run together in that sense. And we did use Subversion as a solution to actually archive them, it's a real challenge. We had one situation where we had a whole bunch of data on tape, and it was only because we had a what we call a bin diver at work, a guy that trawls through the trash and takes the interesting things that are in the trash home, that we managed to find a reader for that data because it was in his garage. But it's going to be increasingly an issue. I talked about the stack of CD-ROMs before. Well, we'll pretty soon be in the state where we're not going to have CD-ROM readers because we'll change the format again.
Again, this sort of emphasises the importance of actually having librarians, people that specialise in actually managing this information and change management of basically the way information is stored and kept in archived properly.
Okay, so in universities, all universities love libraries. They have a research library, which used to be the centre of the university. But actually, my students in engineering and science never went into the library other than for a place to chat, Wi-Fi, quiet place to work, warm in winter. And you can do that in the US, in Starbucks. I learned that Starbucks didn't work so well in Melbourne. But you can imagine the equivalent. So why do you have librarians? And they actually, I think, their role is to be the guardian of the intellectual output of the institution.
Yes.
And they need subject librarians to work with scientists to do something about the data.
Yes.
There's a budget already there, spent at the moment on journals.
Well, secondly, I find that librarians are way more progressive in this regard than most scientists. They really actually think about this.
Some librarians.
Yeah, well, more in response to what Pepe was bringing
The
up.
librarians were sort of in the
Yes.
There are successful interdisciplinary exchanges. I mean, your own group, Alex's, you're working on something with biologists and things like that. This, on a group collaboration level, there is some transfer of knowledge that goes on. And I do go to all these e-science conferences, which I enjoy enormously, but whenever I dig into talking to somebody how to actually use what they've done, usually boils down to the cottage industry approach that actually would be faster for me to develop it from scratch with my friends in computer science. And so it's that lack of scalability, which is why I keep talking about new scientific methodology. So in my mind, it's not astronomers talking to biologists, but this new breed of data scientists, computational scientists, or paradigm scientists, however you want to call them, like in center that Alex has formed, like at CSIRO at Caltech. I mean, those are the people who can perform that interdisciplinary glue and transfer of knowledge.
I'm interested to hear from sort of the people from geoscience, environmental science, about just in your community how, how familiar are people some of the IT requirements for accessing the data, and do they embrace these new sort of web access for data? Is it an uphill battle, and what sort of strategies you use to get your community still on board and accessing information?
I think it's a bit of a mix, and probably in CSIRO we're probably very lucky. We've got a lot of very technical people and a lot of crossover between software engineers and modelers and data people, and we probably have a bit more of that than elsewhere. I came from the state government space, and it's very much using a focus on using internal systems, using the tools you're given, the formats you're used to, and the ways that that's actually where a huge amount of the data is generated and where a huge amount of information exists. The high quality data is collected by state governments, and that's a space where it's very risk averse from an IT perspective, very slow to develop new systems and new tools, and even if we work with state governments from a CSIRO perspective, it's a huge job to transition new tools or new technologies into some of those organisations. And perhaps Geoscience Australia has been through a bit of an evolution recently, but even some of the big federal agencies are very protective about the systems they use and the way they do things, and I think that's a huge hurdle.
Katia, you mentioned that you sort of need to track the science and citation publication output. Do you see evidence in tracking that usage, evidence that the uptake is increasing? And
yes, it's displayed on the website, for instance for ARGO, and it can show the amount of science that is being done with the kind of data and what kind of science is being done and what they are using that science for. And also that fits back into when you need to apply for jobs and fund more flows.
If you think astronomy professors are slow to change, you want to try geologists, right? They work in geological time, and so look, in the geosciences, it gets to what George was saying before. We're actually evolving so quickly in this computational age that previously it would have been generational change that would allow people to keep up. That's not happening anymore. So it's somewhat dependent on people that do cross those disciplines coming through the ranks to an extent. And a good example, Jonathan mentioned that Geoscience Australia has changed in the last couple of years. It was known as the place, the hole that data went into and never came out for a long time, right? It really was. And the whole culture in there was of keeping the data safe and secure and keeping it for someone sometime to use again. But they totally lost the focus that it's bloody useless if you just got it safe and secure and you're not making it accessible. So, I'm a water scientist, a biologist, a chemist by training, came through CSIRO. I've been a hacker in my student days, etc. So, but now I've risen to a point in government where I can actually, I'm not a computer scientist, but I've got enough knowledge of what's possible and how to question the paradigms and whatnot that I can actually have an influence. So yeah, go and do that and come back with the answer. And until you get people that are willing to support that into the hierarchy, whether it be as professors or chiefs or whatever else, you're not going to get the change. So the sooner you can get people that have that crossover skill set, standing up and taking some risks, you won't get the change.
Can I just reply to Giuseppe very quickly? What I would have found interesting, in Microsoft Research I'm surrounded by machine learning people. The person who took over David Heckerman's group, Jim Gray's group is David Heckerman, who used to recruit all the machine learning people in Microsoft Research. So I would have found interesting seeing how the geo community are using Bayesian methods, are using clusters, are using whatever algorithms, and how the astronomy community is doing that. Maybe that's later in the week. I'm sorry, I'll miss it. But that I think is a point of contact, because those are actually, you've got lots of data. How do you find signals of a particular type in the data? And I hope there will be a discussion, and I could go find it on the website. And the last thing I'd like to say, Ray, is I only to wave as a prop, right? I don't really want to take it back. So if you think anybody would like an autographed copy, I'm happy to read it. So,
why don't you hold on to it for a little bit longer, and maybe the first person who pours you a drink or something.
Something like that.
If there's open access wine and cheese out there, and, yes, you don't need to be a data specialist to get it.
No, but we have a joke.
He was on the zip side, Scott. I've never met him.